spawning devices like lasers and transistors, and facilitating advancements in technologies once deemed purely speculative, such as quantum computing. Physicists are investigating how quantum science may revolutionize our understanding of gravity and its relationship with space and time. There's even the potential for quantum science to unveil the interconnectedness of all things in the universe, or across multiple universes, through higher dimensions, which elude our sensory perception. The field of quantum physics arose in the late 1800s and early 1900s from a series of experimental observations of atoms that didn't make intuitive sense in classical physics. Among the basic discoveries was the realization that matter and energy can be thought of as discrete packets, or quanta, with a minimum value. For example, a fixed frequency light will deliver energy in quanta called photons. Each photon at this frequency will have the same amount of energy, and this energy can't be broken down into smaller units. In fact, the word quantum has Latin roots and means how much. Knowledge of quantum principles transformed our conceptualization of the atom, which consists of a nucleus surrounded by electrons. Early models depicted electrons as particles that orbited the nucleus, much like satellites orbit Earth. Modern quantum physics instead understands electrons as being distributed within orbitals, mathematical descriptions representing the probability of the electron's existence in more than one location within a given range at any given time. Electrons can jump from one orbital to another as they gain or lose energy, but cannot be found between orbitals. Other central concepts help to establish the foundations of quantum physics. Wave-particle duality. This principle dates back to the earliest days of quantum science. It describes the outcomes of experiments that showed that light and matter had the properties of particles or waves, depending on how they were measured. Today, we understand that these different forms of energy are actually neither particles nor waves. They are distinct quantum objects that we cannot easily conceptualize. Superposition. This term describes an object as a combination of multiple possible states simultaneously. A superposed object is analogous to a ripple on the surface of a pond that is a combination of two waves overlapping. In a mathematical sense, an object in superposition can be represented by an equation with more than one solution or outcome. Uncertainty principle. This mathematical concept represents a trade-off between complementary points of view. In physics, this means that two properties of an object, such as its position and velocity, cannot be precisely known simultaneously. If we precisely measure the position of an electron, for example, we will be limited in how precisely we can know its speed. Entanglement occurs when two or more objects are connected to be considered a single system, even if they are very far apart. The state of one object in that system can only be fully described with information on the other object's state. Likewise, learning information about one object automatically tells you something about the other, and vice versa. The field of quantum physics emerged during the late 1800s and early 1900s due to a series of experimental observations involving atoms. These observations defied intuitive understanding within the framework of classical physics. One of the fundamental revelations was the recognition that matter and energy could be conceptualized as discrete packets, referred to as quanta, each possessing a minimum associated value. For instance, light with a fixed frequency imparts energy in quanta called photons. Each photon of that specific frequency carries an identical amount of energy, indivisible into smaller units. The term quantum has Latin origins, signifying how much. This newfound understanding of quantum principles revolutionized our perception of the atom, composed of a central nucleus surrounded by electrons. Early models depicted electrons as discrete particles orbiting the nucleus, akin to satellites circling the Earth. In modern quantum physics, electrons are instead described as being distributed within orbitals, mathematical representations that denote the probability of finding electrons at various locations within a specified range at any given moment. Electrons can transition between orbitals as they gain or lose energy, but do not exist between these orbital states. Several key concepts formed the bedrock of quantum physics. Wave-particle duality. This concept, rooted in the earliest days of quantum science, encompasses the findings that light and matter exhibit characteristics of particles and waves contingent upon the measurement method. In contemporary understanding, these forms of energy are neither purely particles nor waves. They are distinct quantum entities defying easy categorization. Superposition. This term describes an object existing as a blend of multiple possible states simultaneously. An object in superposition can be likened to the intersection of two overlapping waves, analogous to ripples on a pond's surface. Mathematically, a superposed object is represented by an equation with multiple solutions or outcomes. Uncertainty principle. A mathematical concept denoting a trade-off between complementary perspectives. In physics, it implies that two attributes of an object, such as its position and velocity, cannot be precisely known simultaneously. For instance, a precise measurement of an electron's position limits the precision of knowledge about its velocity. Entanglement arises when two or more objects are connected to be viewed as a unified system, even when separated by great distances. The state of one object in this entangled system cannot be fully described without considering the other object's state. Information about one object inherently conveys information about the other, and vice versa. The visualization of many quantum physics concepts proves challenging, if possible. Thus, mathematics plays a crucial role in this field. Equations serve to articulate and predict quantum entities and phenomena with a precision beyond the reach of our imaginations. Furthermore, mathematics is essential for encapsulating the probabilistic nature of quantum occurrences. Consider, for instance, the uncertainty surrounding the exact position of an electron, which is often described as existing within a range of potential locations, such as an orbital. Each of these locations carries an associated probability of discovering the electron there. Given the probabilistic aspect, quantum objects are frequently characterized by mathematical constructs known as wave functions, solutions to the Schrödinger equation. Unlike waves in water, which represent fluctuations in water height or sound waves, depicting alterations in air molecule compression or expansion as they pass. A point, wave functions don't correspond to tangible physical property in this manner. Instead, these solutions offer insights into the likelihood of locating a specific object within a range of potential positions. Much like ripples in a pond or musical notes played on a trumpet extend across multiple points and lack confinement to one location. To a physicist, quantum mechanics is one of the three great pillars supporting our understanding of the natural world, the others being Einstein's theories of special and general relativity. Einstein's theories deal with the nature of space and time and the force of gravity. Quantum mechanics deals with everything else. And one can argue that it doesn't matter a jot whether it's evocative, bewildering, or fascinating. It's simply a physical theory that describes the way things behave. Measured by this pragmatic yardstick, it is quite dazzling in its precision and explanatory power. There is a test of quantum electrodynamics, the oldest and most well understood of the modern quantum theories, which involves measuring the way an electron behaves in the vicinity of a magnet. Theoretical physicists worked hard for years using pens, paper, and computers to predict what the experiments should find. Experimenters built and operated delicate experiments to tease out the finer details of nature. Both camps independently returned precision results, comparable in their accuracy to measuring the distance between Manchester and New York to within a few centimeters. Remarkably, the number returned by the experimenters agreed exquisitely with that computed by the theorists. Measurement and calculation were in perfect agreement. This is impressive, but it is also esoteric. And if mapping the miniature were the only concern of quantum theory, you might be forgiven for wondering what all the fuss is about. Science, of course, has no brief to be useful, but many of the technological and social changes that have revolutionized our lives have arisen out of fundamental research carried out by modern-day explorers, whose only motivation is to better understand the world around them. These curiosity-led voyages of discovery across all scientific disciplines have delivered increased life expectancy, Intercontinental air travel, modern telecommunications, freedom from the drudgery of subsistence farming, and a sweeping, inspiring and humbling vision of our place within an infinite sea of stars. But these are all, in a sense, spin-offs. We explore because we're curious, not because we wish to develop grand views of reality or better widgets. Quantum theory is perhaps the prime example of the infinitely esoteric becoming the profoundly useful. Esoteric because it describes a world in which a particle really can be in several places at once, and moves from one place to another by exploring the entire universe simultaneously. Useful because understanding the behavior of the smallest building blocks of the universe underpins our understanding of everything else. This claim borders on the hubristic because the world is filled with diverse and complex phenomena. Notwithstanding this complexity, we have discovered that everything is constructed out of a handful of tiny particles that move around according to the rules of quantum theory. The rules are so simple that they can be summarized on the back of an envelope. And the fact that we do not need a whole library of books to explain the essential nature of things is one of the greatest mysteries of all. It appears that the more we understand about the elemental nature of the world, the simpler it looks. We will, in due course, explain what these basic rules are, and how the tiny building blocks conspire to form the world. But lest we get too dazzled by the underlying simplicity of the universe, a word of caution is in order. Although the basic rules of the game are simple, their consequences are not necessarily easy to calculate. Our everyday experience of the world is dominated by the relationships between vast collections of many trillions of atoms, and to try to derive the behavior of plants and people from first principles would be folly. Admitting this doesn't diminish the point. All phenomena really are underpinned by the quantum physics of tiny particles. Consider the world around you. You are holding a book made of paper, the crushed pulp of a tree. Unless, of course, you're reading an electronic version of the book or listening to the audiobook, in which case you will need to exercise your imagination. Trees are machines able to take a supply of atoms and molecules, break them down, and rearrange them into cooperating colonies composed of many trillions of individual parts. They do this using a molecule known as chlorophyll, composed of over 100 carbon, hydrogen, and oxygen atoms twisted into an intricate shape with a few magnesium and nitrogen atoms bolted on. This assembly of particles is able to capture the light that has traveled the 93 million miles from our star, a nuclear furnace the volume of 1 million Earths, and transfer that energy into the heart of cells, where it is used to build molecules from carbon dioxide and water, giving out life-enriching oxygen as it does so. It's these molecular chains that form the superstructure of trees and all living things, and the paper in your book. You can read the book and understand the words, because you have eyes that can convert the scattered light from the pages into electrical impulses that are interpreted by your brain, the most complex structure we know of in the universe. We have discovered that all these things are nothing more than assemblies of atoms, and that the wide variety of atoms are constructed using only 3 particles: electrons, protons, and neutrons. We've also discovered that protons and neutrons are themselves made up of smaller entities called quarks, and that is where things stop, as far as we can tell today. Underpinning all of this is quantum theory. The picture of the universe we inhabit, as revealed by modern physics, is therefore one of underlying simplicity. Elegant phenomena dance away out of sight, and the diversity of the macroscopic world emerges. This is perhaps the crowning achievement of modern science, the reduction of the tremendous complexity in the world, human beings included, to a description of the behavior of just a handful of tiny subatomic particles and the 4 forces that act between them. The best descriptions we have of 3 of the forces, the strong and weak nuclear forces that operate deep within the atomic nucleus, and the electromagnetic force that glues atoms and molecules together are provided by quantum theory. Only gravity, the weakest but perhaps most familiar of the four, does not at present have a satisfactory quantum description. Quantum theory does admittedly have something of a reputation for weirdness, and there have been reams of drivel penned in its name. Cats can be both alive and dead, particles can be in two places at once, Heisenberg says everything is uncertain. These things are all true, but the conclusion so often drawn that since something strange is afoot in the microworld, we are steeped in mystery, is most definitely not. Extrasensory perception, mystical healing, vibrating bracelets to protect us from radiation, and who knows what else are regularly smuggled into the pantheon of the possible under the cover of the word quantum. This is nonsense born from a lack of clarity of thought, wishful thinking, genuine or mischievous misunderstanding, or some unfortunate combination of all of the above. Quantum theory describes the world with precision, using mathematical laws as concrete as anything proposed by Newton or Galileo. That is why we can compute the magnetic response of an electron with such exquisite accuracy. Quantum theory provides a description of nature that, as we shall discover, has immense predictive and explanatory power, spanning a vast range of phenomena from silicon chips to stars. Quantum theory was precipitated, as is often the case in science, by the discovery of natural phenomena that could not be explained by the scientific paradigms of the time. For quantum theory, these were many and varied. A cascade of inexplicable results caused excitement and confusion, and catalyzed a period of experimental and theoretical innovation that truly deserves to be accorded that most cliched label, a golden age. The names of the protagonists are etched into the consciousness of every student of physics and dominate undergraduate lecture courses even today. Rutherford, Bohr, Planck, Einstein, Pauli, Heisenberg, Schrödinger, Dirac. There will probably never again be a time in history where so many names become associated with scientific greatness in the pursuit of a single goal, a new theory of the atoms and forces that make up the physical world. In 1924, looking back on the early decades of quantum theory, Ernest Rutherford, the New Zealand-born physicist who discovered the atomic nucleus in Manchester, wrote, "The year 1896 marked the beginning of what has been aptly termed the heroic age of physical science. Never before in the history of physics has there been witnessed such a period of intense activity, when discoveries of fundamental importance have followed one another with such bewildering rapidity." But before we travel to 19th century Paris and the birth of quantum theory, what of the word quantum itself? The term entered physics in 1900 through the work of Max Planck. Planck was concerned with finding a theoretical description of the radiation emitted by hot objects, the so-called black body radiation, apparently because he was commissioned to do so by an electric lighting company. The doors to the universe have occasionally been opened by the prosaic. We will discuss Planck's great insight in more detail later in the book, but for the purposes of this brief introduction, suffice to say, he found that he could only explain the properties of black body radiation if he assumed that light is emitted in little packets of energy, which he called quanta. The word itself means packets or discrete. Initially, he thought that this was purely a mathematical trick, but subsequent work in 1905 by Albert Einstein on a phenomenon called the photoelectric effect gave further support to the quantum hypothesis. These results were suggestive, because little packets of energy might be taken to be synonymous with particles. The idea that light consists of a stream of little bullets had a long and illustrious history dating back to the birth of modern physics and Isaac Newton. But Scottish physicist James Clerk Maxwell appeared to have comprehensively banished any lingering doubts in 1864 in a series of papers that Albert Einstein later described as the most profound and the most fruitful that physics has experienced since the time of Newton. Maxwell showed that light is an electromagnetic wave, surging through space. So the idea of light as a wave had an immaculate and, it seemed, unimpeachable pedigree. Yet in a series of experiments from 1923 to 1925, conducted at Washington University in St. Louis, Arthur Compton and his co-workers succeeded in bouncing the quanta of light off electrons. Both behaved rather like billiard balls, providing clear evidence that Planck's theoretical conjecture had a firm grounding in the real world. In 1926, the light quanta were christened photons. The evidence was incontrovertible. Light behaves both as a wave and as a particle. That signaled the end for classical physics, and the end of the beginning for quantum theory. Ernest Rutherford cited 1896 as the beginning of the quantum revolution, because this was the year Henri Becquerel, working in his laboratory in Paris, discovered radioactivity. Becquerel was attempting to use uranium compounds to generate X-rays, discovered just a few months previously by Wilhelm Röntgen in Würzburg. Instead, he found that uranium compounds emit les rayons uraniques, which were able to darken photographic plates even when they were wrapped in thick paper that no light could penetrate. The importance of Becquerel's rays was recognized in a review article by the great scientist Henri Poincaré as early as 1897, in which he wrote presciently of the discovery, "One can think today that it will open for us an access to a new world which no one suspected." The puzzling thing about radioactive decay, which proved to be a hint of things to come, was that nothing seemed to trigger the emission of the rays. They just popped out of substances spontaneously and unpredictably. In 1900, Rutherford noted the problem. All atoms formed at the same time should last for a definite interval. This, however, is contrary to the observed law of transformation, in which the atoms have a life embracing all values from 0 to infinity. This randomness in the behavior of the microworld came as a shock because, until this point, science was resolutely deterministic. If at some instant in time you knew everything it is possible to know about something, then it was believed you could predict with absolute certainty what would happen to it in the future. The breakdown of this kind of predictability is a key feature of quantum theory. It deals with probabilities rather than certainties, not because we lack absolute knowledge, but because some aspects of nature are, at their very heart, governed by the laws of chance. And so we now understand that it is simply impossible to predict when a particular atom will decay. Radioactive decay was science's first encounter with nature's dice, and it confused many physicists for a long time. Clearly there was something interesting going on inside atoms, although their internal structure was entirely unknown. The key discovery was made by Rutherford in 1911, using a radioactive source to bombard a very thin sheet of gold with a type of radiation known as alpha particles. We now know them to be the nuclei of helium atoms. Rutherford, with his co-workers Hans Geiger and Ernest Marsden, discovered to their immense surprise that around 1 in 8,000 alpha particles did not fly through the gold as expected, but bounced straight back. Rutherford later described the moment in characteristically colourful language. "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." By all accounts, Rutherford was an engaging and no-nonsense individual. He once described a self-important official as being like a Euclidean point. He has position without magnitude. Rutherford calculated that his experimental results could be explained only if the atom consists of a very small nucleus at the center, with electrons orbiting around it. At the time, he probably had in mind a situation similar to the planets orbiting around the Sun. The nucleus contains almost all the mass of the atom, which is why it's capable of stopping his 15-inch shell alpha particles and bouncing them back. Hydrogen, the simplest element, has a nucleus consisting of a single proton with a radius of around 1.75 times 10 to the minus 15 meters. If you are unfamiliar with this notation, this means 0.000000000000000000175 meters, or in words, just under 2,000 million millionths of a meter. As far as we can tell today, the single electron is like Rutherford's self-important official, point-like, and it orbits around the hydrogen nucleus at a radius around 100,000 times larger than the nuclear diameter. The nucleus has a positive electric charge, and the electron has a negative electric charge, which means that there is an attractive force between them, analogous to the force of gravity that holds the Earth in orbit around the Sun. This, in turn, means that atoms are largely empty space. If you imagine a nucleus scaled up to the size of a tennis ball, then the tiny electron would be smaller than a mote of dust, orbiting at a distance of 1 kilometer. These figures are quite surprising because solid matter certainly does not feel very empty. Rutherford's nuclear atom raised a host of problems for the physicists of the day. It was well known, for instance, that the electron should lose energy as it moves in orbit around the atomic nucleus, because all electrically charged things radiate energy away if they move in curved paths. This is the idea behind the operation of the radio transmitter, inside which electrons are made to jiggle, and as a result, electromagnetic radio waves issue forth. Heinrich Hertz invented the radio transmitter in 1887, and by the time Rutherford discovered the atomic nucleus, there was a commercial radio station sending messages across the Atlantic from Ireland to Canada. So there was clearly nothing wrong with the theory of orbiting charges and the emission of radio waves, and that meant confusion for those trying to explain how electrons can stay in orbit around nuclei. A similarly inexplicable phenomenon was the mystery of the light emitted by atoms when they are heated. As far back as 1853, the Swedish scientist Anders Jonas Ångström discharged a spark through a tube of hydrogen gas and analyzed the emitted light. One might assume that a glowing gas would produce all the colors of the rainbow. After all, what is the sun but a glowing ball of gas? Instead, Ångström observed that hydrogen emits light of 3 very distinct colors: red, blue-green, and violet, like a rainbow with 3 pure, narrow arcs. It was soon discovered that each of the chemical elements behaves in this way, emitting a unique barcode of colors. By the time Rutherford's nuclear atom came along, a scientist named Heinrich Gustav Johannes Kaiser had compiled a 6-volume, 5,000-page reference work entitled Handbuch der Spektroskopie, documenting all the shining colored lines from the known elements. The question, of course, was why? Not only why Professor Kaiser, he must have been great fun at dinner parties, but also why the profusion of colored lines? For over 60 years, the science of spectroscopy, as it was known, had been simultaneously an observational triumph and a theoretical wasteland. In March 1912, fascinated by the problem of atomic structure, Danish physicist Niels Bohr traveled to Manchester to meet with Rutherford. He later remarked that trying to decode the inner workings of the atom from the spectroscopic data had been akin to deriving the foundations of biology from the colored wing of a butterfly. Rutherford's solar system atom provided the clue Bohr needed, and by 1913 he had published the first quantum theory of atomic structure. The theory certainly had its problems, but it did contain several key insights that triggered the development of modern quantum theory. Bohr concluded that electrons can only take up certain orbits around the nucleus, with the lowest energy orbit lying closest in. He also said that electrons are able to jump between these orbits. They jump out to a higher orbit when they receive energy, from a spark in a tube, for example, and in time they will fall back down, emitting light in the process. The color of the light is determined directly by the energy difference between the 2 orbits. Figure 2.1 in the reference PDF illustrates the basic idea. The arrow represents an electron as it jumps from the 3rd energy level down to the 2nd energy level, emitting light represented by the wavy line as it does so. In Bohr's model, The electron is only allowed to orbit the proton in one of these special quantized orbits. Spiraling inwards is simply forbidden. In this way, Bohr's model allowed him to compute the wavelengths, i.e. colors, of light observed by Ångström. They were to be attributed to an electron hopping from the 5th orbit down to the 2nd orbit, the violet light, from the 4th orbit down to the 2nd, the blue-green light, or from the 3rd orbit down to the 2nd, the red light. Bohr's model also correctly predicted that there should be light emitted as a result of electrons hopping down to the 1st orbit. This light is in the ultraviolet part of the spectrum, which is not visible to the human eye, and so it was not seen by Ångström. It had, however, been spotted in 1906 by Harvard physicist Theodore Lyman, and Bohr's model described Lyman's data beautifully. Although Bohr did not manage to extend his model beyond hydrogen, the ideas he introduced could be applied to other atoms. In particular, if one supposes that the atoms of each element have a unique set of orbits, then they will only ever emit light of certain colors. The colors emitted by an atom therefore act like a fingerprint, and astronomers were certainly not slow to exploit the uniqueness of the spectral lines emitted by atoms as a way to determine the chemical composition of the stars. Bohr's model was a good start, but it was clearly unsatisfactory. Just why were electrons forbidden from spiraling inwards, when it was known that they should lose energy by emitting electromagnetic waves, an idea so firmly rooted in reality with the advent of radio? And why are the electron orbits quantized in the first place? And what about the heavier elements beyond hydrogen? How was one to go about understanding their structure? Half-baked though Bohr's theory may have been, it was a crucial step, and an example of how scientists often make progress. There is no point at all in getting completely stuck in the face of perplexing and often quite baffling evidence. In such cases, scientists often make an Ansatz, an educated guess, if you like, and then proceed to compute the consequences of the guess. If the guess works, in the sense that the subsequent theory agrees with experiment, then you can go back with some confidence to try to understand your initial guess in more detail. Bohr's Ansatz remained successful but unexplained for 13 years. We will revisit the history of these early quantum ideas as the book unfolds, but for now we leave a mass of strange results and half-answered questions, because this is what the early founders of quantum theory were faced with. In summary, following Planck, Einstein introduced the idea that light is made up of particles, but Maxwell had shown that light also behaves like waves. Rutherford and Bohr led the way in understanding the structure of atoms, but the way that electrons behave inside atoms was not in accord with any known theory. And the diverse phenomena collectively known as radioactivity, in which atoms spontaneously split apart for no discernible reason, remained a mystery, not least because it introduced a disturbingly random element into physics. There was no doubt about it. Something strange was afoot in the subatomic world. The first step towards a consistent, unified answer is widely credited to the German physicist Werner Heisenberg, and what he did represented nothing less than a completely new approach to the theory of matter and forces. In July of 1925, Heisenberg published a paper throwing out the old hodgepodge of ideas and half-theories, including Bohr's model of the atom, and ushered in an entirely new approach to physics. He began, "In this paper, it will be attempted to secure the foundations for a quantum theoretical mechanics, which is exclusively based on relations between quantities which in principle are observable." This is an important step because Heisenberg is saying that the underlying mathematics of quantum theory need not correspond to anything with which we are familiar. The job of quantum theory should be to predict directly observable things, such as the color of the light emitted from hydrogen atoms. It should not be expected to provide some kind of satisfying mental picture for the internal workings of the atom, because this is not necessary, and it may not even be possible. In one fell swoop, Heisenberg removed the conceit that the workings of nature should necessarily accord with common sense. This is not to say that a theory of the subatomic world shouldn't be expected to accord with our everyday experience when it comes to describing the motion of large objects like tennis balls and aircraft. But we should be prepared to abandon the prejudice that small things behave like smaller versions of big things, if this is what our experimental observations dictate. There is no doubt that quantum theory is tricky, and absolutely no doubt that Heisenberg's approach is extremely tricky indeed. Nobel laureate Steven Weinberg, one of the greatest living physicists, wrote of Heisenberg's 1925 paper, "If the reader is mystified at what Heisenberg was doing, he or she is not alone." I've tried several times to read the paper that Heisenberg wrote on returning from Heligoland, and although I think I understand quantum mechanics, I have never understood Heisenberg's motivations for the mathematical steps in his paper. Theoretical physicists in their most successful work tend to play one of two roles. They are either sages or magicians. It is usually not difficult to understand the papers of sage physicists, but the papers of magician physicists are often incomprehensible. In that sense, Heisenberg's 1925 paper was pure magic. Heisenberg's philosophy, though, is not pure magic. It is simple, and it lies at the heart of our approach in this book. The job of a theory of nature is to make predictions for quantities that can be compared to experimental results. We are not mandated to produce a theory that bears any relation to the way we perceive the world at large. Fortunately, although we are adopting Heisenberg's philosophy, we shall be following Richard Feynman's more transparent approach to the quantum world. We've used the word theory liberally in the last few pages, and before we continue to build quantum theory, it will be useful to take a look at a simpler theory in more detail. A good scientific theory specifies a set of rules that determine what can and cannot happen to some portion of the world. They must allow predictions to be made that can be tested by observation. If the predictions are shown to be false, the theory is wrong and must be replaced. If the predictions are in accord with observation, the theory survives. No theory is true in the sense that it must always be possible to falsify it. As the biologist Thomas Huxley wrote, "Science is organized common sense, where many a beautiful theory was killed by an ugly fact." Any theory that is not amenable to falsification is not a scientific theory. Indeed, one might go as far as to say that it has no reliable information content at all. The reliance on falsification is why scientific theories are different from matters of opinion. This scientific meaning of the word theory, by the way, is different from its ordinary usage, where it often suggests a degree of speculation. Scientific theories may be speculative if they have not yet been confronted with the evidence, but an established theory is something that is supported by a large body of evidence. Scientists strive to develop theories that encompass as wide a range of phenomena as possible. And physicists in particular tend to get very excited about the prospect of describing everything that can happen in the material world in terms of a small number of rules. One example of a good theory that has a wide range of applicability is Isaac Newton's theory of gravity, published on the 5th of July 1687 in his Philosophiae Naturalis Principia Mathematica. It was the first modern scientific theory, and although it's subsequently been shown to be inaccurate in some circumstances, it was so good that it is still used today. Einstein developed a more precise theory of gravity, general relativity, in 1915. Newton's description of gravity can be captured in a single mathematical equation: F equals g m1 m2 all over r squared. This may look simple or complicated depending on your mathematical background. We do occasionally make use of mathematics as this book unfolds. For those readers who find the maths difficult, our advice is to skip over the equations without worrying too much. We will always try to emphasize the key ideas in a way that does not rely on the maths. The maths is included mainly because it allows us to really explain why things are the way they are. Without it, we should have to resort to the physicist guru mentality, whereby we pluck profundities out of thin air, and neither author will be comfortable with guru status. Now let us return to Newton's equation. Imagine there is an apple hanging precariously from a branch. The consideration of the force of gravity triggered by a particularly ripe apple bouncing off his head one summer's afternoon was, according to folklore, Newton's root to his theory. Newton said that the apple is subject to the force of gravity, which pulls it towards the ground, and that force is represented in the equation by the symbol F. So first of all, the equation allows you to calculate the force on the apple if you know what the symbols on the right-hand side of the equal sign mean. The symbol R stands for the distance between the center of the apple and the center of the Earth. It's R squared because Newton discovered that the force depends on the square of the distance between the objects. In non-mathematical language, this means that if you double the distance between the apple and the center of the Earth, the gravitational force drops by a factor of 4. If you triple the distance, it drops by a factor of 9, and so on. Physicists call this behavior an inverse square law. The symbols M1 and M2 stand for the mass of the apple and the mass of the Earth, and their appearance encodes Newton's recognition that the gravitational force of attraction between two objects depends on the product of their masses. That then begs the question, what is mass? This is an interesting question in itself, and for the deepest answer available today, we'll need to wait until we talk about a quantum particle known as the Higgs boson. Roughly speaking, mass is a measure of the amount of stuff in something. The Earth is more massive than the apple. This kind of statement isn't really good enough, though. Fortunately, Newton also provided a way of measuring the mass of an object independently of his law of gravitation, and it's encapsulated by the second of his 3 laws of motion, the ones so beloved of every high school student of physics. 1. Every object remains in a state of rest or uniform motion in a straight line unless it is acted upon by a force. 2. An object of mass m undergoes an acceleration a when acted upon by a force F. In the form of an equation, this reads F equals ma. 3. To every action, there is an equal and opposite reaction. Newton's 3 laws provide a framework for describing the motion of things under the influence of a force. The first law describes what happens to an object when no forces act. The object either just sits still or moves in a straight line at constant speed. We shall be looking for an equivalent statement for quantum particles later on. And it's not giving the game away too much to say that quantum particles do not just sit still. They leap around all over the place, even when no forces are present. In fact, the very notion of force is absent in the quantum theory, and so Newton's second law is bound for the waste paper basket too. We do mean that, by the way. Newton's laws are heading for the bin because they have been exposed as only approximately correct. They work well in many instances, but fail totally when it comes to describing quantum phenomena. The laws of quantum theory replace Newton's laws and furnish a more accurate description of the world. Newton's physics emerges out of the quantum description, and it's important to realize that the situation is not Newton for big things and quantum for small. It is quantum all the way. Although we aren't really going to be very interested in Newton's third law here, it does deserve a comment or two for the enthusiast. The third law says that forces come in pairs. If I stand up, then my feet press into the Earth, and the Earth responds by pushing back. This implies that for a closed system, the net force acting on it is 0, and this in turn means that the total momentum of the system is conserved. We shall use the concept of momentum throughout this book, and for a single particle, it is defined to be the product of the particle's mass and its speed, which we write P equals mv. Interestingly, momentum conservation does have some meaning in quantum theory, even though the idea of force does not. For now, though, it is Newton's second law that interests us. F equals ma says that if you apply a known force to something and measure its acceleration, then the ratio of the force to the acceleration is its mass. This in turn assumes we know how to define force, but that's not so hard. A simple but not very accurate or practical way would be to measure force in terms of the pull exerted by some standard thing. An average tortoise, let us say, walking in a straight line with a harness attaching it to the object being pulled. We could term the average tortoise the SI tortoise and keep it in a sealed box in the International Bureau of Weights and Measures in Sèvres, France. 2 harnessed tortoises would exert twice the force, 3 would exert 3 times the force, and so on. We could then always talk about any push or pull in terms of the number of average tortoises required to generate it. Given this system, which is ridiculous enough to be agreed on by any international committee of standards, but not so ridiculous when you consider that an oft-used unit of power even to this day is the horsepower. We can simply pull an object with a tortoise and measure its acceleration, and this will allow us to deduce its mass using Newton's second law. We can then repeat the process for a second object to deduce its mass, and then we can put both masses into the law of gravity to determine the force between the masses due to gravity. To put a tortoise equivalent number on the gravitational force between 2 masses, though, we would still need to calibrate the whole system to the strength of gravity itself. And this is where the symbol G comes in. G is a very important number called Newton's gravitational constant, which encodes the strength of the gravitational force. If we doubled G, we would double the force, and this would make the apple accelerate at double the rate towards the ground. It therefore describes one of the fundamental properties of our universe, and we would live in a very different universe if it took on a different value. It's currently thought that G takes the same value everywhere in the universe, and that it has remained constant throughout all of time. It appears in Einstein's theory of gravity too, where it is also a constant. There are other universal constants of nature that we'll meet in this book. In quantum mechanics, the most important is Planck's constant, named after quantum pioneer Max Planck and given the symbol h. We shall also need the speed of light, c, which is not only the speed that light travels in a vacuum, but the universal speed limit. It is impossible to travel faster than the speed of light, and certainly not desirable, Woody Allen once said, as one's hat keeps blowing off. Newton's 3 laws of motion and the law of gravitation are all that is needed to understand motion in the presence of gravity. There are no other hidden rules that we did not state. Just these few laws do the trick, and allow us, for example, to understand the orbits of the planets in our solar system. Together, they severely restrict the sort of paths that objects are allowed to take when moving under the influence of gravity. It can be proved using only Newton's laws that all of the planets, comets, asteroids, and meteors in our solar system are only allowed to move along paths known as conic sections. The simplest of these, and the one that the Earth follows to a very good approximation in its orbit around the Sun, is a circle. More generally, planets and moons move along orbital paths known as ellipses, which are like stretched circles. The other 2 conic sections are known as the parabola and the hyperbola. A parabola is the path that a cannonball takes when fired from the cannon. The final conic section, the hyperbola, is the path that the most distant object ever constructed by humankind is now following outwards to the stars. Voyager 1 is, at the time of writing, around 17,610,000,000 kilometers from the Earth, and traveling away from the solar system at a speed of 538 million kilometers per year. This most beautiful of engineering achievements was launched in 1977 and is still in contact with the Earth, recording measurements of the solar wind on a tape recorder and transmitting them back with a power of 20 watts. Voyager 1 and her sister ship Voyager 2 are inspiring testaments to the human desire to explore our universe. Both spacecraft visited Jupiter and Saturn, and Voyager 2 went on to visit Uranus and Neptune. They navigated the solar system with precision, using gravity to slingshot them beyond the planets and into interstellar space. Navigators here on Earth used nothing more than Newton's laws to plot their courses between the inner and outer planets, and outwards to the stars. Voyager 2 will sail close to Sirius, the brightest star in the skies, in just under 300,000 years. We did all this, and we know all this, because of Newton's theory of gravity and his laws of motion. Newton's laws provide us with a very intuitive picture of the world. As we have seen, they take the form of equations, mathematical relationships between measurable quantities, that allow us to predict with precision how objects move around. Inherent in the whole framework is the assumption that objects are, at any instant, located somewhere, and that as time passes, objects move smoothly around from place to place. This seems so self-evidently true that it's hardly worth commenting upon. But we need to recognize that this is a prejudice. Can we really be sure that things are definitely here or there, and that they are not actually in two different places at the same time? Of course, your garden shed is not in any noticeable sense sitting in two distinctly different places at once. But how about an electron in an atom? Could that be both here and there? Right now, that kind of suggestion sounds crazy, mainly because we can't picture it in our mind's eye. But it will turn out to be the way things actually work. At this stage in our narrative, all we are doing in making this strange-sounding statement is pointing out that Newton's laws are built on intuition, and that is like a house built on sand as far as fundamental physics is concerned. There's a very simple experiment first conducted by Clinton Davison and Lester Germer at Bell Laboratories in the United States and published in 1927, which shows that Newton's intuitive picture of the world is wrong. Although apples, planets, and people certainly appear to behave in a Newtonian way, gliding from place to place in a regular and predictable fashion as time unfolds, their experiment showed that the fundamental building blocks of matter do not behave at all like this. Davison and Germer's paper begins, "The intensity of scattering of a homogeneous beam of electrons of adjustable speed incident upon a single crystal of nickel has been measured as a function of direction." Fortunately, there's a way to appreciate the key content of their findings using a simplified version of their experiment, known as the double-slit experiment. The experiment consists of a source that sends electrons towards a barrier with two small slits, or holes, cut into it. On the other side of the barrier, there is a screen that glows when an electron hits it. It doesn't matter what the source of electrons is, but practically speaking, one can imagine a length of hot wire stretched out along the side of the experiment. Once upon a time, televisions operated using this idea. A stream of electrons generated by a hot wire was gathered, focused into a beam, and deflected by a magnetic field onto a screen that glowed when the electrons hit it. We've sketched the double-slit experiment in figure 2.2 on the reference PDF. Imagine pointing a camera at the screen and leaving the shutter open to take a long exposure photograph of the little flashes of light emitted as one by one the electrons hit it. A pattern will build up. And the simple question is, what is the pattern? Assuming electrons are simply little particles that behave rather like apples or planets, we might expect the emergent pattern to look something like that shown in figure 2.2. Some electrons go through the slits, most don't. The ones that make it through might bounce off the edge of the slits a bit, which will spread them out, but the most hits, and therefore the brightest bits of the photograph, will surely appear directly aligned with the two slits. This isn't what happens. Instead, the picture looks like figure 2.3, several parallel vertical lines. A pattern like this is what Davison and Germer published in their 1927 paper. Davison subsequently received the 1937 Nobel Prize for the experimental discovery of electron diffraction by crystals. He shared the prize not with Germer, but with George Paget Thomson, who saw the same pattern independently in experiments at the University of Aberdeen. The alternating stripes of light and dark are known as an interference pattern, and interference is more usually associated with waves. To understand why, let's imagine doing the double-slit experiment with water waves instead of electrons. Imagine a water tank with a wall midway down with two slits cut into it. The screen and camera could be replaced with a wave height detector, and the hot wire with something that makes waves, a plank of wood along the side of the tank attached to a motor that keeps it dipping in and out of the water would do. The waves from the plank will travel across the surface of the water until they reach the wall. When a wave hits the wall, most of it will bounce back, but two small pieces will pass through the slits. These two new waves will spread outwards from the slits towards the wave height detector. Notice that we use the term spread out here, because the waves don't just carry on in a straight line from the slits. Instead, the slits act as two sources of new waves, each issuing forth in ever-increasing semicircles. Figure 2.4 on the reference PDF illustrates what happens. The figure provides a striking visual demonstration of the behavior of waves in water. There are regions where there are no waves at all, which seem to radiate out from the slits like the spokes of a wheel, whilst other regions are still filled with the peaks and troughs of the waves. The parallels with the pattern seen by Davison, Germer and Thomson are striking. For the case of electrons hitting the screen, the regions where few electrons are detected correspond to the places in the tank where the water surface remains flat. The spokes you can see radiating outwards in the figure. In a tank of water, it is quite easy to understand how these spokes emerge. It is in the mixing and merging of the waves as they spread out from the slits. Because waves have peaks and troughs, when two waves meet, they can either add or subtract. If two waves meet such that the peak of one is aligned with the trough of the other, they will cancel out and there will be no wave at that point. At a different place, the waves might arrive with their peaks in perfect alignment, and here they will add to produce a bigger wave. At each point in the water tank, the distance between it and the two slits will be a little different, which means that at some places the two waves will arrive with peaks together, at others with peaks and troughs aligned, and in most places with some combination of these two extremes. The result will be an alternating pattern, an interference pattern. In contrast to water waves, the experimentally observed fact that electrons also produce an interference pattern is very difficult to understand. According to Newton and common sense, the electrons emerge from the source, travel in straight lines towards the slits, because there are no forces acting on them, remember Newton's first law, pass through with perhaps a slight deflection if they glance off the edge of the slit, and continue in a straight line until they hit the screen. But this would not result in an interference pattern. It would give the pair of stripes as shown in figure 2.2. Now we could suppose that there is some clever mechanism whereby the electrons exert a force on each other so as to deflect themselves from straight lines as they stream through the slits. But this can be ruled out because we can set the experiment up such that we send just one electron at a time from source to screen. You would have to wait, but slowly and surely as the electrons hit the screen one after the other, the stripy pattern would build up. This is very surprising, because the stripy pattern is absolutely characteristic of waves interfering with each other, yet it emerges one electron at a time, dot by dot. It's a good mental exercise to try to imagine how it could be that particle by particle, an interference pattern builds up as we fire tiny bullet-like particles at a pair of slits in a screen. It's a good exercise because it's futile, and a few hours of brain-racking should convince you that a stripy pattern is inconceivable. Whatever those particles are that hit the screen, they are not behaving like regular particles. It is as if the electrons are in some sense interfering with themselves. The challenge for us is to come up with a theory that can explain what that means. There's an interesting historical coda to this story, which provides a glimpse into the intellectual challenge raised by the double-slit experiment. George Paget Thomson was the son of J.J. Thomson, who himself received a Nobel Prize for his discovery of the electron in 1899. J.J. Thomson showed that the electron is a particle with a particular electric charge and a particular mass, a tiny, point-like grain of matter. His son received the Nobel Prize 40 years later for showing that the electron doesn't behave as his father might have expected. Thomson Sr. was not wrong. The electron does have a well-defined mass and electric charge, and every time we see one, it appears as a little point of matter. It just doesn't seem to behave exactly like a regular particle, as Davison, Germer, and Thomson Jr. discovered. Importantly, though, it doesn't behave exactly like a wave either, because the pattern is not built up as a result of some smooth deposition of energy. Rather, it is built out of many tiny dots. We always detect Thomson Senior's single point-like electrons. Perhaps you can already see the need to engage with Heisenberg's way of thinking. The things we observe are particles, so we had better construct a theory of particles. Our theory must also be able to predict the appearance of the interference pattern that builds up as the electrons, one after another, pass through the slits and hit the screen. The details of how the electrons travel from source to slits to screen are not something we observe, and therefore need not to be in accord with anything we experience in daily life. Indeed, the electron's journey need not even be something we can talk about at all. All we have to do is find a theory capable of predicting that the electrons hit the screen in the pattern observed in the double slit experiment. This is what we will do in the next chapter. Lest we lapse into thinking that this is merely a fascinating piece of microphysics that has little relevance to the world at large, we should say that the quantum theory of particles we developed to explain the double slit experiment will also turn out to be capable of explaining the stability of atoms, the colored light emitted from the chemical elements, radioactive decay, and indeed all of the great puzzles that perplexed scientists at the turn of the 20th century. The fact that our framework describes the way electrons behave when locked away inside matter will also allow us to understand the workings of quite possibly the most important invention of the 20th century, the transistor. In the very final chapter of this book, we will meet a striking application of quantum theory that is one of the great demonstrations of the power of scientific reasoning. The more outlandish predictions of quantum theory usually manifest themselves in the behavior of small things. But because large things are made of small things, there are certain circumstances in which quantum physics is required to explain the observed properties of some of the most massive objects in the universe, the stars. Our sun is fighting a constant battle with gravity. This ball of gas, 1/3 times more massive than our planet, has a gravitational force at its surface that is almost 28 times that at the Earth, which provides a powerful incentive for it to collapse in on itself. The collapse is prevented by the outward pressure generated by nuclear fusion reactions deep within the solar core, as 600 million tons of hydrogen are converted into helium every second. Vast though our star is, burning fuel at such a ferocious rate must ultimately have consequences, and one day the sun's fuel source will run out. The outward pressure will then cease, and the force of gravity will reassert its grip unopposed. It would seem that nothing in nature could stop a catastrophic collapse. In reality, quantum physics steps in and saves the day. Stars that have been rescued by quantum effects in this way are known as white dwarfs, and such will be the final fate of our sun. At the end of this book, we will employ our understanding of quantum mechanics to determine the maximum mass of a white dwarf star. This was first calculated in 1930 by the Indian astrophysicist Subrahmanyan Chandrasekhar, and it turns out to be approximately 1.4 times the mass of our Sun. Quite wonderfully, that number can be computed using only the mass of a proton and the values of the three constants of nature we have already met: Newton's gravitational constant, the speed of light, and Planck's constant. The development of the quantum theory itself and the measurement of these four numbers could conceivably have been achieved without ever looking at the stars. It's possible to imagine a particularly agoraphobic civilization confined to deep caves below the surface of their home planet. They would have no concept of a sky, but they could have developed quantum theory. Just for fun, they may even decide to calculate the maximum mass of a giant sphere of gas. Imagine that one day, an intrepid explorer chooses to venture above ground for the first time and gaze in awe at the spectacle above. A sky full of lights, a galaxy of 100 billion suns arcing from horizon to horizon. The explorer would find, just as we have found from our vantage point here on Earth, that out there amongst the many fading remnants of dying stars, there is not a single one with a mass exceeding the Chandrasekhar limit. 3. What is a particle? Our approach to quantum theory was pioneered by Richard Feynman, the Nobel Prize-winning bongo-playing New Yorker, described by his friend and collaborator Freeman Dyson as half genius, half buffoon. Dyson later changed his opinion. Feynman could be more accurately described as all genius, all buffoon. We will follow his approach in our book because it is fun, and probably the simplest route to understanding our quantum universe. As well as being responsible for the simplest formulation of quantum mechanics, Richard Feynman was also a great teacher, able to transfer his deep understanding of physics to the page or lecture theatre, with unmatched clarity and a minimum of fuss. His style was contemptuous of those who might seek to make physics more complicated than it need be. Even so, at the beginning of his classic undergraduate textbook series, The Feynman Lectures on Physics, he felt the need to be perfectly honest about the counterintuitive nature of the quantum theory. Subatomic particles, Feynman wrote, do not behave like waves, they do not behave like particles, they do not behave like clouds or billiard balls or weights on springs, or like anything that you have ever seen. Let's get on with building a model for exactly how they do behave. As our starting point, we will assume that the elemental building blocks of nature are particles. This has been confirmed not only by the double-slit experiment, where the electrons always arrive at specific places on the screen, but by a whole host of other experiments. Indeed, particle physics is not called that for nothing. The question we need to address is, how do particles move around? Of course, the simplest assumption would be that they move in nice straight lines, or curved lines when acted upon by forces, as dictated by Newton. This cannot be correct, though, because any explanation of the double-slit experiment requires that the electrons interfere with themselves when they pass through the slits. And to do that, they must in some sense be spread out. This, therefore, is the challenge. Build a theory of point-like particles such that those same particles are also spread out. This is not as impossible as it sounds. We can do it if we let any single particle be in many places at once. Of course, that may still sound impossible, but the proposition that a particle should be in many places at once is actually a rather clear statement, even if it sounds silly. From now on, we'll refer to these counterintuitive, spread-out yet point-like particles as quantum particles. With this, a particle can be in more than one place at once proposal, we are moving away from our everyday experience and into uncharted territory. One of the major obstacles to developing an understanding of quantum physics is the confusion this kind of thinking can engender. To avoid confusion, we should follow Heisenberg and learn to feel comfortable with views of the world that run counter to tangible experience. Feeling uncomfortable can be mistaken for confusion, and very often students of quantum physics continue to attempt to understand what is happening in everyday terms. It is the resistance to new ideas that actually leads to confusion, not the inherent difficulty of the ideas themselves, because the real world simply doesn't behave in an everyday way. We must therefore keep an open mind and not be distressed by all the weirdness. Shakespeare had it right when Hamlet says, "And therefore as a stranger give it welcome. There are more things in heaven and earth, Horatio, than are dreamt of in your philosophy." A good way to begin is to think carefully about the double-slit experiment for water waves. Our aim will be to work out just what it is about waves that causes the interference pattern. We should then make sure that our theory of quantum particles is capable of encapsulating this behavior, so that we can have a chance of explaining the double-slit experiment for electrons. There are two reasons why waves journeying through two slits can interfere with themselves. The first is that the wave travels through both of the slits at once, creating two new waves that head off and mix together. It's obvious that a wave can do this. We have no problem visualizing one long ocean wave rolling to the shore and crashing onto a beach. It is a wall of water, an extended, traveling thing. We are therefore going to need to decide how to make our quantum particle an extended, traveling thing. The second reason is that the two new waves heading out from the slits are able either to add to or to subtract from each other when they mix. This ability for two waves to interfere is clearly crucial in explaining the interference pattern. The extreme case is when the peak of one wave coincides with the trough of another, in which case they completely cancel each other out. So we are also going to need to allow our quantum particle to interfere somehow with itself. The double-slit experiment connects the behavior of electrons and the behavior of waves. So let us see how far we can push the connection. Take a look at figure 3.1 in the reference PDF. And for the time being, ignore the lines joining A to E and B to F, and concentrate on the waves. The figure could then describe a water tank, with the wavy lines representing from left to right how a water wave rolls its way across the tank. Imagine taking a photograph of the tank just after a plank of wood has splashed in on the left-hand side to make a wave. The snapshot would reveal the newly formed wave that extends from top to bottom in the picture. All the water in the rest of the tank would be calm. A second snapshot taken a little later reveals that the water wave has moved towards the slits, leaving flat water behind it. Later still, the water wave passes through the pair of slits and generates the stripy interference pattern illustrated by the wavy lines on the far right. Now let us reread that last paragraph, but replace water wave with electron wave, whatever that may mean. An electron wave, suitably interpreted, has the potential to explain the stripy pattern we want to understand as it rolls through the experiment like a water wave. But we do need to explain why the electron pattern is made up of tiny dots as the electrons hit the screen one by one. At first sight, that seems in conflict with the idea of a smooth wave. But it is not. The clever bit is to realize that we can offer an explanation if we interpret the electron wave not as a real material disturbance, as is the case with a water wave, but rather as something that simply informs us where the electron is likely to be found. Notice we said the electron, because the wave is to describe the behavior of a single electron. That way we have a chance of explaining how these dots emerge. This is an electron wave and not a wave of electrons. We must never fall into the trap of thinking otherwise. If we imagine a snapshot of the wave at some instant in time, then we want to interpret it such that where the wave is largest, the electron is most likely to be found, and where the wave is smallest, the electron is least likely to be found. When the wave finally reaches the screen, a little spot appears and informs us of the location of the electron. The sole job of the electron wave is to allow us to compute the odds that the electron hits the screen at some particular place. If we do not worry about what the electron wave actually is, then everything is straightforward, because once we know the wave, then we can say where the electron is likely to be. The fun comes next, when we try to understand what this proposal for an electron wave implies for the electron's journey from slit to screen. Before we do this, it might be worth listening to the last paragraph again, because it is very important. It's not supposed to be obvious, and it is certainly not intuitive. The electron wave proposal has all the necessary properties to explain the appearance of the experimentally observed interference pattern, but it is something of a guess as to how things might work out. As good physicists, we should work out the consequences and see if they correspond to nature. Returning to figure 3.1 in the reference PDF, we have proposed that at each instant in time, the electron is described by a wave, just as in the case of water waves. At an early time, the electron wave is to the left of the slits. This means that the electron is in some sense located somewhere within the wave. At a later time, the wave will advance towards the slits just as the water wave did, and the electron will now be somewhere in the new wave. We are saying that the electron could be first at A and then at C, or it could be first at B and then at D, or it could be at A and then at D, and so on. Hold that thought for a minute, and think about an even later time after the wave has passed through the slits and reached the screen. The electron could now be found at E, or perhaps at F. The curves that we have drawn on the diagram represent two possible paths that the electron could have taken from the source through the slits and onto the screen. It could have gone from A to C to E, and it could have gone from B to D to F. These are just two out of an infinite number of possible paths that the electron could have taken. The crucial point is that it makes no sense to say that the electron could have ventured along each of these routes, but really it went along only one of them. To say that the electron really ventured along one particular path would be to give ourselves no more of a chance of explaining the interference pattern than if we had blocked up one of the slits in the water wave experiment. We need to allow the wave to go through both slits in order to get an interference pattern. And this means that we must allow all the possible paths for the electron to travel from source to screen. Put another way, when we said that the electron is somewhere within the wave, we really meant to say that it is simultaneously everywhere in the wave. This is how we must think. Because if we suppose the electron is actually located at some specific point, then the wave is no longer spread out, and we lose the water wave analogy. As a result, we cannot explain the interference pattern. Again, it might be worth re-listening to the last piece of reasoning, because it motivates much of what follows. There is no sleight of hand. What we are saying is that we need to describe a spread-out wave that is also a point-like electron. And one possible way to achieve this is to say that the electron sweeps from source to screen, following all possible paths at once. This suggests that we should interpret an electron wave as describing a single electron that travels from source to screen by an infinity of different routes. In other words, the correct answer to the question, how did that electron get to the screen, is it traveled by an infinity of possible routes, some of which went through the upper slit and some of which went through the lower one. Clearly, the it that is the electron is not an ordinary, everyday particle. This is what it means to be a quantum particle. Having decided to seek a description of an electron that mimics in many ways the behavior of waves, we need to develop a more precise way to talk about waves. We shall begin with a description of what is happening in a water tank when two waves meet, mix, and interfere with each other. To do this, we must find a convenient way of representing the positions of the peaks and troughs of each wave. In the technical jargon, these are known as phases. Colloquially, things are described as in phase if they reinforce one another in some way, or out of phase if they cancel each other out. The word is also used to describe the moon. Over the course of around 29.5 days, the moon passes from new to full and back again in a continuous waxing and waning cycle. The etymology of the word phase stems from the Greek phasis, which means the appearance and disappearance of an astronomical phenomenon. And the regular appearance and disappearance of the bright lunar surface seems to have led to its 20th century usage, particularly in science, as a description of something cyclical. And this is a clue as to how we might find a pictorial representation of the positions of the peaks and troughs of water waves. Have a look at figure 3.2 on the reference PDF. One way to represent a phase is as a clock face with a single hand rotating around. This gives us the freedom to represent visually a full 360 degrees worth of possibilities. The clock hand can point to 12 o'clock, 3 o'clock, 9 o'clock, and all points in between. In the case of the moon, you could imagine a new moon represented by a clock hand pointing to 12 o'clock, a waxing crescent at 1:30, the first quarter at 3, the waxing gibbous at 4:30, the full moon at 6, and so on. What we are doing here is using something abstract to describe something concrete, a clock face to describe the phases of the moon. In this way, we could draw a clock with its hand pointing to 12 o'clock, and you'd immediately know that the clock represented a new moon. And even though we haven't actually said it, you'd know that a clock with the hand pointing to 5 o'clock would mean that we are approaching a full moon. The use of abstract pictures or symbols to represent real things is absolutely fundamental in physics. This is essentially what physicists use mathematics for. The The power of the approach comes when the abstract pictures can be manipulated using simple rules to make firm predictions about the real world. As we'll see in a moment, the clock faces will allow us to do just this, because they're able to keep track of the relative positions of the peaks and troughs of waves. This in turn will allow us to calculate whether they will cancel or reinforce one another when they meet. Figure 3.3 shows a sketch of two water waves at an instant in time. Let's represent the peaks of the waves by clocks reading 12 o'clock and the troughs by clocks reading 6 o'clock. We can also represent places on the waves intermediate between peaks and troughs with clocks reading intermediate times, just as we did for the phases of the moon between new and full. The distance between the successive peaks and troughs of the wave is an important number. It is known as the wavelength of the wave. The two waves in figure 3.3 are out of phase with each other, which means that the peaks of the top wave are aligned with the troughs of the bottom wave, and vice versa. As a result, it is pretty clear that they will entirely cancel each other out when we add them together. This is illustrated at the bottom of the figure, where the wave is flatlining. In terms of clocks, all of the 12 o'clock clocks for the top wave, representing its peaks, are aligned with the 6 o'clock clocks for the bottom wave, representing its troughs. In fact, everywhere you look, the clocks for the top wave are pointing in the opposite direction to the clocks for the bottom wave. Using clocks to describe waves does, at this stage, seem like we are overcomplicating matters. Surely if we want to add together two water waves, then all we need to do is add the heights of each of the waves and we don't need clocks at all. This is certainly true for water waves. But we are not being perverse, and we have introduced the clocks for a very good reason. We will discover soon enough that the extra flexibility they allow is absolutely necessary when we come to use them to describe quantum particles. With this in mind, we shall now spend a little time inventing a precise rule for adding clocks. In the case of figure 3.3, the rule must result in all the clocks cancelling out, leaving nothing behind. 12 o'clock cancels 6 o'clock, 3 o'clock cancels 9 o'clock, and so on. This perfect cancellation is, of course, for the special case when the waves are perfectly out of phase. Let's search for a general rule that will work for the addition of waves of any alignment and shape. Figure 3.4 on the reference PDF shows two more waves, this time aligned in a different way, such that one is only slightly offset against the other. Again, we have labelled the peaks, troughs, and points in between with clocks. Now the 12 o'clock clock of the top wave is aligned with the 3 o'clock clock of the bottom wave. We are going to state a rule that allows us to add these two clocks together. The rule is that we take the two hands and stick them together head to tail. We then complete the triangle by drawing a new hand, joining the other two hands together. We have sketched this recipe in figure 3.5 in the reference PDF. The new hand will be a different length to the other two, and point in a different direction. It is a new clock face, which is the sum of the other two. We can be more precise now, and use simple trigonometry to calculate the effect of adding together any specific pair of clocks. In figure 3.5, we are adding together the 12 o'clock and 3 o'clock clocks. Let's suppose that the original clock hands are of length 1 centimeter, corresponding to water waves of peak height equal to 1 centimeter. When we place the hands head to tail, we have a right-angled triangle with two sides each of length 1 centimeter. The new clock hand will be the length of the third side of the triangle, the hypotenuse. Pythagoras' theorem tells us that the square of the hypotenuse is equal to the sum of the squares of the other two sides. H squared equals x squared plus y squared. Putting the numbers in, h squared equals 1 squared plus 1 squared, which equals 2. So the length of the new clock hand h is the square root of 2, which is approximately 1.414 centimeters. In what direction will the new hand point? For this we need to know the angle in our triangle, labelled theta in the figure. For the particular example of two hands of equal length, one pointing to 12 o'clock and one to 3 o'clock, you can probably work it out without knowing any trigonometry at all. The hypotenuse obviously points at an angle of 45 degrees, so the new time is halfway between 12 o'clock and 3 o'clock, which is 1:30. This example is a special case, of course. We chose the clocks so that the hands were at right angles and of the same length to make the mathematics easy. But it is obviously possible to work out the length of the hand and time resulting from the addition of any pair of clock faces. Now look again at figure 3.4 in the reference PDF. At every point along the new wave, we can compute the wave height by adding the clocks together using the recipe we just outlined, and asking how much of the new clock hand points in the 12 o'clock direction. When the clock points to 12 o'clock, this is obvious. The height of the wave is simply the length of the clock hand. Similarly, at 6 o'clock, it's obvious because the wave has a trough with a depth equal to the length of the hand. It's also pretty obvious when a clock reads 3 o'clock or 9 o'clock, because then the wave height is 0, since the clock hand is at right angles to the 12 o'clock direction. To compute the wave height described by any particular clock, we should multiply the length of the hand, h, by the cosine of the angle the hand makes with the 12 o'clock direction. For example, the angle that a 3 o'clock makes with a 12 o'clock is 90 degrees, and the cosine of 90 degrees is 0, which means the wave height is 0. Similarly, a time of 1:30 corresponds to an angle of 45 degrees with the 12 o'clock direction, and the cosine of 45 degrees is approximately 0.707. So the height of the wave is 0.707 times the length of the hand. Notice that 0.707 is 1/√2. If your trigonometry is not up to those last few sentences, then you can safely ignore the details. It's the principle that matters, which is that given the length of a clock hand and its direction, you can go ahead and calculate the wave height. And even if you don't understand trigonometry, you could make a good stab at it by carefully drawing the clock hands and projecting onto the 12 o'clock direction using a ruler. We would like to make it very clear to any students reading this book that we do not recommend this course of action. Sines and cosines are useful things to understand. That's the rule for adding clocks, and it works a treat, as illustrated in the bottom of the 3 pictures in figure 3.4, where we have repeatedly applied the rule for various points along the waves. In this description of water waves, all that ever matters is the projection of the time in the 12 o'clock direction, corresponding to just one number, the wave height. That is why the use of clocks is not really necessary when it comes to describing water waves. Take a look at the 3 clocks in figure 3.6. They all correspond to the same wave height, and so they provide equivalent ways of representing the same height of water. But clearly they are different clocks. And as we shall see, these differences do matter when we come to use them to describe quantum particles, because for them, the length of the clock hand, or equivalently the size of the clock, has a very important interpretation. At some points in this book, and at this point especially, things are abstract. To keep ourselves from succumbing to dizzying confusion, we should remember the bigger picture. The experimental results of Davison, Germer, and Thomson, and their similarity with the behavior of water waves, have inspired us to make an ansatz. We should represent a particle by a wave, and the wave itself can be represented by lots of clocks. We imagine that the electron wave propagates like a water wave, but we haven't explained how that works in any detail. But then we never said how the water wave propagates either. All that matters for the moment is that we recognize the analogy with water waves, and the notion that the electron is described at any instant by a wave that propagates and interferes like water waves do. In the next chapter we will do better than this, and be more precise about how an electron actually moves around as time unfolds. In doing that, we will be led to a host of treasures, including Heisenberg's famous uncertainty principle. Before we move on to that, we want to spend a little time talking about the clocks that we are proposing to represent the electron wave. We emphasize that these clocks are not real in any sense, and their hour hand has absolutely nothing to do with what time of day it is. This idea of using an array of little clocks to describe a real physical phenomenon is not so bizarre a concept as it may seem. Physicists use similar techniques to describe many things in nature, and we've already seen how they can be used to describe water waves. Another example of this type of abstraction is the description of the temperature in a room, which can be represented using an array of numbers. The numbers do not exist as physical objects any more than our clocks do. Instead, the set of numbers and their association with points is simply a convenient way of representing the temperature. Physicists call this mathematical structure a field. The temperature field is simply an array of numbers, one for every point. In the case of a quantum particle, the field is more complicated because it requires a clock face at each point rather than a single number. This field is usually called the wave function of the particle. The fact that we need an array of clocks for the wave function, whilst a single number would suffice for the temperature field or for water waves, is an important difference. In physics jargon, the clocks are there because the wave function is a complex field, whilst the temperature or water wave heights are both real fields. We shall not need any of this language because we can work with the clock faces. For those who are familiar with mathematics, just exchange the words as follows: clock for complex number, size of the clock for modulus of the complex number, and the direction of the hour hand for the phase. The rule for adding clocks is nothing more than the rule for adding complex numbers. We should not worry that we have no direct way to sense a wave function, in contrast to a temperature field. The fact that it is not something we can touch, smell, or see directly is irrelevant. Indeed, we would not get very far in physics if we decided to restrict our description of the universe to things we can directly sense. In our discussion of the double-slit experiment for electrons, we said that the electron wave is largest where the electron is most likely to be. This interpretation allowed us to appreciate how the stripy interference pattern can be built up dot by dot as the electrons arrive. But this is not a precise enough statement for our purposes now. We want to know what the probability is to find an electron at a particular point. We want to put a number on it. This is where the clocks become necessary, because the probability that we want is not simply the wave height. The correct thing to do is to interpret the square of the length of the clock hand as the probability to find the particle at the site of the clock. This is why we need the extra flexibility that the clocks give us over simple numbers. That interpretation is not meant to be at all obvious, and we cannot offer any good explanation for why it is correct. In the end, we know that it is correct because it leads to predictions that agree with experimental data. This interpretation of the wave function was one of the thorny issues facing the early pioneers of quantum theory. The wave function, that is our cluster of clocks, was introduced into quantum theory in a series of papers published in 1926 by the Austrian physicist Erwin Schrödinger. His paper of the 21st of June contains an equation that should be etched into the mind of every undergraduate physics student. It is known, naturally enough, as the Schrödinger equation. I, h bar, times the partial derivative of psi with respect to time equals capital H psi. The Greek symbol psi represents the wave function, and the Schrödinger equation describes how it changes as time passes. The details of the equation are irrelevant for our purposes because we're not going to follow the Schrödinger approach in this book. What's interesting, though, is that although Schrödinger wrote down the correct equation for the wave function, he initially got the interpretation wrong. It was Max Born, one of the oldest of the physicists working on the quantum theory in 1926, who at the grand old age of 43 gave the correct interpretation in a paper submitted just 4 days after Schrödinger's. We mention his age because quantum theory during the mid-1920s gained the nickname Knabenphysik, boy physics, because so many of the key protagonists were young. In 1925, Heisenberg was 23, Wolfgang Pauli, whose famous exclusion principle we shall meet later on, was 22, as was Paul Dirac, the British physicist, who first wrote down the correct equation describing the electron. It is often claimed that their youth freed them from the old ways of thinking and allowed them fully to embrace the radical new picture of the world represented by quantum theory. Schrödinger, at 38, was an old man in this company, and it is true that he was never completely at ease with the theory he played such a key role in developing. Born's radical interpretation of the wave function, for which he received the Nobel Prize for Physics in 1954, was that the square of the length of the clock hand at a particular point represents the probability of finding a particle there. For example, if the hour hand on the clock located at some place has a length of 0.1, then squaring this gives 0.01. This means that the probability to find the particle at this place is 0.01, i.e. 1 in 100. You might ask why Born didn't just square the clocks up in the first place, so that in the last example the clock hand would itself have a length of 0.01. That will not work, because to account for interference we're going to want to add clocks together. And adding 0.01 to 0.01, say, which gives 0.02, is not the same as adding 0.1 to 0.1 and then squaring, which gives 0.04. We can illustrate this key idea in quantum theory with another example. Imagine doing something to a particle such that it is described by a specific array of clocks. Also imagine we have a device that can measure the location of particles. A simple to imagine but not so simple to build device might be a little box that we can rapidly erect around any region of space. If the theory says that the chance of finding a particle at some point is 0.01, because the clock hand at that point has length 0.1, then when we erect the box around that point, we have a 1 in 100 chance of finding the particle inside the box afterwards. This means that it is unlikely that we'll find anything in the box. However, if we are able to reset the experiment by setting everything up such that the particle is once again described by the same initial set of clocks, then we could redo the experiment as many times as we wish. Now, for every 100 times we look in the box, we should, on average, discover that there is a particle inside it once. It will be empty the remaining 99 times. The interpretation of the squared length of the clock hand as the probability to find a particle at a particular place is not particularly difficult to grasp, but it does seem as if we, or to be more precise, Max Born, plucked it out of the blue. And indeed, from a historical perspective, it proved very difficult for some great scientists, Einstein and Schrödinger among them, to accept. Looking back on the summer of 1926, 50 years later, Dirac wrote, "This problem of getting the interpretation proved to be rather more difficult than just working out the equations." Despite this difficulty, it is noteworthy that by the end of 1926, the spectrum of light emitted from the hydrogen atom, one of the great puzzles of 19th century physics, had already been computed using both Heisenberg's and Schrödinger's equations. Dirac eventually proved that their two approaches were in all cases entirely equivalent. Einstein famously expressed his objection to the probabilistic nature of quantum mechanics in a letter to Born in December 1926. "The theory says a lot, but does not really bring us any closer to the secret of the old one. I, at any rate, am convinced that he is not playing at dice." The issue was that, until then, it had been assumed that physics was completely deterministic. Of course, the idea of probability is not exclusive to quantum theory. It's regularly used in a variety of situations, from gambling on horse races to the science of thermodynamics, upon which whole swathes of Victorian engineering rested. But the reason for this is a lack of knowledge about the part of the world in question, rather than something fundamental. Think about tossing a coin, the archetypal game of chance. We are all familiar with probability in this context. If we toss the coin 100 times, we expect, on average, that 50 times it will land heads and 50 times tails. Pre-quantum theory, we were obliged to say that if we knew everything there is to know about the coin, the precise way we tossed it into the air, the pull of gravity, the details of little air currents that swish through the room, the temperature of the air, etc., then we could, in principle, work out whether the coin would land heads or tails. The emergence of probabilities in this context is therefore a reflection of our lack of knowledge about the system, rather than something intrinsic to the system itself. The probabilities in quantum theory are not like this at all. They are fundamental. It is not the case that we can only predict the probability of a particle being in one place or another because we are ignorant. We can't, even in principle, predict what the position of a particle will be. What we can predict with absolute precision is the probability that a particle will be found in a particular place if we look for it. More than that, we can predict with absolute precision how this probability changes with time. Born expressed this beautifully in 1926. The motion of particles follows probability laws, but the probability itself propagates according to the law of causality. This is exactly what Schrödinger's equation does. It is an equation that allows us to calculate exactly what the wave function will look like in the future, given what it looks like in the past. In that sense, it is analogous to Newton's laws. The difference is that whilst Newton's laws allow us to calculate the position and speed of particles at any particular time in the future, quantum mechanics allows us to calculate only the probability that they will be found at a particular place. This loss of predictive power was what bothered Einstein and many of his colleagues. With the benefit of over 80 years of hindsight and a great deal of hard work, the debate now seems somewhat redundant, and it's easy to dismiss it with the statement that Born, Heisenberg, Pauli, Dirac and others were correct, and Einstein, Schrödinger and the old guard were wrong. But it was certainly possible back then to believe that quantum theory was incomplete in some way, and that the probabilities appear, just as in thermodynamics or coin tossing, because there is some information about the particles that we are missing. Today, that idea gains little purchase. Theoretical and experimental progress indicate that nature really does use random numbers, and the loss of certainty in predicting the positions of particles is an intrinsic property of the physical world. Probabilities are the best we can do. 4. Everything that can happen does happen. We've now set up a framework within which we can explore quantum theory in detail. The key ideas are very simple in their technical content, but tricky in the way they challenge us to confront our prejudices about the world. We have said that a particle is to be represented by lots of little clocks dotted around, and that the length of the clock hand at a particular place, squared, represents the probability that the particle will be found at that place. The clocks are not the main point. They are a mathematical device we'll use to keep track of the odds on finding a particle somewhere. We also gave a rule for adding clocks together, which is necessary to describe the phenomenon of interference. We now need to tie up the final loose end and look for the rule that tells us how the clocks change from one moment to the next. This rule will be the replacement of Newton's first law, in the sense that it will allow us to predict what a particle will do if we leave it alone. Let's begin at the beginning and imagine placing a single particle at a point. We know how to represent a particle at a point, and this is shown in figure 4.1 in the reference PDF. There will be a single clock at that point with a hand of length 1, because 1 squared is 1, and that means the probability to find the particle there is equal to 1, i.e. 100%. Let's suppose that the clock reads 12 o'clock, although this choice is completely arbitrary. As far as the probability is concerned, the clock hand can point in any direction, but we have to choose something to start with, so 12 o'clock will do. The question we want to answer is the following. What is the chance that the particle will be located somewhere else at a later time? In other words, how many clocks do we have to draw, and where do we have to place them at the next moment? To Isaac Newton, this would have been a very dull question. If we place a particle somewhere and do nothing to it, then it's not going to go anywhere. But nature says, quite categorically, that this is simply wrong. In fact, Newton could not be more wrong. Here is the correct answer. The particle can be anywhere else in the universe at the later time. That means we have to draw an infinite number of clocks, one at every conceivable point in space. That sentence is worth listening to lots of times. Probably we need to say more. Allowing the particle to be anywhere at all is equivalent to assuming nothing about the motion of the particle. This is the most unbiased thing we can do, and that does have a certain aesthetic appeal to it, or aesthetic appeal depending on your point of view. Although, admittedly, it does seem to violate the laws of common sense, and perhaps the laws of physics as well. A clock is a representation of something definite, the likelihood that a particle will be found at the position of the clock. If we know that a particle is at one particular place at a particular time, we represent it by a single clock at that point. The proposal is that if we start with a particle sitting at a definite position at time 0, then at time 0 plus a little bit, we should draw a vast, indeed infinite array of new clocks, filling the entire universe. This admits the possibility that the particle hops off to anywhere and everywhere else in an instant. Our particle will simultaneously be both a nanometer away and also a billion light years away in the heart of a star in a distant galaxy. This sounds, to use our native northern vernacular, daft. But let's be very clear. The theory must be capable of explaining the double-slit experiment. And just as a wave spreads out if we dip a toe into still water, so an electron initially located somewhere must spread out as time passes. What we need to establish is exactly how it spreads. Unlike a water wave, we are proposing that the electron wave spreads out to fill the universe in an instant. Technically speaking, we'd say that the rule for particle propagation is different from the rule for water wave propagation, although both propagate according to a wave equation. The equation for water waves is different from the equation for particle waves, which is the famous Schrödinger equation we mentioned in the last chapter, but both encode wavy physics. The differences are in the details of how things propagate from place to place. Incidentally, if you know a little about Einstein's theory of relativity, you might be getting nervous when we speak of a particle hopping across the universe in an instant, because that would seem to correspond to something traveling faster than the speed of light. Actually, the idea that a particle can be here and an instant later somewhere else very far away is not in itself in contradiction with Einstein's theories, because the real statement is that information cannot travel faster than the speed of light. And it turns out that quantum theory remains constrained by that. As we shall learn, the dynamics corresponding to a particle leaping across the universe are the very opposite of information transfer, because we cannot know where the particle will leap to beforehand. It seems we're building a theory on complete anarchy, and you might naturally be concerned that nature surely cannot behave like this. But as we shall see as the book unfolds, the order we see in the everyday world really does emerge out of this fantastically absurd behavior. If you're having trouble swallowing this anarchic proposal, that we have to fill the entire universe with little clocks in order to describe the behavior of a single subatomic particle from one moment to the next, then you are in good company. Lifting the veil on quantum theory and attempting to interpret its inner workings is baffling to everyone. Niels Bohr famously wrote that those who are not shocked when they first come across quantum mechanics cannot possibly have understood it. And Richard Feynman introduced Volume 3 of the Feynman Lectures on Physics with the words, "I think I can safely say that nobody understands quantum mechanics." Fortunately, following the rules is far simpler than trying to visualize what they actually mean. The ability to follow through the consequences of a particular set of assumptions carefully without getting too hung up on the philosophical implications is one of the most important skills a physicist learns. This is absolutely in the spirit of Heisenberg. Let us set out our initial assumptions and compute their consequences. If we arrive at a set of predictions that agree with observations of the world around us, then we should accept the theory as good. Many problems are far too difficult to solve in a single mental leap, and deep understanding rarely emerges in eureka moments. The trick is to make sure that you understand each little step, and after a sufficient number of steps, the bigger picture should emerge. Either that, or we realize we have been barking up the wrong tree and have to start over from scratch. The little steps we've outlined so far are not difficult in themselves, But the idea that we have decided to take a single clock and turn it into an infinity of clocks is certainly a tricky concept, especially if you try to imagine drawing them all. Eternity is a very long time, to paraphrase Woody Allen, especially near the end. Our advice is not to panic or give up, and in any case, the infinity bit is a detail. Our next task is to establish the rule that tells us what all those clocks should actually look like at some time after we laid down the particle. The rule we are after is the essential rule of quantum theory, although we will need to add a second rule when we come to consider the possibility that the universe contains more than just one particle. But first things first, for now, let's focus on a single particle alone in the universe. No one can accuse us of rushing into things. At one instant in time, we'll suppose we know exactly where it is, and it's therefore represented by a single solitary clock. Our specific task is to identify the rule that will tell us what each and every one of the new clocks scattered around the universe should look like at any time in the future. We'll first state the rule without any justification. We'll come back to discuss just why the rule looks like it does in a few paragraphs, but for now, we should treat it as one of the rules in a game. Here's the rule. At a time t in the future, a clock at distance x from the original clock has its hand wound in an anti-clockwise direction by an amount proportional to x squared. The amount of winding is also proportional to the mass of the particle m and inversely proportional to the time t. In symbols, this means we are to wind the clock hand anti-clockwise by an amount proportional to mx squared over t. In words, it means that there is more winding for a more massive particle, more winding the further away the clock is from the original, and less winding for a bigger step forward in time. This is an algorithm, a recipe if you like, that tells us exactly what to do to work out what a given arrangement of clocks will look like at some point in the future. At every point in the universe, we draw a new clock with its hand wound around by an amount given by our rule. This accounts for our assertion that the particle can, and indeed does, hop from its initial position to each and every other point in the universe, spawning new clocks in the process. To simplify matters, we have imagined just one initial clock, but of course at some instant in time there might already be many clocks, representing the fact that the particle is not at some definite location. How are we to figure out what to do with a whole cluster of clocks? The answer is that we are to do what we did for one clock, and repeat that for each and every one of the clocks in the cluster. Figure 4.2 in the reference PDF illustrates this idea. The initial set of clocks are represented by the little circles, and the arrows indicate that the particle hops from the site of every initial clock to the point X, depositing a new clock in the process. Of course, this delivers one new clock to X for every initial clock, and we must add all these clocks together in order to construct the final definitive clock at X. The size of this final clock's hand gives us the chance of finding the particle at X at the later time. It is not so strange that we should be adding clocks together when several arrive at the same point. Each clock corresponds to a different way that the particle could have reached X. This addition of the clocks is understandable if we think back to the double-slit experiment. We are simply trying to rephrase the wave description in terms of clocks. We can imagine two initial clocks, one at each slit. Each of these two clocks will deliver a clock to a particular point on the screen at some later time, and we must add these two clocks together in order to obtain the interference pattern. If you're having trouble with that last sentence, try replacing the word clock with wave. In summary, therefore, the rule to calculate what the clock looks like at any point is to transport all the initial clocks to that point one by one, and then add them together using the addition rule we encountered in the previous chapter. Since we developed this language in order to describe the propagation of waves, we can also think about more familiar waves in these terms. The whole idea, in fact, goes back a long way. Dutch physicist Christian Huygens famously described the propagation of light waves like this as far back as 1690. He did not speak about imaginary clocks, but rather he emphasized that we should regard each point on a light wave as a source of secondary waves, just as each clock spawns many secondary clocks. These secondary waves then combine to produce a new resultant wave. The process repeats itself, so that each point in the new wave also acts as a source of further waves, which again combine, and in this way a wave advances. We can now return to something that may quite legitimately have been bothering you. Why on earth did we choose the quantity mx²/t to determine the amount of winding of the clock hand? This quantity has a name. It is known as the action, and it has a long and venerable history in physics. Nobody really understands why nature makes use of it in such a fundamental way, which means that nobody can really explain why these clocks get wound round by the amount they do. Which somewhat begs the question, how did anyone realize it was so important in the first place? The action was first introduced by the German philosopher and mathematician Gottfried Leibniz in an unpublished work written in 1669, although he did not find a way to use it to make calculations. It was reintroduced by the French scientist Pierre-Louis Moreau de Maupertuis in 1744, and subsequently used to formulate a new and powerful principle of nature by his friend, the mathematician Leonhard Euler. Imagine a ball flying through the air. Euler found that the ball travels on a path such that the action computed between any 2 points on the path is always the smallest that it can be. For the case of a ball, the action is related to the difference between the kinetic and potential energies of the ball. The kinetic energy is equal to mv²/2, and the potential energy is mgh, when the ball is a height h above the ground. G is the rate at which all objects accelerate in the vicinity of the Earth. The action is their difference integrated between the times associated with the 2 points on the path. This is known as the principle of least action, and it can be used to provide an alternative to Newton's laws of motion. At first sight, it's a rather odd principle, because in order to fly in a way that minimizes the action, the ball would seem to have to know where it is going before it gets there. How else could it fly through the air such that when everything is done, the quantity called the action is minimized? Phrased in this way, the principle of least action sounds teleological. That is to say, things appear to happen in order to achieve a pre-specified outcome. Teleological ideas generally have a rather bad reputation in science, and it's easy to see why. In biology, a teleological explanation for the emergence of complex creatures would be tantamount to an argument for the existence of a designer, whereas Darwin's theory of evolution by natural selection provides a simpler explanation that fits the available data beautifully. There is no teleological component to Darwin's theory. Random mutations produce variations in organisms, and external pressures from the environment and other living things determine which of these variations are passed on to the next generation. This process alone can account for the complexity we see in life on Earth today. In other words, there is no need for a grand plan, and no gradual ascent of life towards some sort of perfection. Instead, the evolution of life is a random walk, generated by the imperfect copying of genes in a constantly shifting external environment. The Nobel Prize-winning French biologist Jacques Monod went so far as to define a cornerstone of modern biology as the systematic or axiomatic denial that scientific knowledge can be obtained on the basis of theories that involve, explicitly or not, a teleological principle. As far as physics is concerned, there is no debate as to whether or not the least action principle actually works, for it allows calculations to be performed that correctly describe nature, and it is a cornerstone of physics. It can be argued that the least action principle is not teleological at all, but the debate is in any case neutralized once we have a grasp of Feynman's approach to quantum mechanics. The ball flying through the air knows which path to choose because it actually, secretly, explores every possible path. How was it discovered that the rule for winding the clocks should have anything to do with this quantity called the action? From a historical perspective, Dirac was the first to search for a formulation of quantum theory that involved the action. But rather eccentrically, he chose to publish his research in a Soviet journal to show his support for Soviet science. The paper, entitled The Lagrangian in Quantum Mechanics, was published in 1933 and languished in obscurity for many years. In the spring of 1941, the young Richard Feynman had been thinking about how to develop a new approach to quantum theory using the Lagrangian formulation of classical mechanics, which is the formulation derived from the principle of least action. He met Herbert Jahler, a visiting physicist from Europe, at a beer party in Princeton one evening, and as physicists tend to do when they've had a few drinks, they began discussing research ideas. Jahler remembered Dirac's obscure paper, and the following day they found it in the Princeton library. Feynman immediately started calculating using Dirac's formalism, and in the course of an afternoon, with Jahler looking on, he found that he could derive the Schrödinger equation from an action principle. This was a major step forward, although Feynman initially assumed that Dirac must have done the same, because it was such an easy thing to do. Easy, that is, if you're Richard Feynman. Feynman eventually asked Dirac whether he'd known that with a few additional mathematical steps his 1933 paper could be used in this way. Feynman later recalled that Dirac, lying on the grass in Princeton after giving a rather lackluster lecture, simply replied, "No, I didn't know. That's interesting." Dirac was one of the greatest physicists of all time, but a man of few words. Eugene Wigner, himself one of the greats, commented that Feynman is a second Dirac, only this time human. To recap, we have stated a rule that allows us to write down the whole array of clocks representing the state of a particle at some instant in time. It's a bit of a strange rule. Fill the universe with an infinite number of clocks, all turned relative to each other by an amount that depends on a rather odd but historically important quantity called the action. If two or more clocks land at the same point, add them up. The rule is built on the premise that we must allow a particle the freedom to jump from any particular place in the universe to absolutely anywhere else in an infinitesimally small moment. We said at the outset that these outlandish ideas must ultimately be tested against nature to see whether anything sensible emerges. To make a start on that, let's see how something very concrete, one of the cornerstones of quantum theory, emerges from this apparent anarchy: Heisenberg's uncertainty principle. Heisenberg's uncertainty principle. Heisenberg's uncertainty principle is one of the most misunderstood parts of quantum theory, a doorway through which all sorts of charlatans and purveyors of tripe can force their philosophical musings. Wikipedia describes tripe as a type of edible offal from the stomachs of various farm animals, but it is colloquially used to mean nonsense. Either definition is appropriate here. He presented it in 1927 in a paper entitled Über den anschaulichen Inhalt der quantentheoretischen Kinematik und Mechanik, which is very difficult to translate into English. The difficult word is anschaulich, which means something like physical or intuitive. Heisenberg seems to have been motivated by his intense annoyance that Schrödinger's more intuitive version of quantum theory was more widely accepted than his own, even though both formalisms led to the same results. In the spring of 1926, Schrödinger was convinced that his equation for the waveform provided a physical picture of what was going on inside atoms. He thought that his wave function was a thing you could visualize, and was related to the distribution of electric charge inside the atom. This turned out to be incorrect, but at least it made physicists feel good during the first 6 months of 1926, until Born introduced his probabilistic interpretation. Heisenberg, on the other hand, had built his theory around abstract mathematics, which predicted the outcomes of experiments extremely successfully, but was not amenable to a clear physical interpretation. Heisenberg expressed his irritation to Pauli in a letter on the 8th of June 1926, just weeks before Born threw his metaphorical spanner into Schrödinger's intuitive approach. The more I think about the physical part of Schrödinger's theory, the more disgusting I find it. What Schrödinger writes about the Anschaulichkeit of his theory, I consider mist. The translation of the German word mist is rubbish, or bullshit, or tripe. What Heisenberg decided to do was to explore what an intuitive picture, or Anschaulichkeit, of a physical theory should mean. What, he asked himself, does quantum theory have to say about the familiar properties of particles, such as position? In the spirit of his original theory, he proposed that a particle's position is a meaningful thing to talk about, only if you also specify how you measure it. So you can't ask where an electron actually is inside a hydrogen atom, without describing exactly how you'd go about finding out that information. This might sound like semantics, but it most definitely is not. Heisenberg appreciated that the very act of measuring something introduces a disturbance, and that as a result there is a limit on how well we can know an electron. Specifically, in his original paper, Heisenberg was able to estimate what the relationship is between how accurately we can simultaneously measure the position and the momentum of a particle. In his famous uncertainty principle, he stated that if delta x is the uncertainty in our knowledge of the position of a particle, and delta p is the corresponding uncertainty in the momentum, then delta x delta p tilde h, where h is Planck's constant and the tilde symbol means is similar in size to. In words, the product of the uncertainty in the position of a particle and the uncertainty in its momentum will be roughly equal to Planck's constant. This means that the more accurately we identify the location of a particle, the less well we can know its momentum, and vice versa. Heisenberg came to this conclusion by contemplating the scattering of photons off electrons. The photons are the means by which we see the electron, just as we see everyday objects by scattering photons off them and collecting them in our eyes. Ordinarily, the light that bounces off an object disturbs the object imperceptibly. But that is not to deny our fundamental inability to absolutely isolate the act of measurement from the thing one is measuring. One might worry that it could be possible to beat the limitations of the uncertainty principle by devising a suitably ingenious experiment. We are about to show that this is not the case, and the uncertainty principle is absolutely fundamental, because we are going to derive it using only our theory of clocks.
The deeper we look into the universe, the more mysteries it reveals to us. Gravity, the invisible force that binds the cosmos together, may not be as unchanging as we once thought. From ancient civilizations to Einstein's groundbreaking discoveries, our understanding of gravity has constantly evolved. However, recent discoveries suggest that there may be a cosmic glitch on the grandest of scales. A subtle deviation in the force governing galaxies and stars. Ancient scientists pondered the nature of gravity, laying the foundation for Newton's elegant laws. But it was Einstein in the early 20th century who changed our perception. His theory of general relativity describes gravity not as a force, but as a curvature of space-time itself. Despite its success in predicting phenomena such as black holes and gravitational waves, Einstein's theory has its limitations. When we turn our eyes to the scale of galaxy clusters and beyond, we encounter inconsistencies. Gravity seems to weaken slightly over billions of light years, and it's this phenomena that researchers now call a cosmic glitch. This anomaly may hint at new physics, perhaps an extension of the standard cosmological model to include a varying gravitational constant. Such a modification could reconcile these inconsistencies without reversing the established successes of general relativity. The discovery of a cosmic glitch is forcing us to rethink our understanding of gravity. Could this be the first clue in a new puzzle that will eventually lead us to a theory that unifies the fundamental forces of nature? Long before the scientific revolution, ancient civilizations had encountered the concept of gravity, although they understood it in very different ways. The Greeks, for example, believed in the geocentric model, in which the Earth was the center of the universe. Aristotle argued that objects fall in the direction of their natural place, and this theory dominated Western thought for centuries. In ancient India, Hindu scriptures describe the concept of gravity as an inherent force that pulls objects toward the earth. Similarly, the Chinese philosopher Mozi in the 4th century BC suggested that objects fall because of the force of the earth's energy. These early ideas, although primitive by modern standards, laid the foundation for future scientific research. It was not until the Renaissance that a more precise understanding emerged. The work of Copernicus, Galileo, and Kepler challenged Aristotelian views, paving the way for the pioneering work of Isaac Newton. Newton's formulation of the law of universal gravitation in the 17th century was a monumental leap. He described gravity as the force that attracts two bodies to each other proportional to their masses and inversely proportional to the square of the distance between them. This elegant equation united the heavens and the earth under a single universal law. In the early 20th century, Albert Einstein revolutionized our understanding of gravity. He proposed the general theory of relativity, which described gravity not as a force, but as a curvature of space-time caused by mass and energy. Einstein's equations suggested that massive objects such as stars and planets warp the fabric of space-time, creating what we perceive as gravity. This concept was visually confirmed during the 1919 solar eclipse expedition led by Sir Arthur Eddington. By observing the bending of starlight around the sun, Eddington provided one of the first experimental confirmations of the general theory of relativity. Consider this. Almost a century ago, Einstein added fudge factor to his equations to bring them in line with the then-accepted idea of a static universe, and later called this factor his greatest mistake. However, this very constant, lambda, reappeared many years later to explain the accelerating expansion of the universe. Einstein's theory also predicted phenomena such as black holes and gravitational waves that we have only begun to observe in recent years, further confirming the validity of his theory. The Event Horizon Telescope's image of a black hole in 2019 and LIGO's detection of gravitational waves in 2015 were monumental achievements in modern astrophysics. Despite its successes, however, general relativity has its limitations. It's inconsistent with quantum mechanics, the basis for understanding the subatomic world. This has led scientists to search for a more comprehensive theory that unites these two pillars of physics. In the quest to understand the universe, scientists have discovered anomalies that challenge our generally accepted understanding of gravity. These inconsistencies indicate that our current theories, while robust, may be incomplete. The general theory of relativity proposed by Albert Einstein has become a cornerstone of modern physics. The theory has been remarkably successful in explaining a wide range of phenomena, from the orbits of planets to the behavior of light around massive objects. However, recent research points to potential inconsistencies when the general theory of relativity is applied at cosmic scales. Recent research conducted by Robin, Y. Wen, and colleagues in 2024 hypothesized a cosmic glitch in gravity. Their research suggests that the gravitational constant may not be exactly constant over vast cosmic distances. In particular, gravity appears to be about 1% weaker when it comes to distances of billions of light years. This anomaly causes difficulties in our understanding of what's happening because it implies a deviation from Einstein's theory of extreme scales. To solve this problem, scientists propose a modification of the standard cosmological model, known as lambda, cold dark matter. This adaptation involves adding a new parameter that slightly corrects the gravitational constant on cosmic scales, without affecting its proven accuracy on smaller scales. The conflict between general relativity and quantum mechanics further complicates our understanding of gravity. General relativity best describes large-scale structures, such as galaxies and black holes, while quantum mechanics provides the best framework for understanding particles on the smallest scales. However, the two theories are fundamentally incompatible. One of the most striking proofs of this contradiction is the behavior of black holes. The general theory of relativity predicts the existence of singularities, points of infinite density at the centers of black holes. In contrast, quantum mechanics suggests that such infinities cannot exist, indicating the need for a new theory that could unify the two systems. Recent advances in technology, such as precise measurements of the cosmic microwave background satellite, have provided new data that both confirm and refute existing theories. These observations have led to the discovery of the Hubble tension, a significant discrepancy between the observed and predicted expansion rate of the universe. The Hubble contradiction suggests that either our understanding of the early universe or the nature of dark matter and gravity needs revision. The cosmic glitch theory, which introduces a small change in the gravitational constant, offers one potential solution to this problem. In addition, the detection of gravitational waves by the LIGO and Virgo collaborations has opened new possibilities for testing gravitational theories. These observations provide an opportunity to observe the universe in a new way, potentially revealing deviations from the general theory of relativity that could not be detected before. The intersection of these anomalies with the predictions of quantum mechanics could lead to revolutionary discoveries. Experiments conducted at CERN at the Large Hadron Collider are aimed at exploring the boundaries between these two realms, searching for evidence that could bridge the gap between general relativity and quantum mechanics. In search of understanding of gravitation, some scientists suggest that it may not be a fundamental force, but rather an emergent phenomenon arising from deeper principles. This idea does not cross the traditional ideas about gravitation, but rather opens new ways of theoretical research. One well-known alternative is modified Newtonian dynamics, or MOND, proposed by Mordecai Milgrom in the early 1980s. The theory suggests that Newton's laws need adjustment at the very low accelerations, characteristic of the outskirts of galaxies. According to MOND, these changes can explain the observed rotation curves of galaxies without involving dark matter. MOND has had some success in predicting the behavior of stars and galaxies, where traditional theories of gravity fail. However, it is unable to explain phenomena on large cosmic scales, such as galaxy clusters and the cosmic microwave background, where dark matter remains a more acceptable explanation. Another interesting theory is emergent gravity, Eric Verlin proposed in 2010. Verlin suggests that gravity is not a fundamental interaction, but arises from thermodynamic principles of information storage on holographic screens. From this point of view, the universe can be described as a hologram, where gravity arises from changes in entropy associated with the information stored on these screens. To simplify, imagine the universe as a giant laboratory where books, information, are stored on shelves, holographic screens. The arrangement and number of books change over time, affecting the overall structure and creating what we think of as gravity. Verlin's emergent gravity has intriguing implications for our understanding of dark matter. Instead of invisible particles, the effects attributed to dark matter may be a consequence of emergent properties of space-time itself. This theory allows us to take a new look at the connection between gravitation and thermodynamics. In addition to Mond and Verlin's theory, there are several other alternative approaches. One such theory is modified gravity, or simply MOG, proposed by John Moffat, which introduces additional gravitational fields to explain the rotation curves of galaxies and the dynamics of galaxy clusters without dark matter. Mogg suggests that these additional fields modify the strength of gravity on different scales. In addition, the concept of entropic gravity, closely related to Verlin's ideas, suggests that gravity arises from the tendencies of systems to increase entropy. This thermodynamic interpretation is consistent with the principles of statistical mechanics, providing a new lens through which gravitational interactions can be viewed. These alternative theories, although not universally recognized, open before us new perspectives and require further research and experiments. They force us to reconsider the view of gravitation not as an inherent force of nature, but as a consequence of deeper, fundamental principles. As we move toward the middle of the 21st century, our quest to understand gravity continues to push the boundaries of technology and knowledge. State-of-the-art experiments and missions are being designed to test the limits of our gravitational theories, yielding new insights and potentially revolutionary discoveries. One of the most significant ongoing projects is, of course, the acclaimed James Webb Space Telescope. JWST observations to date have been crucial for testing theories of gravity on the largest scales, especially those that predict deviations from general relativity. Another key player in gravitational research is the Large Hadron Collider at CERN. This particle gas pedal, the largest and most powerful in the world, collides protons at unprecedented energies. These collisions allow physicists to study fundamental particles and forces, including the potential discovery of particles that can mediate gravitational interaction at quantum scales. Experiments at the LHC are critical to understanding how gravity can combine with other fundamental forces. Space missions such as the Laser Interferometer Space Antenna, LISA, also loom on the horizon. Planned for launch in the mid-2030s, LISA will consist of 3 spacecraft forming a giant triangular interferometer in space. This facility will detect gravitational waves with much greater sensitivity than existing ground-based detectors, such as LIGO and Virgo. The goal of LISA is to observe gravitational waves from the merger of supermassive black holes, which will test Einstein's general theory of relativity and provide new insights into dark matter and dark energy. But let's get closer to home, where Event Horizon Telescope continues to make groundbreaking contributions. In 2019, EHT obtained the first ever image of the black hole M87, demonstrating the power of synchronizing telescopes around the world to create a planet-sized interferometer. EHT is now focused on even more precise observations of black holes, including the one at the center of our galaxy, Sagittarius A. These observations will test the predictions of the general theory of relativity in extreme gravitational fields. In addition, let us recall the already mentioned recent study by Wen et al., which proposes a cosmic glitch in gravity, suggesting that the gravitational constant may vary over cosmic distances. This study will be further tested with data from the Planck satellite and future cosmic microwave background experiments. Upcoming missions such as the Simons Observatory and CMB-S4 aim to make more precise measurements of the CMB that can confirm or refute the existence of such a glitch, offering a deeper understanding of the nature of gravity at the largest scales. In addition, the Vera C. Rubin Observatory, which will soon become fully operational, will conduct the Legacy Survey of Space and Time. This survey will map billions of galaxies, providing a detailed view of the structure and evolution of the universe. The data from LLST will help test theories of dark matter, dark energy, and gravity, and possibly reveal new phenomena that will change our current understanding. Another exciting frontier is the search for quantum gravity using benchtop experiments. These experiments use highly sensitive equipment to detect tiny gravitational effects on very small scales, where quantum mechanical effects become significant. Such experiments are designed to bridge the gap between general relativity and quantum mechanics, which may lead to a unified theory of gravitation. These state-of-the-art experiments and missions represent the cutting edge of gravitational research. They are designed not only to test existing theories, but also to discover new phenomena that could revolutionize our understanding of the universe. Revising our understanding of gravity could have profound implications for cosmology, astrophysics, and technology. The anomalies and alternative theories that we've studied suggest that our understanding of gravity is far from complete. As our models improve, we can expect significant progress in several key areas. In cosmology, a more accurate model of gravity could solve existing mysteries, such as the nature of dark matter and dark energy. If gravity behaves differently over vast cosmic distances, it could provide a new explanation for the accelerated expansion of the universe and the distribution of galaxies. This could lead to a unified model of the cosmos that better integrates general relativity and quantum mechanics. For astrophysics, improved gravitational theories can improve our understanding of black holes, neutron stars, and other extreme environments. By accurately describing the behavior of matter under the influence of intense gravitational fields, we can better understand the life cycle of stars and the dynamics of galaxies. This knowledge may even reveal new types of astrophysical objects or phenomena. Technologically, advances in the understanding of gravity will undoubtedly spur innovations in various fields. For example, accurate measurements of gravitational waves can improve navigation systems and geophysical research. In addition, breakthroughs in quantum gravity could lead to new technologies based on quantum information and communication, revolutionizing computing and data transmission. Imagine a future in which our understanding of gravity will enable ultra-precise space-time sensors, leading to the development of autonomous vehicles, precision agriculture, and disaster prediction systems. As we wait for the launch of new missions, projects, and discoveries, the anticipation grows. Each step forward brings us closer to unlocking the mysteries of the universe, promising a future in which our understanding of gravity and the cosmos is richer and deeper than ever before. Surely you've heard by now that black holes can be so massive that they can outshine entire galaxies. But some of them are quite mobile, so much so that they roam the Milky Way like cosmic ghosts, undetectable. Of course, you may be confused or even mesmerized by the fact that the nearest black hole to Earth is not as far away as you think. And when these cosmic giants collide, they generate frequencies as unique as fingerprints. Frequencies that may hold the key to unlocking the deepest mysteries of the universe. But did you know that these waves interact in a far more complex way than we ever imagined? Get ready for an extraordinary journey as we begin to delve into the mysteries of black holes, the truly enigmatic titans of the universe. In the cosmic pattern, black holes are weavers of riddles and paradoxes. Although we're familiar with small black holes, the remnants of dying stars and supermassive ones lurking in the hearts of galaxies, there is an enigmatic class that eludes our telescopic gaze: intermediate mass black holes. The Hubble Space Telescope, our eye in the sky, recently focused its attention on Messier 4, the ball cluster closest to Earth. What he discovered was nothing short of groundbreaking. A black hole with a mass about 800 times the mass of our Sun. This celestial object is somewhere between 6,000 and 7,200 light-years away from us. Why is this so important, you ask? Well, for years, astronomers have struggled with a gap in the black hole genealogical tree. We've had evidence of both small black holes, a few times the mass of our Sun, and supermassive black holes with masses in the millions or billions of solar masses. But black holes of intermediate mass turned out to be a missing link, mysterious relatives about which everyone has heard but no one has met. An equally interesting question is how these black holes of intermediate mass form. One theory suggests that they could be the nuclei of dwarf galaxies that lost their outer stars when they merged into larger galaxies. Another theory states that they could have formed from the collision and merger of smaller black holes. Identifying these elusive black holes is no easy task. It requires a symphony of scientific instruments, from X-ray observatories to precise calculations based on the motion of surrounding stars. The Hubble Space Telescope, with its unprecedented resolution, has played an important role in this discovery. The presence of a black hole affects its cosmic environment. By studying the gravitational choreography of stars orbiting this massive object, scientists have been able to estimate its mass. It's like understanding the character of an invisible puppeteer by watching the puppets dance. The discovery of intermediate mass black holes could rewrite the cosmic narrative. They may be key players in the formation of galaxies, and may even hold clues to the mysterious dark matter that makes up most of the universe. In a cosmic world where distances are often incomprehensible, the term neighbor takes on new meaning. While our closest celestial neighbor, the Moon, is only 238,855 miles away, our nearest neighboring black hole, Gaia BH1, is thousands of light years away from Earth. But what does that proximity mean in the context of black holes? And why is this proximity important? In 2020, the European Southern Observatory, ESO, made headlines when it announced the discovery of a black hole in the HR 6819 system, located just 1,000 light-years away. This would make it the closest known black hole to Earth. However, this claim was later disproved. Subsequent research by Abigail Frost of the University of Leuven in Belgium found that HR 6819 does not contain a black hole at all. Instead, it's a double star system in which one star absorbs the mass of the other, a process known as stellar vampirism. This revelation was more than just a correction. It opened up new possibilities for studying stellar evolution and interactions. After the ejection of HR 6819, the title of the closest black hole to Earth went to Gaia BH1. This black hole was discovered by the Gaia Space Observatory, a mission of the European Space Agency, ESA. The main task of Gaia is to map the Milky Way in unprecedented detail, and it was thanks to this painstaking work that Gaia BH1 was discovered. As the closest known black hole to Earth, Gaia BH1 offers a unique opportunity for scientific observations and research. Its relative proximity allows for more detailed measurements, and may help answer fundamental questions about the properties of black holes, such as mass, rotation, and behavior near their event horizons. The study of black holes like Gaia BH1 relies on several observational instruments, from X-ray observatories to radio telescopes. Each instrument represents a piece of the puzzle. The closer a black hole is, the more accurately these instruments will be able to measure its properties, offering a more complete picture of these mysterious objects. Beyond its scientific significance, the idea of a nearby black hole captivates the public imagination. It makes the cosmic more personal and provides a tangible focus for education and outreach. The story of Gaia BH1 can serve as a gateway for people to astronomy and astrophysics, enriching our collective understanding of the universe. In the cosmic theater, black holes often play the role of mysterious villains lurking in the centers of galaxies or double star systems. But what happens when a black hole is left to roam the universe alone, unconnected to any galaxy or star? What causes these black holes to become rogue? And how do astronomers even manage to find such elusive objects? Let's dive into the mysterious world of rogue black holes. The scientific community was ecstatic when astronomers announced the first ever unambiguous discovery of a wandering black hole. Located 5,000 light-years away from Earth, this black hole weighs 7.1 times the mass of our Sun and moves at a staggering speed of about 28 miles per second. The key to this revolutionary discovery lies in a phenomena predicted by Einstein's general theory of relativity, known as gravitational lensing. When a massive object, such as a black hole, passes in front of a background star, its intense gravitational field deflects the light of that star. This creates a brief brightening phenomena, which is how this wandering black hole was discovered. As we know, the birth of a wandering black hole is nothing short of a dramatic event. When a massive star exhausts its nuclear fuel, its core collapses, leading to a supernova explosion. The energy released can be so enormous that it ejects the newborn black hole from its stellar cradle, sending it on an endless journey through space. And this is how our newly discovered wandering black hole likely began its cosmic odyssey. What is even more intriguing is the speed at which this wandering black hole is traveling. Its speed is about 28 miles per second, which is a very large value relative to the nearest stars. This speed is likely the result of the very impact of a dying massive star, sending it on a lonely journey. The discovery of this lone black hole is just the tip of the iceberg. In upcoming missions, such as the European Space Agency's Gaia telescope and NASA's Nancy Grace Roman Space Telescope, astronomers expect to find even more such space travelers. These future discoveries will not only increase the number of known rogue black holes, but also refine our theories about their properties and frequencies. Each galaxy is like a cosmic dance floor, where stars, gas, and dust swirl in a complex choreography. At the center of this dance is a supermassive black hole that sets the rhythm and tempo of the entire galaxy. Research published in the monthly notices of the Royal Astronomical Society shows that galaxies and their central black holes grow together, regardless of their location in the universe. Astronomers have long been puzzled over the relationship between the mass of a galaxy and its central black hole. The two seem to be aware of each other, even though the black hole is much smaller than the galaxy in which it resides. This relationship implies a deep cosmic connection, a kind of cosmic codependency, where the growth of one affects the other. One of the most intriguing questions in astronomy is, which came first, the galaxy or its central black hole? The answer remains elusive. What is clear, however, is that a close connection was established very quickly on a cosmic scale, paving the way for a complex interplay of growth and evolution. Let's dive into the young, gas-rich galaxies, the cradle of giant black holes. These galaxies are like cosmic nurseries, teeming with the raw materials needed for star formation and black hole growth. Studies show that such galaxies, known as blue nuggets, have exceptionally high star formation rates. They are fed by nearby gas streams, which not only accelerate star formation, but also contribute to the rapid growth of their central black holes. When black holes are fed, they become active. The gas around them heats up and emits powerful waves of radiation. This heated gas is less likely to hit the black hole, creating a feedback loop that stabilizes the size of the black hole. However, as the galaxy grows, it can push more gas toward the center, allowing the black hole to feed and grow again. The relationship between galaxies and their black holes adjusts itself. If a black hole is too large for its galaxy, it grows slower, and if it's too small, it catches up due to the abundance of gas and dust in the galaxy. So some galaxies defy the norm. These blue nuggets, despite their small size, have exceptionally large central black holes. As these galaxies age, their star formation stops, and they turn into red nuggets, still retaining their huge black holes. As we move farther into the black hole abyss, it becomes apparent that young, gas-rich galaxies serve as the birthplace of various black hole phenomena, whether they're luminous black holes or intermediate mass, wandering black holes hurtling through space, or the nearest black holes to Earth. Their origins can often be traced back to these bright, young galaxies. Understanding the cradle of these cosmic giants helps us unlock the mysteries that black holes hold. Now, let's look at something really rare. There is a situation where black holes collide. In doing so, they create a cosmic symphony of gravitational waves around them that vibrate in the very fabric of space-time. These waves, first detected by the Laser Interferometer Gravitational Wave Observatory, in 2015, opened a new frontier in astronomy. However, recent research shows that these waves interact in complex ways as they propagate, thereby testing our understanding of gravity and the general theory of relativity. Traditionally, scientists have used linear models to describe these waves. However, a new study has revealed nonlinear effects that reveal a more complex picture. It's akin to the difference between a calm pond and a rough sea. In a calm pond, or linear pond, the throw of a stone creates an isolated ripple. In a stormy sea, or nonlinear, however, multiple forces interact to create complex wave patterns. When black holes collide, they emit unique frequencies or chirps. These sounds are like individual notes in our cosmic symphony, each telling us something about the properties of colliding black holes. They offer a new way to test the limits of the general theory of relativity, and may even provide clues to the nature of dark matter. Recent discoveries have shown that pairs of black holes and dwarf galaxies are on a collision course. These dwarf galaxies attract gas that feeds their black holes, causing them to grow even before they merge. This process is a microcosm of the larger universe, where galaxies and their central black holes grow in tandem. These colliding dwarf galaxies offer a glimpse into the early universe, which was filled with similar small galaxies. Most of these eventually merge to form larger galaxies, like our Milky Way. Understanding these processes helps us piece together the cosmic mystery of galaxy and black hole formation. As we travel deeper into the abyss of black holes, we discover that each type, from luminous black holes of intermediate mass to wandering black holes hurtling through space, plays a unique role in this great cosmic symphony. The next generation of gravitational wave detectors will likely deepen our understanding of these cosmic phenomena. And, of course, each discovery, from the frequencies they generate to the nature of gravity itself, undoubtedly adds a new level to our understanding of the universe. As our telescopic eyes become sharper and computational models become more sophisticated, who knows what other cosmic mysteries these giants of the cosmos will reveal. Imagine a single point, just a speck of light, hovering in an endless sea of darkness. It's not just a random dot, it's our home, Earth. But what if we told you that this dot is just a fleeting moment in a cosmic panorama so vast and complex that it defies human comprehension? Imagine a night sky decorated with stars, each representing a sun, many of which have their own planets. Now, multiply that image by 100 billion. Even in this case, you've barely touched the surface. Beyond our Earth, beyond our sun, even beyond our galaxy, lies a structure so vast that everything you know seems like a single thread in an unfathomable cosmic web. The human mind, which is itself a marvel, struggles to grasp this scale. Our brains are built to comprehend the rises and slopes of mountains and the vastness of oceans. But how do we comprehend a structure that stretches billions of light years? Today we're on a journey to explore these galactic threads, the sinews and muscles of the universe itself. We will venture into a realm of the almost incomprehensible, where even the speed of light seems pedestrian. Spiders weave intricate webs, thin but strong, each thread connected to the other in a complex pattern. Architects of nature create these webs to survive, capture prey, and probe the environment. Now, imagine a web woven not by spiders, but by the very fabric of space and time itself. A web that links galaxies, star clusters, and dark matter into a complex web. This is the cosmic web, the grand architecture of our universe. Each node you see here is not a single star or planet, but an entire galaxy, a colossal cluster of billions of stars, planets, and other celestial objects bound by gravity. But what gives this network this structure? The answer lies in something we can't even see: dark matter. Dark matter, which scientists believe makes up about 27% of the universe, acts as the framework on which this web is built. Although invisible, its presence is felt through the gravitational pull that determines the formation of galaxies and the paths they take. The cosmic web was not always as we see it today. It evolved over billions of years, beginning with tiny fluctuations in the density of the early universe. These fluctuations grew, pulled together by gravity, eventually forming the majestic filaments and nodes we now see. One of the most impressive examples of a galactic filament is the Great Wall of Hercules' northern corona. This colossal structure spans a distance of up to 23 billion light-years, making it one of the largest known structures in the universe. Understanding this network is not just an academic exercise. It's a quest to understand our place in the universe. Are we simply an accidental byproduct of cosmic evolution? Or is there a grander design at work here? Scientists use a range of tools to study this network, from telescopes that can see distant galaxies to simulations that model the behavior of dark matter. Each discovery is a piece of the puzzle, a thread of a story that spans the entire universe. Here it is, Earth, a pearl of blue and green, suspended in the vastness of space. A planet teeming with life, from microscopic to magnificent. It's easy to think of the Earth as the center of everything, but in the grand scheme of the universe, it's just a speck. In our solar system alone, Earth is only one of 8 planets orbiting the Sun, and yet it stands out for its unique ability to support life. The oceans, the atmosphere, the magnetic field, all these elements are in delicate balance. Zoom out even further, and our entire solar system becomes a tiny dot in one of the spiral arms of the Milky Way galaxy, a galaxy that's home to hundreds of billions of stars, each potentially containing its own system of planets. In the Milky Way, it's just one galaxy in a cosmic web of hundreds of billions of galaxies. Each of these galaxies is a node, a focal point in this unimaginable structure. Even within our galaxy, the Earth is influenced by forces beyond its control. Dark matter, the invisible backbone of the cosmic web, shapes the structure of the galaxy and, as a result, the environment around the Earth. Yet despite its seemingly insignificant place in the cosmos, Earth is unusual for one reason. It has life. It's the only known celestial body where life not only originated, but has evolved to an incredible level of diversity and complexity. Humanity's quest to understand its place in the universe has led to remarkable scientific advances. Telescopes peer into remote corners of the universe, and supercomputers simulate the cosmic web, helping to answer fundamental questions about the nature of reality. For example, look at the Sun. the blazing ball of plasma that lights up our sky and warms our planet. It's the reason you can see these very images, the reason life exists on Earth. But in the context of the cosmic web, the sun is just one node, a lone star among countless others. Close to the sun, we find other stars, some smaller and cooler, others larger and hotter. Each of these stars is like a bead on a huge cosmic thread, linked together by gravity and dark matter. Our sun is located in the Orion sleeve of the Milky Way, a small spiral arm located about 27,000 light-years from the center of the galaxy. Even within our galaxy, it is far from special, just one of about 400 billion stars. In the great expanse of the cosmic web, stars like our sun form complex nodes that connect larger structures, such as galaxies and galaxy clusters. They are the building blocks, the fundamental units that give the web its shape. So what powers this celestial beacon? The answer is nuclear fusion. Deep in the sun's core, hydrogen atoms collide and fuse to form helium, releasing massive amounts of energy. This energy not only powers the sun, but also balances the gravitational forces trying to compress it. This energy has far-reaching consequences. It provides the Earth with the heat and light necessary for life. It drives our weather systems, powers photosynthesis, and even influences Earth's climate over the long term. Understanding the sun is crucial to understanding the cosmic web. Various missions, such as the Parker Solar Probe and the Solar Dynamics Observatory, have been launched to study the sun's behavior. These missions provide insights into solar cycles, magnetic fields, and even the future of the sun. Although the sun serves as a vital node in the cosmic web, nourishing life on Earth and influencing our local space environment, it's just one example in a universe teeming with stellar diversity. Every star, regardless of its size or lifespan, plays a role in shaping the cosmic web. From the tiniest red dwarfs to massive blue giants, each star is a unique knot contributing to the overall structure of galactic filaments. Stars are often classified by their mass and brightness, and plotted on a graph known as the Hertzsprung-Russell diagram. This diagram shows the life stage of a star and gives clues about its future fate. Take, for example, a red dwarf, the most common type of star in the universe. They're small, cold stars, also called M-type stars. Often less than half the mass of our sun, they make up for their lack of size with longevity, burning for tens to hundreds of billions of years. Red dwarfs are frugal. They turn hydrogen into helium much more slowly than larger stars. This slow lifestyle allows them to be among the longest-lived objects in space. Now compare that to O-type stars, the rare titans of the stellar world. These stars are more than 15 times more massive than the sun and can be 1,000,000 times brighter. Yet they live fast, die young, often in spectacular supernova explosions. O-type stars dramatically end their lives. They collapse under their own gravity and then explode as supernovae. These explosions scatter elements such as carbon, oxygen, and iron into space, promoting the formation of new stars and planets. Star clusters are like cosmic nurseries, places where stars of different types are born. These clusters serve as nodes in the cosmic web, linking different regions of a galaxy and even connecting galaxies to each other through filaments. Computer simulations help astronomers understand how different types of stars contribute to the cosmic network. These virtual models can simulate billions of years of cosmic evolution in a matter of weeks, showing how stars serve as the building blocks of larger cosmic structures. So, we've already found out, stars are not eternal. They are born, live, and eventually die. The life cycle of a star is a cosmic journey spanning billions of years, a journey that plays a key role in the evolution of the universe and the structure of the cosmic web. The birth of a star is a spectacle of cosmic proportions. It begins in a nebula, a vast cloud of gas and dust. Gravity pulls these particles together, getting denser and hotter until nuclear fusion ignites. A new star is born. Once a star reaches the main sequence stage, it enters a period of relative stability. The hydrogen in the core turns to helium, releasing energy that balances the gravitational forces trying to compress the star. This is the longest phase of a star's life, and it's where our sun is now. But even stars like our sun must face change. In about 5 billion years, the sun will run out of hydrogen fuel. Its core will shrink, but its outer layers will expand, turning it into a red giant. This phase is the prelude to the final fate of the star. Depending on its mass, the star will meet one of several ends. Stars with less mass, such as our sun, will shed their outer layers, leaving behind a white dwarf. More massive stars may undergo a supernova explosion, resulting in a neutron star or black hole. These deaths are not in vain. The death agonies of stars scatter important elements into space, elements that will become the building blocks of new stars, planets, and even life. Thus, the life and death of stars is an integral part of the cycle of cosmic creation and destruction. The cosmic web, from individual stars to entire galaxies, is a complex network of interconnected structures. But what binds these galaxies together? What are the threads that weave the complex fabric of the universe? The answer lies in galaxy clusters. Galactic clusters are massive collections of galaxies bound together by gravitational force. They may contain only a few or thousands of galaxies, and often span millions of light years across. Just as dark matter plays a role in individual galaxies, it also acts as an invisible glue in galactic clusters. Even though we can't see it, we know it exists, holding the cluster together and forming its overall structure. Within a cluster, galaxies are not static. They are in constant motion. Some of them may be heading toward the center of the cluster, while others may be on their way to its edge, under the influence of complex gravitational interactions. Sometimes these interactions can lead to dramatic events, such as galactic collisions. When galaxies collide, their stars, gas, and dark matter merge to form a new, larger galaxy. These events are crucial to the evolution of galaxy clusters, and, by extension, the cosmic web. But clusters are not the end of the story. They often cluster together to form superclusters, which are among the largest known structures in the universe. These superclusters serve as the main nodes of the cosmic web, linking numerous clusters and filaments. Understanding galaxy clusters is the key to unlocking the mysteries of the cosmic web. They serve as threads connecting galaxies, forming the paths along which matter and energy flow on cosmic scales. Having studied the colossal structures of galactic clusters, the threads that weave the cosmic web, we now turn our eyes to an even more mysterious phenomenon. What if there were actual threads, strings of pure energy that stitch together the fabric of the universe? These hypothetical one-dimensional defects in space-time could be the loose threads of the universe, remnants of the first moments after the Big Bang. Imagine the universe just moments after the Big Bang, a hot, dense state of pure energy. As the universe cooled and expanded, this energy condensed into matter and structure. However, not everything went smoothly. In some regions, kinks occurred, leading to the formation of cosmic strings. Cosmic strings, if they existed, would be unimaginably thin, but incredibly dense. A string less than an inch wide could weigh as much as the Earth. They would stretch across the vast expanse of the universe, perhaps even from one end to the other. Because of their enormous mass, cosmic strings would exert a strong gravitational pull, affecting the motion of galaxies and even bending light. They could serve as cosmic highways, directing the flow of matter and energy through the universe. The search for cosmic strings continues. Scientists are using a combination of theoretical physics and observational astronomy to search for these elusive structures. If the existence of strings is confirmed, they may become the missing links that will help us understand not only how the universe is organized, but also why it is organized this way. However, let's return to structures of unfathomable scale. Superclusters. They are the gravitational anchors that hold together vast networks of galaxies and galaxy clusters. Imagine moving away from our Milky Way galaxy, past our local group of galaxies, and even beyond our local Virgo supergroup. You'll find a network of superclusters, each containing hundreds to thousands of individual galaxies bound together in a complex dance of gravity. The superclusters are unevenly distributed. They form a kind of cosmic skeleton around which galaxies and galaxy clusters are located. This skeleton gives the cosmic web the shape that defines the large-scale structure of the universe. Within the supercluster, galaxies and clusters are in constant motion under the influence of the collective gravitational pull of the entire structure. This dynamic flow of matter and energy is what keeps the cosmic network alive and ever-changing. Among the most intriguing aspects of superclusters is the presence of gravitational anomalies, like the Great Attractor. These are regions with such a strong gravitational pull that they influence the motion of the entire supercluster, serving as the pivots of the cosmic web. Understanding superclusters is crucial to cosmology. They serve as the largest laboratories for studying the expansion of the universe, the distribution of dark matter, and even the mysterious force of dark energy. The observable universe is estimated by scientists to contain 2 trillion galaxies. And yet, what we can see represents less than 5% of the universe. Standing over the precipice of cosmic understanding, we are humbled by the scale and complexity of the universe. From the smallest particles to the largest galactic filaments, each element serves as a piece of the puzzle. Here we are, a pale blue dot, a mere speck in the cosmic web. Yet it is from this vantage point that we've begun to unravel the deepest mysteries of the universe. Armed with telescopes capable of looking billions of light years away, we become not just spectators, but active participants in this cosmic journey. And each new discovery is a step towards the answer to the eternal question that prompts all of us to ponder, what other mysteries does the universe hold that we have yet to unravel? The solar system has served as a reliable bulwark for life. But one day humanity will have to leave its native Earth to continue existing. In recent decades, scientists have been desperately looking into the dim depths of space in search of a haven for life. So far, none of the exoplanets we've found have refuted the hypothesis of the uniqueness of life. But what if we're simply looking in the wrong place? Perhaps it's not the planets that hold all the answers, but their moons. In the mystical deep space, exomoons are unlike any other satellite in the solar system. The size of our Earth, these hidden giants have an amazing feature. Life can be found in their interior, many times more often than on ordinary exoplanets. Today, we'll dive into the mysterious, distant universe and try to discover why exomoons may someday change humanity. Let's go back to the very beginning of the history of exoplanet science. Since astronomy received a strong impetus only in the middle of the 20th century, scientists began to study the first exoplanets not so long ago. The first confirmed exoplanets were recorded in 1992. It was a group of Earth-mass planets orbiting the pulsar PSR B1257+12. Just 3 years later, scientists found the first planet orbiting the star 51 Pegasi, similar to our Sun. This was the birth of exoplanetary science, which is dedicated to the study of planetary systems outside our solar system, and, in addition, the search for places where human-like life could originate. Other exoplanets available in our visible universe didn't have to wait long either. In the following years, astronomers found several more exoplanets, until in 2009, the Kepler Space Telescope was sent to explore outer space. In just 5 years of operation, it was able to confirm about 715 exoplanets, with a size and conditions similar to Earth's. As of now, we already know about more than 5,500 planets outside the solar system, and the recently sent James Webb Telescope will likely to be able to show us more distant planets. Further, in 2013, scientists were able to determine the planet's color for the first time, and a year later, they were able to record the magnetic field, and later, volcanic activity. Finally, in 2018, astronomers made a new, potentially breakthrough discovery. For the first time, a possible exomoon was recorded near the planet Kepler 1625b. While this may not seem like such an incredible discovery at first glance, exomoons open a new chapter in modern astronomy, not only as novel, hitherto unexplored space objects, but also as potential elements for supporting life on exoplanets and satellites themselves. Every year, knowledge about distant, dim exoplanets deepens, bringing scientists closer to a complete picture of the history of the entire universe. But how did the scientists manage to confirm so many planets in such a short time, when it's impossible to take a photo of each one? Only 69 planets were found with images. The most popular method is the transit method, which you may already know. When an exoplanet passes by its central star, the same star becomes slightly dimmer, which reveals the presence of an object orbiting it. Although this method doesn't allow us to directly observe the planet, and may turn out to be just a glitch, it is currently the most effective of all. Exoplanet exploration plays a crucial role in all of astronomy and the future of all of humanity. Exomoons, as a new chapter in exoplanet science, may have great potential for the search for extraterrestrial life. However, despite this, exosatellites are of not much interest to current research. The main problem associated with the search for these exoplanets is their elusiveness to telescope radar. Although no scientists deny that some exoplanets may have satellites, it's an extremely difficult and, to some extent, even impossible task for our current technologies to investigate them. The transit method, or, more precisely, the method of studying the shift in the spectrum of stars, can confirm an exoplanet. But a satellite orbiting it? Almost under no circumstances, unless, for example, the spacecraft is in the closest possible proximity to the object of observation due to a completely insignificant change in the brightness of the star. Thus, even the very first exomoon found by Kepler and the ones discovered later near the planets Kepler 1708b and Kepler 1513b are still not perceived as full-fledged proof of their existence, and therefore there is a possibility that it could be just some kind of technical error during the observation, which is not so far from the truth, since further observations did not yield any encouraging results. However, as in the case of the giant planet satellite Kepler 1625b, an exomoon can be seen if it is large enough. So far, the first hypothetical exomoon could be the size of the Earth and have a strange tilted orbit like Neptune's moon Triton. Such a huge size of a possible moon may become one of the most important elements in the further search for other moons. Thus, more than 20 exomoon candidates are currently known. All of them are gigantic. Probably at least for Kepler 1625b, it's the star around which it orbits. It is a red giant. This dying star can heat the moon's atmosphere, increasing its effective diameter and allowing scientists to detect satellites more often. However, perhaps right now, exomoons are not of too much scientific importance for scientists to invest a lot of resources in developing technologies to find them. At this stage of our science, exomoons don't seem to be a higher priority than other space objects, such as exoplanets. The satellites of distant planets are too complex to study, and have a very high chance of a false positive result. Therefore, it may take months or even years of observation and analysis to confirm one satellite, when it seems more rational to spend this resource on exploring a planet with potential support for life, including human life. Of course, it is possible that exomoons may hide life in their interior, but alternatives in the form of rocky exoplanets like Earth are still of much higher importance in scientific circles. But we're going to focus on the exomoons themselves and try to investigate them. Is there any need to study these mysterious and hidden moons at all? In fact, these moons contain a lot of information for our complete understanding of the structure of the universe. But this will only be possible in the future, albeit not in the near future. The first thing that draws scientists' attention to even just candidates for exomoons is their size. The largest moon in the solar system, Ganymede, orbiting Jupiter, has a diameter of 3,273 miles, or 5,268 kilometers. But recorded exomoons can reach the size of the Earth, or even Neptune. Therefore, since such moons are even difficult to distinguish among exoplanets, it's incredibly exciting to imagine what moons might look like and what activity they exhibit. It's possible that some large exomoons have many of the features of planets, and that their study could overturn everything we know about satellites. Their similarities to other exoplanets, such as their likely geologic activity, bring us to the next important point for careful study in the future, and that is the support of life. We know that several moons of the solar system, such as Enceladus or Europa, despite their low surface temperatures and small size, could, hypothetically, be a haven for living organisms due to the presence of global oceans. However, what about the much more massive moons, which not only can support a dense atmosphere, but also have more access to building chemicals, both from the inside and outside? According to a study by the University of Washington, exomoons have more potential to support life than even exoplanets. They also have a habitable zone, although it's slightly different. But the main argument for exomoons as one of the most intriguing places for life to exist is the availability of several heat sources for them. The first source is the star itself, and the second is their planet. The moons are heated by the gravitational pull of the planet, which keeps the probable water in the interior of the moon in a liquid state. Moreover, heating from an exoplanet can stimulate geological activity, such as volcanic eruptions, creating enough gas inside the moon to maintain an atmosphere for a long time, and also bringing various crucial chemical elements to the surface. So exomoons are not as simple as they may seem. Perhaps the difficulty of finding them will be rewarded with a potential breakthrough in science. Finally, exomoons may become the necessary tool to study the formation of our universe. Thus, the analysis of exomoons near different stars and planets can reveal to scientists how space objects are formed, what factors are responsible for supporting life, and what the history of other planetary systems is in general. In particular, comparing the moons of the solar system with those of distant systems can give scientists an understanding of the specifics and conditions of their development, as well as an approximate value of the abundance of systems where complex intelligent life has developed. The Earth, hypothetically, may be almost the only planet on which life could have formed, at least in the visible universe. And any clues on exomoons with potentially higher chances of supporting living organisms can confirm or deny this. However, for now, deep exploration of exomoons is only a matter of the future. On the other hand, the James Webb Space Telescope mission will continue for several more years, so perhaps the hope of finding an exomoon for the first time in this decade is not going away. Nevertheless, since the search for exomoons is an extremely difficult and almost impossible task for our current technologies, exomoons are likely to become one of the drivers of technological progress. As we know, the transit method or gravitational lensing will not help to look for microsigns of the presence of exomoons, so this factor is already challenging scientists to modify or even create new technologies to capture such subtle objects. But this is a task for the near future. In the long term, both intriguing moons and exoplanets will require much more thorough analysis, including using images and samples of the atmosphere or even soils. So, if interesting candidates where extraterrestrial life exists are ever found, then comprehensive space missions are likely to follow, advancing human knowledge of the research focus. The only step we have left to take is to find such an exoplanet or exomoon. In 2026, the European Space Agency plans to send the Plato mission, which will continuously look at several areas in outer space to capture transiting objects. The mission will last for 6 years and may be the one to make this expected discovery. However, the benefits of exomoon search and exploration do not end with a technological breakthrough. Exomoons are very valuable natural laboratories located near various planets and stars. Analyzing the impact of these bodies on the moons will not only deepen what's known about the formation of planets, but also demonstrate to scientists the variety of conditions under which life can develop. For example, traces of bio or even techno-signatures created by civilizations on various moons can provide a clearer picture of the signs for the development of intelligent life, thus building more prioritized paths for future missions to the most likely planets or moons for aliens to live on. But for now, we can only wait for the moment when we find the first exomoon and begin a long but life-changing scientific and technological ascent. Exomoons, despite their invisibility and skeptical insignificance, may one day critically change everything known to the entire human race about our vast universe. Even a small observation can eventually become the main driver for revolutionary discoveries. Continued research will reveal more and more answers, and only by pursuing this knowledge will the cumbersome, mysterious cosmos one day become less confusing to us. But in the face of the vast universe, we must never lose our enthusiasm for learning, no matter how difficult and distant our desired outcome. Amidst the peace and tranquility of the celestial bodies of the solar system, there is one object that greatly disturbs the peace of the rest: the moon, Io. Unlike any other orbiting the mighty Jupiter, shrouded in mystery, Io is a world of fire and fury, a stark contrast to the icy moons and calm planets that share its cosmic neighborhood. This mysterious moon, the most volcanic body in our solar system, is a testament to the dynamic forces at work in the cosmos. Its surface, riddled with hundreds of active volcanoes, tells the story of the relentlessly complex gravitational pull of Jupiter and other moons. Meet Juno, NASA's intrepid explorer, on a journey to this fiery world. Its mission is to unravel the mysteries of Io, capture its fiery essence, and uncover the secrets that have long lurked beneath its tumultuous surface. As Juno makes its closest approach in 2 decades, we stand on the threshold of new discoveries and are ready to unravel the mysteries of this volcanic moon. What will Juno tell us about Io's turbulent volcanoes? How does the turbulent nature of this moon affect giant Jupiter and its other moons? And what can Io tell us about the forces that shape our solar system? Let's find out. Discovering new space vistas, Juno, a spacecraft made not only of metal and circuitry but also of ambition and curiosity, is embarking on a journey that hasn't been taken in more than 2 decades. For the first time in 20 years, a spacecraft dares to come so close to Io that we can come face to face with a world of extreme volcanic activity. Juno's close approach is not just a routine flyby, but a bold dive into the unknown. The spacecraft, equipped with state-of-the-art instruments, is designed to withstand the harsh radiation environment of Jupiter and its moons. As it approaches the rough surface of Io at a distance of 930 miles, Juno's sensors come to life, taking high-resolution images and collecting valuable data. In late 2023, the probe made its closest flyby of Io, taking some incredible images in the process. In them, Jupiter's moon appears to glisten with sulfuric hues, and its surface is speckled with spots created by the ongoing volcanic activity that rages on it. By combining data from this flyby with our previous observations, the Juno science team is studying how Io's volcanoes vary, says astronomer Scott Bolton of the Southwest Research Institute. We are looking for how often they erupt, how bright and how hot they are, how the shape of the lava flow changes, and how Io's activity is connected to the flow of charged particles in Jupiter's magnetosphere. The heart of this mission lies in the technological prowess that Juno possesses. The spacecraft's JunoCam continues to take spectacular images, despite the challenges of Jupiter's intense radiation. The Stellar Reference Unit's Stellar Navigation Camera is also a scientific instrument, providing the highest resolution images of Io's surface to date. On Earth, scientists are studying the data coming from Juno. Each byte of data is a piece of the puzzle, revealing new information about the volcanic nature of Io. Analyzing this is a window into our solar system's past, present, and future. So, late last year, NASA's Juno probe took the highest resolution images of this moon to date. Among these images, one that stands out is one taken on December 30th, which vividly depicts the volcanic nature of Io. This image, enhanced to emphasize details, shows a volcanic plume erupting from Io's surface, with plumes reaching more than 60 miles. Given that the moon's diameter is about 2,200 miles. As Juno continues its journey around Jupiter, each orbit brings new opportunities, new challenges, and new discoveries. Among the planet's other 95 moons, Io stands out not only for its proximity to Jupiter, but also for the dramatic geologic activity that this proximity provokes. The volcanic nature of the moon is a direct consequence of Jupiter's enormous gravitational forces. Io is not a huge moon. It's only slightly larger than the one orbiting our planet. However, as the largest planet in our solar system, Jupiter has tremendous gravity. This enormous force stretches and squeezes Io, creating what is known as tidal heating. The satellite's orbit itself is not a perfect circle, resembling more of an ellipse, so the moon experiences varying degrees of gravitational pull from Jupiter. As it approaches Jupiter, the planet's gravity stretches Io, and as it moves away, it compresses it. This constant stretching creates tremendous internal heat within Io, leading to its intense volcanic activity. This JunoCam image captures a plume of material ejected from the unseen volcanic Prometheus. Indicated by the red arrow, the plume is just visible in the darkness below the terminator, the line dividing day and night. The image was taken by spacecraft on October 15, 2023. Tidal heating is so intense that it turns Io's interior into a bubbling cauldron of molten rock. This heat leads to the volcanic activity that defines Io's landscape. Hundreds of volcanoes dot its surface, some of them spewing lava fountains up to hundreds of kilometers high. There are about 400 active volcanoes on Io, about 150 of which are erupting at any given time. But Jupiter is not the only player in this gravitational confrontation. The other Galilean moons, Europa, Ganymede, and Callisto, also exert their influence on Io. Their gravitational attraction helps to maintain Io's elliptical orbit, thus playing a crucial role in the tidal heating process. This complex gravitational interaction is a perfect example of how celestial mechanics determine the fate of a moon. The tidal forces of Jupiter and its moons don't just heat Io, they create a world in which geologic activity is the norm, not the exception. Io, a moon shrouded in fire and brimstone, plays a key role in the grand theater of Jupiter's system. Its incessant volcanic activity not only shapes the landscape, but also significantly affects the very nature of Jupiter's magnetosphere. As we mentioned earlier, the volcanoes on this satellite are the most active in the solar system. In doing so, they spew huge amounts of sulfur dioxide, or SO2, into space. This outgassing, a direct result of intense internal heating, contributes to an atmosphere rich in sulfur compounds. But Io's influence extends far beyond its own atmosphere. As Io rotates within Jupiter's massive magnetosphere, sulfur dioxide and other volcanic gases ionize, becoming charged particles. These particles become trapped in Jupiter's magnetic field, forming a plasma torus along Io's orbit. This torus, a glowing ring of ionized particles, is a direct manifestation of the Moon's volcanic power. The plasma torus is not a static feature. It changes in response to Io's volcanic activity. The ejection of material from volcanoes feeds the torus, affecting its density and composition. This complex interaction between Io's volcanism and the plasma torus illustrates the interconnectedness of Jupiter's system. It's also thought to be responsible for powerful, permanent auroras at the planet's poles. Volcanic emissions, once in the atmosphere, escape into space. Here they undergo rapid reneutralization, a process that ejects these particles at high velocity in a plane perpendicular to the local magnetic field. This phenomenon continues to the formation of extended sodium nebulae, adding another layer to the complex environment around Jupiter. Observational studies have been crucial in shedding light on these interactions. For many years, telescopes, like TRAPPIST, have followed the variability of Io's sodium cloud. These observations have shown that the physical properties of the sodium jets from Io are highly variable, and, interestingly, do not always correlate directly with the global brightening of Jupiter's plasma torus, or the extended sodium nebula. This study highlights the complexity of the surface-atmosphere-magnetosphere coupling in the Jupiter system. Current research aims to reveal the precise mechanisms by which Io's volcanoes supply material to the plasma torus, and how Io's sodium jet contributes to filling the plasma reservoirs of the sphere. Thus, Io's relentless volcanic activity and its interaction with Jupiter's magnetic fields are not just isolated phenomena. They play a fundamental role in shaping the dynamics of Jupiter's magnetosphere, producing plasma structures and neutron clouds that are key to understanding the complexities of planetary magnetospheres. Ongoing research and observations allow us to separate the layers of these interactions, offering a deeper understanding of the workings of our solar system. As we look to the future of space exploration, the fiery moon Io appears as a beacon of mystery and potential. The next phase of Io exploration is poised to reveal secrets that have remained hidden beneath its stormy surface for centuries. Introducing the Jupiter Icy Moons Explorer mission, abbreviated as JUICE. JUICE aims to study Jupiter's icy moons, offering intriguing opportunities to further our understanding of Io. Although JUICE's primary focus is on Ganymede, Europa, and Callisto, its extensive suite of instruments can provide valuable insights into Io's dynamic environment. The interplanetary spacecraft was launched on April 14, 2023, from the Guiana Space Center in French Guiana by the European Space Agency. The spacecraft is expected to reach Jupiter in July 2031 after 4 gravity assists and an 8-year journey. As JUICE passes through the Jupiter system, its trajectory may provide opportunities to observe Io. These encounters may provide additional data on the satellite's volcanic activity and its effect on Jupiter's magnetosphere, complementing the conclusions drawn by missions directly targeting Io. Equipped with sophisticated instruments designed to study magnetic fields, plasma environment, and atmospheric composition, JUICE has the potential to indirectly expand our knowledge of Io. By studying Jupiter's magnetosphere and the interactions within it, JUICE can provide a broader context for the satellite's role in the entire Jupiter system. Another mission, Io Volcano Observer, or IVO, is a bold initiative that represents the next leap in our quest to understand this volcanic moon. IVO is a proposed mission designed to study Io's intense volcanic activity, its subsurface structures, and the complex processes that drive its geologic dynamism. IVO's mission is to enter orbit around Io and make multiple close flybys. Equipped with state-of-the-art instruments, IVO will map Io's volcanic heat flows, study lava composition, and probe the moon's internal structure. This mission aims to answer fundamental questions about the mechanisms of volcanism on Io and the role of tidal heating in its activity. One of the most interesting aspects of the Io mission is exploring the bowels of the moon. What lies beneath its fiery facade? Io seeks to shed light on this mystery by studying the moon's internal structure. Seismic measurements and magnetic field analysis may reveal the presence of subsurface magma chambers and provide insight into the moon's volcanic flow system. The potential for new discoveries about Io's volcanic mechanisms is enormous. Io observations could revolutionize our understanding of volcanic processes, not only on Io, but throughout the solar system. By studying Io's unique volcanism, we'll be able to gain insight into the thermal evolution of planetary bodies and the role of tidal forces in shaping planetary geology. In the meantime, Juno continues to work, with many more observations planned, not only of Io, but also of the other Galilean moons, and, of course, Jupiter itself. The spacecraft will continue to operate until September 2025, or until it breaks down, whichever comes first. In the meantime, we'll look forward to more images taken by the next flyby. In the vastness of our solar system, beyond the belt of asteroids and gas giants, lies a world shrouded in mystery. Neptune, the 8th planet from our sun, a distant ice giant, has long captured our imagination. For decades, we've imagined it as a dark blue sphere at the edge of our cosmic neighborhood. But what if the vision of this distant world was an elaborate illusion? This mysterious planet, named after the Roman god of the sea, has hidden its true colors from us. Cloaked in a shroud of deep blue, Neptune has been the subject of many stories and scientific investigations. But recent discoveries have removed this azure facade, revealing a reality far more complex and fascinating than we could have imagined. For years, our telescopes have been pointed at this distant giant, capturing its essence in pixels and data. What we saw, however, was not the reality of the planet, but a reflection of our own technological and perceptual limitations. The deep blue color we associated with Neptune was actually the result of our own interpretations and enhancements, a story we unwittingly created and believed. Today, we invite you to explore Neptune like never before. Delve into its true colors, understand its dynamic atmosphere, and unravel the secrets of its moons and rings. For centuries, Neptune was portrayed as a dark blue world whose color reflected its cold, distant nature in the solar system. This representation, deeply ingrained in our collective consciousness, has become the cornerstone of our understanding of this icy giant. But what if this image was a reflection of our perceptions, rather than the planet's true appearance? Neptune's color is a story of scientific evolution and the search for truth. It begins with a Voyager 2 probe launched by NASA in 1977. Sent to the outer reaches of the solar system, it took the first close-up images of Neptune, painting a picture of the planet awash in a stunning blue color. However, these images were not a direct window into the true color of Neptune. In fact, they were interpretations, the result of processing the data through the lens of human understanding and the technological capabilities of the time. The deep blue color we saw was the product of enhancements made by scientists to emphasize certain features of the planet. This story began to unravel with the advent of more advanced telescopes, such as the Hubble Space Telescope and the Very Large Telescope. These instruments, equipped with state-of-the-art technology, allowed astronomers to see the true color of the planet again. The results of this study were striking. The new images revealed that Neptune's color was not the previous deep blue, but rather a more muted and varied shade. This discovery was not just aesthetic, but a fundamental shift in our understanding of the planet. The reason for this color misconception lies in the way we process and interpret astronomical data. Colors in space images are often enhanced or altered to emphasize certain features or to make them more distinguishable to the human eye. In the case of Neptune, these enhancements over time have led to a collective opinion of its deep blue color. So, what led to this discovery? The key lies in a meticulous study entitled Modeling the Seasonal Cycle of Uranus's Color and Magnitude and Comparison with Neptune. This study, led by Patrick G.J. Irwin of Oxford University, along with a team of experts, set out to unravel the mysteries of Uranus's seasonal color changes. However, their journey will inadvertently shed light on the true colors of Neptune, disproving long-held beliefs. The team carefully analyzed a huge array of data obtained from Lowell Observatory over 6 decades. These data, supplemented by Hubble Space Telescope observations, produced a detailed picture of Uranus's disk-averaged color and photometric magnitude, revealing the complex interplay of its seasonal changes. One of the most important aspects of this study was the focus on the reflectivity of Uranus and the abundance of methane. The researchers unraveled a complex relationship between the lower methane content at polar latitudes and the different reflectivity of aerosol particles. This complex interaction of elements in the atmosphere of Uranus was thought to be influenced by the presence of methane ice particles, adding a new layer of complexity to our understanding. In parallel, the study allowed for a fascinating comparison with Neptune. Contrary to popular belief, the difference in blue hues between Neptune and Uranus was less pronounced. This discovery was the result of a critical reassessment of Neptune's color, disproving the image of deep blue that had been ingrained in our minds. The methodology used by the team was a combination of quantitative analysis, atmospheric modeling, and advanced spectroscopic observations. They converted measured reflectance spectra into radiance spectra, and then into tri-stimulus values. This process mimicked the visible colors of the planets as perceived by the human eye, bridging the gap between the raw data and our visual interpretation. The use of advanced telescopes such as Hubble and the Very Large Telescope played an important role in this endeavor. These technological marvels allowed the team to revisit and re-examine the true colors of Uranus and, by extension, Neptune, with unprecedented accuracy. As we delve deeper into the mysteries of Neptune, we find ourselves amid a maelstrom of atmospheric activity, in stark contrast to the relative calm of its stellar neighbor Uranus. Neptune's atmosphere, a turbulent and dynamic formation, is home to some of the most extreme weather in our solar system. One of the most striking features of Neptune's atmosphere is the presence of colossal storms, the most famous of which is the Big Dark Spot. Discovered by the Voyager 2 spacecraft in 1989, this massive storm, similar to Jupiter's Great Red Spot, is a testament to the turbulent nature of the planet. A large, dark spot, a giant rotating storm, is a window into Neptune's intense atmospheric dynamics. These storms are caused by the strongest winds in the solar system, reaching speeds of up to 1,300 miles per hour. However, to this day, the power and magnitude of these winds are a mystery to scientists, raising questions about their origin and the energy sources that drive them. In contrast, neighboring Uranus is a picture of tranquility. Its atmosphere, although composed of hydrogen, helium, and methane, does not have the same violent storms and extreme winds as Neptune. The difference in atmospheric activity between these two ice giants is one of the many mysteries of our solar system. Another intriguing aspect of Neptune's atmosphere is the presence of unusual hot spots, where temperatures can reach a staggering 750 degrees Kelvin. These hotspots represent a paradox because they exist on a planet so far from the sun. The source of this heat remains a mystery, but theories suggest it could be caused by internal processes, such as auroras or magnetic reconnection in the plasma layers. The origin of these hotspots and the extreme weather conditions on Neptune are the subject of ongoing research. They force us to seek new answers to questions about planetary atmospheres and hint at complex internal processes that have yet to be understood. Stepping outside Neptune's turbulent atmosphere, we enter a realm of celestial harmony, where moons and rings swirl around this icy giant. Turning our gaze to Triton, Neptune's largest and most intriguing moon, we discover a world of seasonal changes and atmospheric mysteries. Triton, a unique moon with a retrograde orbit, was the last solid object visited by the Voyager 2 spacecraft during its historic journey through the outer solar system. Because of its retrograde orbit, indicating that it was captured by Neptune's gravity, Triton stands out among the moons of our solar system. Its surface, covered in nitrogen ice, is geologically young and active, with dark green streaks indicating the presence of geysers spewing nitrogen gas. Triton's thin atmosphere, whose thickness varies with the seasons, is a fascinating study in extraterrestrial meteorology. Observations with the European Southern Observatory's Very Large Telescope have revealed that Triton's southern hemisphere is in the height of summer. This distant moon, despite its relative distance from the sun, is experiencing significant atmospheric changes. The heat of the summer sun causes the thin layer of frozen nitrogen, methane, and carbon monoxide on Triton's surface to sublimate into gas. This process causes the icy atmosphere to thicken as the season continues in Neptune's 165 Earth-year orbit around the sun. The season on Triton lasted more than 40 years, and the southern summer solstice occurred in 2000. The discovery of carbon monoxide in Triton's atmosphere, as well as the confirmation of the presence of methane, marked a significant advance in our understanding of this moon. The presence of these gases, especially the enrichment of ice with carbon monoxide in the upper surface layer, feeds the atmosphere and determines its seasonal dynamics. These findings required a revision of Triton's climate and atmospheric models. The complex interaction of nitrogen, methane, and carbon monoxide not only determines atmospheric conditions, but also provides insight into the geologic and climatic history of the moon. But Triton is not alone. The planet is accompanied by a retinue of smaller moons, each contributing to our understanding of this distant world. These moons also show seasonal changes and provide insight into the complex gravitational interactions and environmental conditions around Neptune. When we turn our gaze from the moons to Neptune's rings, we encounter another aspect of this planet's mysterious nature. Neptune's rings, made up of a mixture of dust and ice particles, are dull, yet mesmerizing. They testify to the planet's dynamic history. Scientists believe they're remnants of moons that were destroyed by collisions or torn apart by Neptune's gravity. The composition and characteristics of these rings are closely related to Neptune's true color and atmospheric phenomena. The subtle hue of the rings, which are affected by light scattering in Neptune's atmosphere, add another layer to the planet's color palette. The rings, reflecting and refracting light from the sun, create the overall appearance of Neptune seen from afar. In 2022, the James Webb Telescope captured the clearest view of the rings of this distant planet in 30 years. Photographed with unprecedented clarity, these rings have changed the way we think about this distant planet. The most striking thing about the new Webb image is the clear view of Neptune's rings. Some of these rings, dim and dusty, have not been detected since the historic Voyager 2 flyby in 1989. The Webb telescope, with its enhanced capabilities, has brought these elusive rings back into focus. Neptune's rings are made up of several bright and narrow, as well as fainter dust bands. Infrared imaging by the Webb telescope has put these rings in a new light, revealing features that were previously hidden in the darkness of space. This is the first time these rings have been seen in the infrared spectrum, providing new insights into their composition and behavior. Neptune's rings, like the planet itself, are characterized by a unique composition. Unlike the gas giants Jupiter and Saturn, Neptune is an ice giant, rich in elements heavier than hydrogen and helium. This composition also reflected in the planet's signature blue color in visible wavelengths caused by a small amount of methane gas. In infrared images taken by Webb's NIRCam, near-infrared camera, Neptune does not appear blue, in contrast to the darkened appearance one would expect due to methane absorption of light. In infrared images taken by the Space Telescope, Neptune appears as a luminous, glowing white sphere. This absorption also affects the appearance of Neptune's rings, as they reflect and refract light traveling through the planet's atmosphere. This unexpected brightness in the infrared is the result of a unique interaction between the planet's atmosphere and infrared light. While methane gas absorbs red and infrared light, high-altitude clouds in Neptune's atmosphere reflect sunlight before it's absorbed. These methane ice clouds appear as bright streaks and spots that cast a ghostly glow on the planet in the infrared spectrum. By the way, you may wonder why Triton looks like a dazzling point of light adorned with shining spikes, as opposed to the more subdued image of Neptune. These diffraction spike patterns are a characteristic feature of the imaging telescope. They're not physical structures, but rather optical artifacts created by the telescope's design. Light from Triton passing through the mirrors and telescope structure is diffracted, resulting in these striking peaks emitted by the moon. Diffraction, in simple terms, is what happens when a wave, such as light, travels around the edge of an object or through a small opening. Imagine light in the form of water waves flowing through a narrow slit in a wall. When the waves pass through the slit, they diverge in different directions, instead of just going straight through. This propagation of waves after passing through a hole or around an edge is what we call diffraction. In the context of the James Webb Space Telescope and its images, diffraction peaks arise because of the way the mirrors and structure of the telescope are arranged. When light from a bright object, such as a star or Triton in images of Neptune, enters the telescope, it's bent slightly by the edges of the mirrors and other parts of the telescope. As a result of this bending, the light diverges and forms the star-like spikes we see in the images. The study of Neptune's rings, especially in the infrared, provides valuable insights into the atmospheric conditions and internal composition of the planet. The interaction of the rings with Neptune's atmosphere, particularly the methane ice clouds, provides insights into the planet's climatic and environmental processes. The bright equatorial band that girdles the planet hints at the global atmospheric circulation, a key driver of the planet's winds and storms. The atmosphere, which sinks and warms near the equator, glows more intensely in the infrared than the cooler gases that surround it. As we conclude our journey through the mysterious world of Neptune, we reflect on the impact these discoveries are having on the broader field of planetary science and exoplanet exploration. Neptune, once a distant blue spot, is now a testament to space exploration's dynamic and ever-evolving nature. Discoveries concerning Neptune's true color, its atmospheric phenomena, and the intricate details of its rings and moons go far beyond our solar system. They provide a crucial example for understanding similar ice giants and exoplanets in the far reaches of our galaxy. The insights gained from Neptune will help astronomers decipher the mysteries of these distant worlds and enrich our knowledge of the universe. As we continue to gaze into the cosmos, Neptune reminds us of the limitless potential for discovery. Its example encourages us to keep looking, asking questions, and unraveling the mysteries of the universe. Saturn has captivated the human imagination, from ancient civilizations to modern astronomers. The Maori of New Zealand, separated by vast oceans and without telescopes, somehow knew that Saturn had rings. How? The mystery deepens. Saturn has long been a symbol of the unknown and mysterious. Its iconic rings have been the subject of wonder and speculation since the time of Galileo. But what if we told you that these rings, however eternal they may seem, are actually a fleeting cosmic phenomenon? Adding to the intrigue is a storm twice the width of Earth, with a mysterious hexagonal shape that's raging at Saturn's North Pole. What forces could have created such a geometrically perfect formation? But the mysteries don't end there. Saturn's satellites, Titan and Enceladus, offer conditions that could potentially support life. Lakes of liquid methane and geysers spewing water and organic material into space make these satellites more than just celestial bodies. They're potential homes for life. Join us for a closer look at this enigmatic giant and its cosmic mysteries. Our journey begins with Galileo Galilei, the Italian astronomer who first pointed his telescope at Saturn in 1610. What he saw puzzled him, a planet with something like ears. He didn't realize he was looking at the edges of Saturn's magnificent rings, a feature that would puzzle astronomers for centuries to come. Galileo's telescope was primitive by today's standards, and the true nature of Saturn's ears remained a mystery. It was not until 1655 that Christian Huygens, armed with a more advanced telescope, correctly identified them as a system of rings surrounding the planet. Moving into the modern era, we witnessed the Pioneer 11 mission, the first spacecraft to fly past Saturn in 1979. This mission provided us with the first close-up images of the planet and its rings, revealing intricate details that were once inaccessible to Earth's telescopes and us. But it was the Cassini mission that truly revealed Saturn in all its glory. Launched in 1997 and arriving at Saturn in 2004, Cassini spent 13 years studying the planet, its rings, and its satellites. From discovering plumes of water ice on Enceladus to capturing the ethereal beauty of a hexagonal-shaped storm at Saturn's North Pole, Cassini revolutionized our understanding of this distant world. And here's an interesting point. Long before the advent of telescopes, the Maori people of New Zealand had myths that described Saturn as having a parero, or belt, around it. How they knew this remains a matter of debate and speculation. But as we'll see later, Saturn holds more than one mystery. What do you think could have created a hexagonal storm with an area larger than the Earth itself? Saturn harbors a geometric enigma at its North Pole, a six-sided storm that's puzzled scientists for decades. This six-sided wonder is not just a superficial feature, but a deep and enduring mystery that breaks down the understanding of fluid dynamics and planetary atmospheres. The hexagon was first discovered in 1981 by the Voyager spacecraft. But it wasn't until the Cassini mission, which orbited Saturn from 2004 to 2017, that we got a front-row seat to this cosmic spectacle. Cassini's high-resolution images showed a symmetrical jet stream surrounding the hurricane-like vortex at the center of the hexagon. Unlike Earth's chaotic weather systems, Saturn's hexagon is a masterpiece of geometric precision. So what's causing this hexagonal storm? Researchers at Harvard University have developed a 3D model that suggests deep thermal convection in Saturn's outer layers may be the culprit. This model shows that the storm could spread thousands of kilometers deep into Saturn's atmosphere, well beyond what we can see. Interestingly, scientists have been able to reproduce the hexagonal pattern in a laboratory setting. Although these experiments do not capture all the nuances of Saturn's complex atmosphere, they provide a glimpse of extraterrestrial phenomena. Saturn's hexagonal vortex contrasts sharply with Earth's polar vortex, which is irregular and less stable. This difference raises questions about the fundamental properties that distinguish the atmospheres of the gas giants from the Earth group planets. The longevity of the hexagon is another mystery. It's been observed for at least 4 decades, and possibly much longer. This steady feature suggests that everything that feeds the hexagon is not a temporary phenomenon, but a stable, perhaps even permanent, aspect of Saturn's internal dynamics. Let's shift our attention from the mystery of the hexagon to another wonder of Saturn. Saturn's rings are more than just celestial jewelry. They're dynamic, ever-changing systems that interest astronomers and the public alike. But what are these rings made of, and why are they so short-lived? Saturn's rings are composed mostly of water ice with a mixture of dust and rocky material. They range in size from tiny particles to huge chunks the size of houses. These ice particles are not static. They're in constant motion under the influence of Saturn's gravity and the gravitational pull of its satellites. The rings are divided into several subdivisions and gaps, each with its own unique characteristics. Most notable are the A, B, and C rings, separated by gaps, such as the Cassini ring, a gap 3,000 miles between the A and B rings. The origin of Saturn's rings has been the subject of debate. One popular theory suggests that they formed from the remnants of a shattered moon. Another theory states that they're the remnants of material from the formation of the solar system, captured by Saturn's gravitational pull. Recent research has also shown that the rings may be much younger than Saturn itself, perhaps around 400 million years old, based on the rate of dust contamination. Saturn's rings don't last forever. They're slowly disappearing because of a phenomenon known as ring rain, in which ring particles are drawn into Saturn's atmosphere. This process is accelerated by micrometeoroid bombardment and interaction with Saturn's magnetic field. At the current rate, some scientists predict that Saturn's rings could disappear within 100 million years. The depletion of the rings would not only change Saturn's appearance, but could also have consequences for its atmosphere and magnetic field. As we pause for a moment, we realize that even the most fascinating features of our universe are not immune to the inexorable forces of physics, doomed to disappear into the chronicle of eternity. Saturn, the ringed giant of our solar system, is not just a celestial wonder. It's also a cosmic playground that contains some of the most intriguing satellites, 2 of which, Titan and Enceladus, have fascinated scientists and sparked debate about the potential for life beyond Earth. Titan, Saturn's largest satellite, is a world shrouded in mystery. Its dense atmosphere is rich in organic compounds, and there are lakes and rivers of liquid methane on the surface. But what's truly amazing is Titan's rate of removal from Saturn, 100 times faster than previously thought, amounting to a staggering 4.3 inches per year. This rapid drift suggests a dynamic and evolving relationship between Titan and Saturn. Could this drift affect Titan's internal dynamics? And perhaps even its potential for the existence of life. An atmosphere rich in organic compounds such as nitrogen and methane, and the possibility of an underground ocean, make Titan a tempting target for the search for extraterrestrial life. But the question remains, what would life look like in an environment so radically different from Earth's? And let's remember Enceladus, another satellite of Saturn that's very different from Titan. It's an icy world, with a highly reflective surface that outshines any other body in the solar system. Enceladus takes the concept of an ocean world to a new level. Not only does it have a subsurface ocean, but it also sprays it into space, where samples of it can be collected by a space probe. This ocean contains most of the chemical ingredients necessary for life, including hot, mineral-rich water erupting from hydrothermal vents. Hydrothermal vents can provide the necessary conditions for life as we know it. On Earth, these vents are teeming with life forms that thrive in extreme conditions. Could Enceladus's vents be home to similar but alien life forms? Enceladus also contributes to Saturn's E-ring, a unique characteristic that further enriches the dynamic relationship between the Moon and its host planet. The icy particles in this ring open a window into the Moon's internal chemistry, providing clues that may reveal its secrets. Titan and Enceladus are two moons orbiting the same planet, but quite different in their characteristics. Both present compelling arguments in favor of the potential for life, fueling our curiosity. As we ponder the possibilities of life on Saturn's satellites, it's worth noting that our curiosity is not limited to telescopes and computer modeling. Upcoming missions aim to study these satellites up close and perhaps answer some of our most pressing questions. Meet Dragonfly, NASA's ambitious mission to Titan. Scheduled for launch in the 2030s, this rotorcraft will fly over Titan's diverse terrain, from dunes to impact craters. Dragonfly's main goal is to search for the building blocks of life. It will analyze complex organic compounds in the atmosphere and on the surface, providing invaluable data on Titan's chemistry. Equipped with a suite of scientific instruments, Dragonfly seeks to understand the geologic processes on the Moon and how they relate to its potential for life. Could Titan's unique chemical composition and liquid methane cycles offer a different recipe for life? Although no missions to Enceladus are currently planned, the Moon's potential for life has made it a prime candidate for future exploration. Scientists are proposing missions that could fly through Enceladus's plumes and directly sample its underground ocean. Such a mission could analyze the chemistry of the plumes in search of signs of life or prebiotic chemistry. The presence of hydrothermal vents in Enceladus's oceans adds another layer of intrigue, suggesting an environment in which life could potentially thrive. Despite the technical challenges, a mission to Enceladus could revolutionize our understanding of the potential for life in the solar system. It could provide direct evidence for the existence of extraterrestrial life, or at least provide clues to the conditions necessary for life to exist. As we mentioned, Saturn's rings don't last forever, as we once thought. Recent studies have shown that a process that can last hundreds of millions of years is causing these icy wonders to slowly fade away. But what significance does this have for Saturn and its complex atmospheric dynamics? According to a study by the Japan Aerospace Exploration Agency, this material, composed mostly of water, causes a decrease in electron density in Saturn's atmosphere. This phenomenon, known as ring rain, significantly affects Saturn's atmospheric conditions. Ring rain is not just a trickle. It's a stream that carries away water in amounts equivalent to an Olympic-sized swimming pool every half hour. Compounding the mystery is the relative youth of Saturn's rings. Although Saturn itself is about 4.6 billion years old, data from NASA's Cassini mission suggests that the rings may be only a few 100 million years old. This leads us to wonder, if Saturn's rings are so young, what catastrophic event could have led to their formation? Was it the destruction of a moon? Or perhaps the capture of a passing comet? Cassini's Space Dust Analyzer has added another layer of complexity. Over 13 years, it's collected 163 dust particles that came from outside the Saturn system. Surprisingly, the rings turned out to be quite clean, suggesting that they hadn't existed long enough to accumulate excess cosmic dust. This cleanliness raises the question, if the rings are young, why haven't they collected more cosmic dust? The absence of cosmic dust in the rings challenges our understanding of their age and their interaction with the wider cosmic environment. It's as if the rings are in a cosmic laboratory room or clean room, isolated from the dust that permeates the rest of the solar system. As the rings are depleted, Saturn's appearance will undergo a dramatic transformation. These rings have been the planet's hallmark. Their disappearance would not only change Saturn's appearance, but could also have unknown consequences for its atmosphere, perhaps even affecting the planet's albedo and heat retention. The loss of the rings could have a cascading effect on Saturn's atmosphere, potentially altering wind patterns, and even affecting the planet's iconic storms. The full extent of these changes is still unknown, making them a subject of intense scientific interest. Interestingly, the fate of Saturn's rings may be inextricably linked to its satellites. Some theories suggest that gravitational instability may have destroyed some of the icy satellites orbiting Saturn, providing enough material to form the rings. Saturn's rings and satellites are like partners in a cosmic dance, each affecting the other in subtle but significant ways. As we continue to study these celestial bodies, we can say unequivocally that the fate of one can shed light on the mysteries of the other. In the vast theater of our solar system, where planets like Jupiter and Saturn often attract attention with their majestic rings and violent storms, lies a distant world shrouded in mystery and intrigue. This is Uranus, an enigmatic ice giant that often goes unnoticed, but holds secrets that may unravel some of the most enduring mysteries of the cosmos. Far beyond the asteroid belt, nestled between the orbits of Saturn and Neptune, Uranus travels through the cold and dark corners of our solar system. It's a world that lives at a different rhythm, spinning on its side, an oddity that's long puzzled astronomers and spawned countless theories. Discovered in 1781 by William Herschel, Uranus was the first planet discovered through a telescope, extending the known boundaries of our solar system. For centuries, this distant world was just a speck of light in our telescopes, a ghostly blue ball, distant and aloof, keeping its secrets. But now, with the advent of the James Webb Space Telescope, a new chapter in the exploration of Uranus is opening. JWST, with its unprecedented vision, peels back the layers of this icy giant, revealing a world of amazing beauty and complexity. Let's travel together to this mysterious ice giant and learn about the latest discoveries made by the James Webb Space Telescope. In the quest to understand the universe, humankind has launched a sentinel into space, a marvel of engineering and a testament to our insatiable curiosity. This sentinel is the James Webb Space Telescope, the most advanced and powerful space telescope ever built, the successor to the legendary Hubble Space Telescope. Equipped with a set of advanced instruments and a mirror more than 6.5 meters in diameter, JWST is designed to observe the universe in light invisible to the human eye, the infrared spectrum. This allows the telescope to peer through clouds of cosmic dust, discover distant galaxies, and study the atmospheres of exoplanets. The telescope's journey into space was a feat in itself. Launched on an Ariane 5 rocket, JWST traveled to a point in space known as the Second Lagrange Point, or L2, 1,000,000 miles from Earth. Here, in this stable orbit, JWST can observe the universe with minimal interference from Earth and the Sun. JWST's capabilities are not limited to observing the early universe or distant galaxies. It plays a key role in unlocking the mysteries of our solar system. Its powerful instruments, such as the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI, reveal new details about planets, moons, and other celestial bodies closer to home. Take Uranus, for example. In the past, our view of this distant planet was limited to faint images from telescopes such as Hubble. But now, thanks to JWST's enhanced infrared capabilities, we can see Uranus in a new light. The telescope's sensitive instruments allow us to observe the planet's atmosphere, weather patterns, and even its mysterious rings with unprecedented clarity. By analyzing the light of Uranus, JWST can decipher the chemical composition of its atmosphere, revealing the presence of gases such as methane and hydrogen. This not only helps us understand the current state of Uranus, but also provides clues about its formation and evolution. The James Webb Space Telescope continues to exceed expectations, revealing more details about our universe every day. Its latest triumph is a series of images of Uranus taken very recently, surpassing even the stunning observations made in April 2023. In early 2023, JWST provided us with unprecedented views of Uranus, allowing us to look at the planet's atmospheric dynamics and ring system in a new light. The recent images, however, are a step further. Not only are they clear, they reveal aspects of Uranus that were previously hidden or obscured, even in April observations. Take the rings of Uranus, for example. The latest images show them with even greater clarity. We can now observe finer structures within the rings and even detect faint dust bands that were previously invisible, such as the Zeta ring, the incredibly thin ring closest to the planet. The strength of JWST lies not only in its one-off observations, but also in its ability to continuously track celestial objects. Continuous observations of Uranus have allowed us to observe changes in the planet's atmosphere, track the movement of its clouds, and observe the evolution of its storms over time. The changes in the polar regions are particularly striking. Bright white caps and dark bands near the poles, the origin of which is still unclear, have shown marked changes. This continuous observation provides invaluable data for understanding the seasonal changes and long-term climate patterns of Uranus. In the set of planets in our solar system, Uranus stands out with a peculiar feature, an extraordinary axial tilt. Unlike any other planet, Uranus rotates practically on its side, tilted at an angle of about 98 degrees. This unique orientation has long intrigued astronomers and sparked a quest to understand its origin and consequences. To understand the significance of this tilt, we must travel back in time to the early days of our solar system. Uranus probably formed with a much less severe tilt. The prevailing theory suggests that a catastrophic event, perhaps a collision with a planet-sized object, dramatically changed its orientation. This colossal impact would have thrown Uranus aside, changing the definition of its axis of rotation. Such a dramatic event in the planet's history probably not only changed its rotation, but also left an indelible mark on its entire system, including its satellites and rings. Today, this lateral rotation is a unique spectacle. Each pole of Uranus is alternately flooded with sunlight and plunged into darkness at intervals of 42 years. This extreme tilt results in extreme seasons, unlike those observed on other planets. The implications for planetary observations and research are enormous. Uranus's tilt allows us to observe its rings and satellites from different perspectives, offering insights into their composition and dynamics. For example, when Uranus's rings face the Earth, they become nearly invisible, exposing fainter dust bands and smaller satellites. Compare that to Earth, which is tilted only 23.5 degrees. Uranus's extreme tilt causes drastic changes in its weather patterns, which is a goldmine for scientists studying planetary climate. Tilt also affects the circulation of Uranus's atmosphere. Prolonged exposure to sunlight at the poles can result in complex weather systems. as seen in recent JWST images. These systems are very different from those on other planets and provide a unique laboratory for understanding atmospheric physics. Let's take a journey on one Uranian year. Each season on Uranus lasts about 21 Earth years, a consequence of its 84-year orbit around the Sun. This extended duration means that each hemisphere experiences long periods of daylight, followed by equally long nights. As a result, the planet undergoes dramatic changes in appearance and climate. Because one pole of Uranus basks in uninterrupted sunlight, summers are long, while the opposite pole plunges into a deep, dark winter. This stark contrast creates unique atmospheric conditions, causing complex weather patterns and climatic shifts. The impact of these seasonal changes on Uranus's atmosphere is profound. When the sun illuminates the planet's surface, it warms the atmosphere, creating colossal storms and dynamic cloud systems. These atmospheric phenomena are not static. They evolve and change with the seasons, painting an ever-changing portrait of the planet. Among the most striking features are the bright cloud tops that appear when the sun illuminates the planet's atmosphere. These clouds, composed of frozen methane and other gases, reflect sunlight, creating a dazzling spectacle. Conversely, dark storm patches that look like giant hurricanes roam the planet's surface. Moreover, the planet's seasonal phenomena affect not only the planet itself, but also its moons. One recent study of Uranus's moons, or rather a phenomenon that's particularly intriguing, is the development of temporary atmospheres on these moons, a spectacle caused by the unique conditions of the Uranus system. The key to understanding these temporary atmospheres lies in the extreme tilt of Uranus's axis and its effect on the satellite's orbits. As these satellites orbit the planet, they experience dramatic changes in solar exposure, alternating between long periods of intense sunlight and prolonged darkness. During a long summer exposed to sunlight, the icy surfaces of these satellites undergo a process known as sublimation. The ice, composed mainly of water, methane, and carbon dioxide, transforms directly from solid to a gas, bypassing the liquid phase. This sublimation creates thin, temporary atmospheres, or exospheres, that envelop the satellites. These exospheres are most pronounced when moons are warmest. Recent research by the James Webb Space Telescope shows that this phenomena is more dynamic and complex than previously thought. Exospheres are heterogeneous. They vary in composition and density, depending on the topography of the moons and the intensity of solar radiation. As the satellites enter their winter phase, the exospheres gradually dissipate. Gases recondense on the surface, returning to an icy state. This cycle of atmosphere creation and disappearance is a unique characteristic of Uranus's satellites, opening a window into the interaction between solar radiation and surface ice. The rings of Uranus, often overshadowed by the majestic rings of Saturn, hold their own tale of cosmic intrigue and dynamism. A recent comparative study of the rings of Uranus, Saturn, and Jupiter sheds new light on these lesser-known, but no less fascinating, celestial features. In contrast to the wide and bright rings of Saturn, the rings of Uranus are narrow, dim, and less extensive, extending to 4 planetary radii. This includes elusive rings, such as the Mu and Nu rings. The study delves into the gravitational influence of Uranus's main satellites on these rings, a key factor in their formation and evolution. The significant influence of Uranus's 5 major satellites, Miranda, Ariel, Umbriel, Titania, and Oberon, plays a central role in the history of the rings. These satellites, much more massive than their smaller counterparts, dominate the gravitational dynamics within the Uranus system. Their positions and masses relative to Uranus provide a better understanding of the formation of the satellites and the gravitational formation of the rings. The formation of Uranus's rings is attributed to a combination of processes, including collisions, satellite breakup, and gas release from the main satellites. These dynamical processes affect the material composition of the rings and are influenced by the ever-changing environment of the Uranus system. The stability of the rings is intrinsically linked to their dynamical interactions with the satellites of Uranus. The study examines how accretionary processes occur within the Roche limit and how the dynamics of shepherding moons play a crucial role in maintaining the rings. In addition, the rings provide a unique opportunity to understand the internal structure of Uranus through seismological studies. Modeling results show how these satellites shape the ring system, affecting its structure and stability over time. The modeling predicts significant material loss within the ring system, primarily due to gravitational interaction with the satellites. The complex dance between moons and rings is a key aspect of the Uranus system. The dynamic exclusion zones created by the satellites and the influence of these zones on the material distribution of the rings are crucial to understanding the structure and the evolution of the rings. The study also examines the role of satellite-to-satellite interactions in the evolution of the system, especially past resonances between satellites such as Ariel and Umbriel, and their impact on the orbits and geology of satellites, especially Miranda. But the mysteries surrounding this planet don't end there. You've probably heard of the aurora borealis. Well, the latest discovery concerns the auroras of Uranus, which also has them. However, its auroras, unlike Earth's, occur in the infrared spectrum. Using the Keck-2 telescope, astronomers observed enhanced emissions of trihydrogen cation in the planet's atmosphere. This is a groundbreaking discovery that sheds light on the unique magnetic field and dynamics of Uranus's atmosphere. Uranus's magnetic field, which is significantly deflected from the planet's axis of rotation, creates a unique coupling of the magnetosphere, ionosphere, and thermosphere. The detection of these infrared auroras is crucial because it opens up a new window into these processes, previously elusive due to the lack of such detections on Uranus. Comparing the polar auroras of Uranus with those of Jupiter and Saturn reveals their different characteristics. Unlike Jupiter, where the H3+ emissions have short lifetimes that smooth out the variability of the UV emission, the brightest infrared emissions of Uranus do not necessarily coincide with the brightest UV emissions of the other planets. This unique aspect of Uranus's polar lights provides valuable information for exoplanet studies, especially for the worlds of warm ice giants. The study delves deeper into the unusual heat spots on Uranus, observed near the latitudes of the UV northern lights. These spots, analyzed for temperature, column density, and total emission, suggest that the enhancement is not caused by temperature, but rather by increased ionization, probably due to polar aurora activity. Polar lights play a significant role in heating the atmosphere, and on Uranus, the increased H3+ emissions associated with these auroras suggest their involvement in atmospheric processes. By studying such unique things, we gain a deeper understanding of similar processes in different planetary environments, enriching our knowledge of how auroras shape planetary atmospheres, affecting not only thermal properties, but also the overall dynamics of the ionosphere and magnetosphere. In the quest to unravel the mysteries of our solar system, the ice giants Uranus and Neptune are distant enigmas beckoning closer exploration. Recent research, including a fresh analysis of Voyager images, has revealed that the two planets actually have similar shades of greenish-blue color, fundamentally changing our long-held beliefs. Uranus and Neptune share many common characteristics. They're roughly the same size, have the same mass, and are surrounded by deep atmospheres of comparable materials. Nevertheless, it was long thought that their appearance was quite different. This misconception has now been corrected. Both planets are shown in their true colors, largely influenced by the methane layer in their atmospheres. The need for a dedicated mission to Uranus has never been greater. Such a mission would not only deepen our understanding of the planet itself, but also provide a comparative view of Neptune and other similar icy giants. The mission's potential goals range from studying the unique magnetic field and complex ring system to investigating atmospheric dynamics and internal structure. In an important achievement for planetary exploration, the Uranus Orbiter and Probe mission has been elevated to the highest priority for NASA flagship mission within the 2023-2032 Planetary Science Decadal Survey. Future launch windows are available between 2030 and 2034. Key science goals will include a detailed analysis of the unusual tilt of Uranus's axis and its effect on the planet's climate and weather patterns. The mission can also study the intriguing phenomena of infrared auroras and their role in heating the atmosphere, providing a comparative study with other planets. Studying Uranus and Neptune will also provide valuable information about planetary evolution and dynamics. Understanding why Uranus appears slightly whiter, perhaps due to its more stagnant atmosphere, allowing methane haze to accumulate, can tell us a lot about atmospheric processes on the ice giants. As we await a future mission to Uranus, we stand on the threshold of discoveries that could redefine our understanding of the outer solar system. Exploring this distant ice giant will not only unravel its mysteries, but will also expand our knowledge of planetology as a whole, shedding light on the complex picture of our cosmic home. There's an interesting mystery in our world, generated by the equations of Einstein's general theory of relativity. It's the theoretical analog of the black hole familiar to many. We call it a white hole. Imagine a region of space where, unlike an all-consuming black hole, nothing can penetrate. Instead, this cosmic anomaly defies our expectations by ejecting matter and energy, glowing violently on the dark canvas of space. In a universe governed by the concept of an arrow of time, where events flow from past to future, a white hole is a tantalizing paradox. It's like watching a space movie in reverse, where the rules of gravity and time seem to be rewritten. But are these celestial wonders just mathematical curiosities? Or do they hold the key to understanding the deeper truths of our universe? Let us delve into the mysteries of white holes, exploring their theoretical underpinnings, their enigmatic characteristics, and their potential role in the great history of the universe. In the early 20th century, Albert Einstein revolutionized our understanding of the universe by creating the general theory of relativity. This groundbreaking theory proposed a radical idea. Gravity is not a force pulling objects together, but rather a curvature of space-time caused by mass and energy. Imagine space-time as a fabric stretched like a cosmic trampoline. When an object of mass, such as a star or planet, lands on this fabric, it causes a dip. This curvature directs the motion of other objects, which move along curved trajectories in space-time. This is gravity, as Einstein envisioned it. Einstein's theory led to the prediction of black holes, regions in space where the gravitational pull is so strong that nothing, not even light, can escape. These cosmic giants form when massive stars collapse under their gravity, distorting space-time to the extreme. Introducing Carl Schwarzschild, a brilliant physicist who, while fighting in World War I, found an interesting solution to Einstein's equations. Schwarzschild's solution described space-time around a spherical, non-rotating mass, such as a star. Schwarzschild's work laid the foundation for understanding black holes, but it also hinted at something even more mysterious. If a black hole is a region from which nothing can escape, could its polar opposite exist? A region where nothing can enter, but only leave. This led to the birth of the concept of a white hole. Just as a black hole is the end point of gravitational collapse, a white hole can be thought of as a reverse black hole, a cosmic fountain ejecting matter and energy. However, unlike black holes, which have already been observed, white holes remain a theoretical concept, a tantalizing possibility in the vast cosmic mystery. In the field of astrophysics, the path from mathematical abstraction to physical reality is often long and difficult, and white holes are no exception. These theoretical entities arise from the complex equations of the general theory of relativity, the same mathematical structure that predicts the existence of black holes. The math of white holes is robust, but it's like a jigsaw puzzle with missing pieces. We understand their theoretical basis, but the real challenge is to relate these mathematical models to observable phenomena. Imagine a universe in which, instead of collapsing inward, a region of space-time does the opposite. It explosively ejects matter and energy. This is the essence of a white hole, a mirror image of a black hole, in which the flow of time and matter is reversed. But can these mathematical abstractions exist in our physical reality? The debate among scientists is ongoing and multifaceted. Some theorists suggest that white holes may be remnants of the early universe, exotic structures woven into the fabric of space-time itself. Others suggest they may represent the other end of a black hole, a kind of cosmic exit door from which matter and energy reappear after being swallowed up by the black hole. The novel idea of quantum gravity suggests that as a black hole evaporates over many epochs, losing mass, it may reach a point at which it can no longer sustain itself as a black hole. At that point, it may turn into a white hole, releasing the trapped contents back into the universe. However, there are serious problems with the physical existence of white holes. The laws of thermodynamics, especially the concept of entropy, presents a serious obstacle. Entropy, a measure of disorder, tends to increase in the universe. White holes, by their nature, decrease entropy, which contradicts this fundamental principle. Moreover, the stability of white holes is a controversial issue. Some theories suggest that if they did form, they'd be extremely unstable and would probably collapse almost instantaneously into black holes. In outer space, white holes represent one of the most enigmatic and paradoxical concepts. These mirror images of black holes have characteristics that challenge our traditional understanding of physics. Let us understand in more detail what is the concept of a white hole in theoretical physics. At the heart of a white hole is its event horizon, a boundary not of inescapability, as it is with black holes, but of impenetrability. This event horizon marks the point where matter and energy are ejected, creating a spectacle of cosmic proportions. Unlike a black hole, which takes over everything, a white hole is the source of the expulsion, the cosmic fountain from which matter and energy arise. One of the most intriguing aspects of white holes is the concept of time reversal. In the universe, time usually flows in one direction, from the past to the future. However, white holes seem to reverse this flow. It's like watching a space movie played backwards, where the usual rules of time and space are reversed. Deepening into the nature of white holes, we find a realm of paradoxes and problems. One of the most important is their connection with the previously mentioned entropy. According to the second principle of thermodynamics, entropy, or the measure of disorder, should always increase in a closed system. However, white holes seem to ignore this law, decreasing entropy and ejecting matter in an ordered state. This apparent violation of thermodynamic laws presents a serious problem for our understanding of physical processes in the universe. How can such an object as a white hole exist if it contradicts such a fundamental principle? Another paradox lies in the concept of the arrow of time. While the universe moves inexorably forward in time, white holes suggest a scenario in which time can flow backward, at least from a certain point of view. This concept breaks not only our understanding of time, but also the very nature of causality in the universe. Let us summarize the characteristics of white holes, their event horizons, the expulsion of matter, and the concept of time reversal present a fascinating but paradoxical picture for theories that, while we're looking to solve these problems, white holes remain in the realm of theoretical physics. As we delve deeper into the mysteries of the cosmos, the concept of white holes invites us to rethink our understanding of the universe. These theoretical objects are not just surprising anomalies. They may have profound cosmological implications. Consider the Big Bang, the colossal explosion that marked the beginning of our universe. Some theorists suggest that this pivotal moment in cosmic history was not just a random explosion, but that the event may have been a white hole of unimaginable magnitude, an eruption of matter and energy that gave birth to the cosmos. This view offers a radical new interpretation of the origin of our universe, suggesting that white holes may play a role in cosmic genesis. Imagine a white hole not just as a theoretical construct, but as the very source of the creation of our universe. In this scenario, the Big Bang could be envisioned as a white hole of unfathomable scale, spewing out matter, energy, and space-time that subsequently evolved into the stars, galaxies, and planets we observe today. This view offers a radical rethinking of the Big Bang. Instead of an undefined singularity, we have a white hole, an entity defined by the laws of physics, albeit in a form that stretches our understanding to its limits. This white hole may have been the first spark that set the stage for subsequent cosmic evolution. If the Big Bang was indeed a white hole, it raises profound questions about the nature of our universe. What was the source of this white hole? Was it the result of a collapse of the universe from another dimension, or the result of processes beyond our current scientific understanding? This concept also changes our perception of time and causality. If the Big Bang was a white hole, it suggests the existence of a universe with a more complex timeline, in which the beginning and end of cosmic phenomena are intertwined in ways we've yet to understand. This idea of the Big Bang as a white hole organically combines with the Big Bounce theory, according to which the beginning of our universe may be the result of the collapse of the previous universe. It unites the idea of cyclical universes, suggesting that each cosmic end can give rise to a new beginning, similar to the explosive genesis of a white hole. The existence of white holes may also confirm the concept of parallel universes. If white holes can eject matter and energy, could they be a gateway to other universes? This possibility is related to the multiverse theory, which postulates the existence of multiple, possibly infinite universes, along with our own. In parallel universes, there may be different versions of physics, alternate histories, and perhaps even variations of ourselves. Another intriguing connection relates to wormholes, hypothetical tunnels in space-time. Theoretical models suggest that wormholes could link distant regions of space, and perhaps even different universes. If white holes are connected to wormholes, they could serve as cosmic portals, opening paths to remote corners of the universe, or other dimensions altogether. This connection raises tantalizing questions about the nature of space and time. Could white holes and wormholes allow travel over vast cosmic distances, or even between different universes? Looking into the future of astrophysics, we see that at the moment there's a lot of scientific research in one way or another affecting the subject of white holes. But two research papers stand out among the rest, shedding light on the mysterious nature of these cosmic objects and offering new ideas and possibilities that could revolutionize our understanding of white holes. The first paper takes us on a journey to the very edge of black and white holes, exploring the close connections between them and refocusing on the physics occurring near their horizons. The authors introduce the concept of horizon-penetrating coordinate systems, a revolutionary approach that allows us to distinguish between the horizons of black and white holes. They differ from standard curvature coordinates in a small near-horizon region to emphasize the distinction between black and white horizons, which depends on near-horizon physics. This study suggests that black holes may not be the cosmic dead ends we once thought. Instead, they may be in quantum superposition with white holes, creating a scenario in which observed phenomena may hint at the existence of these theoretical white counterparts. The paper also delves into the role of quantum physics in these near-horizon regions, suggesting that quantum effects may dominate, leading to significant implications for our understanding of white holes. However, the authors emphasize that there's a problem in observational astrophysics, in which there is substantial observational evidence for black holes, but relatively weak observational support for white holes. Moving on to the second paper, titled New Black-to-White Hole Solutions with Improved Geometry and Energy Conditions, we find that the focus here is on the way to convert black holes into white holes, guided by the principles of quantum gravity. This study presents models in which the effects of quantum gravity prevent the formation of singularities inside black holes, providing a smooth transition to white holes. This solves the long-standing paradox of information loss by assuming that matter can pass through a black hole and appear in a white hole. The paper also explores geodesics within these models, confirming the completeness of particle trajectories in the transition from the black hole region to the white hole region. This supports the idea of a continuous, unimpeded flow of matter, changing our understanding of these cosmic phenomena. By integrating these theoretical developments with emerging technologies, we stand on the threshold of a new era in astrophysics. The future of white hole research promises to reveal new aspects of the universe, where the boundaries between quantum mechanics and general relativity are blurring. To summarize, we can say that the future of white hole research is very bright. Who knows? Perhaps very soon, we'll be able to discover indirect evidence for the existence of these intriguing objects. Are we alone? This question is, in some ways, as old as the starlight that travels through the eons to reach us. Since the earliest civilizations, our ancestors have looked up at the night sky in wonder, their imaginations fired by the flickering lights overhead. Today, armed with the power of modern science and technology, we still await the answer to this age-old question. But our goal is not just to find primitive life, but to discover the whispers of civilizations that might share this grand cosmic stage with us. The Breakthrough Listen Project, the most ambitious search for these whispers, techno-signatures, is pushing the limits of our hearing in an attempt to capture the murmurs of extraterrestrial life. As we stand at this crossroads of discovery, several teams of scientists in the Breakthrough Listen study and other SETI projects have already published several scientific papers moving us closer to answering this question. So, how close are we to the goal in this grand quest? What non-trivial decisions have been made to ensure a seamless search for signals and improve our chances? Let's get to the bottom of it. In our celestial odyssey to unlock the mysteries of life beyond Earth, scientists have charted two major paths across the cosmic seas: the search for biosignatures and the search for technosignatures. Each path offers a unique lens through which to view the potential for life in the universe, guided by the principles of astrobiology and the advanced technologies at our disposal. Biosignatures, the chemical fingerprints of life, serve as beacons in our search for biological activity on distant worlds. These signatures are not just markers, but signs of complex interactions between living organisms and the environment. Every molecule, from the oxygen and ozone created by photosynthetic life forms to the methane and carbon dioxide produced by biological and geological processes, carries a story of potential life. The James Webb Space Telescope, JWST, with its unprecedented sensitivity to the infrared spectrum, is our most advanced scout in this endeavor. Using transmission spectroscopy, JWST can analyze, dissect light from distant stars as it passes through the atmospheres of orbiting exoplanets. This light bears the fingerprints of various molecules, each absorbing certain wavelengths and leaving behind a spectral signature that JWST can detect and analyze. Peering into the depths of space, JWST searches out these spectral lines with precision, allowing us to infer the presence of water vapor, carbon dioxide, methane, and other potential biosignatures in the atmospheres of exoplanets. This method not only hints at the possibility of life, but also provides insight into the atmospheric composition, climate, and habitability of these distant worlds. Parallel to the search for biosignatures is the search for technosignatures, the hallmarks of advanced technological civilizations. Unlike biosignatures, which indicate the presence of life in any form, technosignatures suggest a leap to complexity, where life has evolved to use and manipulate its environment in profound ways. From radio signals to megastructures orbiting distant stars, technosignatures embody the potential to detect not only life, but also societies that may have mastered the art of cosmic communication. The pursuit of technosignatures spans the galaxy. Initiatives like the Breakthrough Listen project utilize vast networks of radio telescopes to listen to and eavesdrop through space. These telescopes scan the sky for narrowband radio signals, anomalies in the natural cosmic radiophone that may indicate deliberate transmissions from intelligent beings. Biosignatures are whispers of life embedded in the fabric of a planet's atmosphere, providing a glimpse into invisible worlds orbiting distant stars. Among the vast number of potential biosignatures, 4 stand out for their significance: oxygen and ozone, phosphine and ammonia, methane and carbon dioxide, and mysterious unexpected combinations of molecules. Oxygen, the breath of life on our planet, and its companion, ozone, form the first pair of key biosignatures. On Earth, oxygen is a byproduct of photosynthesis, the process that formed our atmosphere and allowed life to thrive. The presence of ozone, a molecule formed from oxygen by the sun's ultraviolet radiation, provides a protective layer shielding the surface from harmful radiation. The discovery of these molecules in the atmosphere of an exoplanet could indicate the presence of a thriving biosphere, perhaps similar to our own. Phosphine and ammonia, less common but no less intriguing, represent a second pair of biosignatures. Phosphine, a gas associated with anaerobic ecosystems on Earth, has been proposed as a potential marker of biological activity on other planets. Ammonia, another molecule with biological ties, may indicate the presence of life, especially in environments where it's not expected to exist in significant quantities due to non-biological processes. Methane and carbon dioxide form the third cornerstone of our quartet of biosignatures. Methane, a potent greenhouse gas, can be produced both biologically by organisms such as methanogens and abiotically by geologic processes. Carbon dioxide, a critical component of Earth's carbon cycle, is a product of respiration and volcanic activity. The simultaneous presence of methane and carbon dioxide, especially in unexpected ratios, may hint at biological processes in nature. Finally, with the fourth point, we move into the realm of unexpected combinations of molecules, methane and carbon dioxide, which cannot be stably present in more or less large quantities simultaneously without being transformed into other substances. Such combinations defy conventional expectations and point to the possibility of life functioning based on alien biochemical processes. The James Webb Space Telescope, JWST, humanity's most advanced observatory, is designed to study the atmospheres of exoplanets in search of these very biosignatures. Using transmission spectroscopy, JWST studies light from a star as it passes through a planet's atmosphere during its transit. When light passes through atmospheric gases, certain wavelengths are absorbed by the molecules, leaving behind a spectral fingerprint that JWST can detect and analyze. On the other hand, technosignatures, like the fingerprints of advanced civilizations, offer a different path in our quest to discover not just life, but societies that have reached a level of technological sophistication, perhaps similar to or even superior to our own. Unlike biosignatures, which hint at the mere presence of life, technosignatures speak of the ability of civilizations to alter the environment on a grand scale, communicate across the stars, and harness energy in ways we're only beginning to imagine. Technosignatures cover a wide range of signals and structures, from radio waves unintentionally emitted by a planet's communication networks to deliberate beacons aimed at the stars, from colossal energy collectors known as Dyson spheres to the barely perceptible glow of city lights on the exoplanet's night side. These signatures, if detected, will not only indicate the presence of life, but will also provide deep insights into the technological capabilities of alien civilizations. Our own planet is a prime example of a world teeming with technosignatures. Every radio broadcast, every satellite, and every piece of space debris orbiting the Earth creates a symphony of signals that, to the distant observer, unmistakably indicate the presence of an advanced civilization. The very fabric of our daily lives, from global communications networks to space probes venturing into the unknown, generates a cascade of signals that radiate out into space, making our presence known to all who can hear us. But why are technosignatures a more accurate way to search for technologically advanced civilizations? The answer lies in their specificity and the intentional or significant nature of the signals and structures they represent. While biosignatures can occur from simple microbial life to complex ecosystems, technosignatures clearly indicate a level of technological development and intent. The discovery of a technosignature not only confirms the existence of life, but also indicates that this life has crossed the threshold of cognitive and technological capability, engaging in activities that leave an indelible mark on the cosmic canvas. Breakthrough Listen was launched in 2016 with an ambitious mission to scour the cosmos for signs of technologically advanced civilizations. The project represents one of the most comprehensive searches for alien technosignatures ever undertaken. Armed with state-of-the-art technology and unprecedented scope, the project utilizes some of the most powerful radio telescopes in the world, including the Green Bank Telescope and Parkes Observatory. These colossal ears, tuned to the quiet whispers of the universe, can detect a range of signals, from faint radio emissions from distant stars to potential transmissions of extraterrestrial origin. At the heart of the mission is the desire to detect technosignatures, signals that, by their nature, can only be produced by technological means. These can range from narrowband radio signals that differ from the natural background noise of space, to powerful laser pulses that cut through cosmic clutter. The project had previously focused on the Milky Way galaxy for strategic reasons. To begin the search in our cosmic neighborhood, where such signals may be strongest and most detectable. The Milky Way, with its billions of stars, provides fertile ground for such work. Each observable star is a potential sun for other planets. Each planet a potential cradle for life as we know it, or life yet to be imagined. The project was originally designed not just to search for signals in our galaxy, but to explore in depth the nature of life and intelligence in the universe. Sifting through the cosmic expanse of the Milky Way looking for signs of life is akin to searching for a single word spoken in a whisper in the middle of a bustling metropolis. A galaxy of about 100 billion stars can easily conceal the signals of other civilizations. The task of monitoring such a vast array of targets for technosignatures is monumental, not only because of the large number of stars, but also because of the complex array of cosmic phenomena that can obscure or mimic the signals we are looking for. The problem is compounded by the limitations of our current technology and the limited resources at our disposal. Even with the most advanced radio telescopes, we can only listen to a small fraction of the stars in the galaxy at any given time. Huge distances dilute the signals, making them fainter as light years pass, and various natural cosmic phenomena such as the emission from pulsars and nebulae add further complexity to the search. In the face of these challenges, astronomers and scientists have looked beyond the familiar boundaries of the Milky Way to the wider universe. By observing galaxies as individual entities, each made up of billions of stars, we can try to pick up the cumulative signals of advanced civilizations. This extragalactic strategy is based on the premise that a sufficiently advanced civilization can harness technologies that affect its entire galaxy, from building megastructures like Dyson spheres to harnessing the energy of supermassive black holes. Such grandiose endeavors could lead to technosignatures that, in theory, could be found in vast intergalactic voids. The transition to extragalactic studies comes with some challenges, from even greater distances to the need for more sensitive instruments and more sophisticated methods of data analysis. Nevertheless, each galaxy observed and each data set analyzed brings us closer to understanding whether we're truly alone in the universe or part of a grander galactic world. Extragalactic exploration is exactly what Carmen Choza and her team did in 2023. Using the Robert C. Byrd Green Bank Telescope, the team has embarked on an ambitious mission to observe the centers of 97 nearby galaxies, studying them for 5 years. This work, one of the largest of its kind, used to search for narrowband Doppler drift in 4 frequency bands from 1 to 11 gigahertz. The goal was to detect signals that could come from civilizations capable of using energy equivalent to that of a Kardashev Type II civilization. The most important aspect of this study was the implementation of the TurboSETI pipeline, a sophisticated tool designed to search for Doppler drift. This pipeline played a crucial role in analyzing the vast amount of data collected during the study. To combat the persistent problem of radio frequency interference, called RFI, which often mimics extraterrestrial signals, the team adopted an on-source, off-source cadence pattern. This method involves alternating between observations of a target galaxy, on-source, and a nearby region devoid of the target, off-source, and is repeated 3 times for each galaxy. Because RF interference and localized noise are present regardless of the telescope's pointing, they'll appear in both on-source and off-source observations. In contrast, a true astronomical signal should only manifest itself in observations from the source and not in the observations beyond the source. This approach helped to distinguish real astronomical signals from terrestrial interference, which improved the reliability of the results. Despite careful methodology and advanced technology, the study faced significant challenges, primarily due to radio frequency interference. The team's innovative radio interference mitigation strategies, including signal injection and recovery tests, were crucial in differentiating terrestrial and potential extraterrestrial signals. These efforts emphasize the difficulty of finding technosignatures, especially since signals must be significantly more powerful than those detectable within our galaxy to be considered extragalactic. The exhaustive search resulted in 6,034,313 hits across all observed galaxies. These matches represent cases where the data analysis pipeline has identified signals that potentially stand out from the background noise and may be of interest for further study. From the original 6,034,313 matches, further refinement and analysis using a computer algorithm narrowed the field to 1,519 events of particular interest. These events were then scrutinized by the research team, which attempted to distinguish potential extraterrestrial signals from the all-pervasive RFI noise. Despite the complexity, the team eventually concluded that all 1,519 events were associated with terrestrial sources, or natural cosmic phenomena. However, The work done by Chosa and her team not only illuminates the path we've traveled, but also beckons us to new horizons. The ability to reanalyze data through the subtle prism of machine learning promises us a chance to uncover signals that previously remained obscure or were perceived as noise. This changing landscape of SETI research, constantly enriched by technological innovation, invites us to look deeper. As we move forward, armed with improved tools and a deeper understanding of the challenges that await us, the search for extraterrestrial technosignatures continues. In the meantime, we'll be eagerly awaiting new opportunities to solve the mysteries of the cosmos. In the shadowy depths of our solar system, far beyond the last known gas giant, lies a world shrouded in intrigue and mystery. This is Pluto. Once considered the 9th planet, it now occupies a separate category, at the center of heated debate and scientific curiosity. For decades, Pluto remained a blurry speck of light in our most powerful telescopes, a distant dot at the edge of our vision. It was a world waiting to be discovered, keeping its secrets in the cold, dark depths of space. At the dawn of the 21st century, an unprecedentedly ambitious mission began. The New Horizons spacecraft embarked on a billion-mile journey to explore Pluto's icy frontiers. What it discovered was astonishing in its diversity: towering ice mountains, huge nitrogen glaciers, and the legendary heart-shaped Tombaugh ratio, an object so large it can be seen from space. But these discoveries are just the beginning. Join us as we journey together into the icy depths of the outer solar system, where one dwarf planet is eagerly waiting to tell us its story. In the early 20th century, the search for a 9th planet, the mysterious Planet X, gripped the world of astronomy. The search was not just about adding another name to the list of planets. It was about understanding the unseen forces that shape the orbits of the then already known celestial bodies around us. At the center of this search was Lowell Observatory in Flagstaff, Arizona, where a young astronomer named Clyde Tombaugh embarked on a painstaking journey through space. Armed with a telescope and photographic plates, Tombaugh set out to scrutinize the night sky, inch by inch, in search of an elusive planet that eluded detection. On a February night in 1930, Tombaugh's diligence paid off. Among the countless stars, he spotted a moving object, a tiny speck of light that was unlike anything else he had observed. It was Pluto, a distant world named after the Roman god of the underworld, a discovery that would change the boundaries of our solar system. As the decades passed, Hubble's Space Telescope brought us closer to Pluto than ever before. Launched into orbit in 1990, Hubble's powerful lens pierced the veil of distance separating us from the outer solar system. The first images of Pluto were a revelation, transforming the distant dwarf planet from a mere glowing dot to a world with distinct features. These Hubble images provided the basis for a more detailed study. They showed Pluto's complex surface, marked by variations in brightness and color, hinting at a dynamic world waiting to be explored. An odyssey of discovery that began with a single blinking dot on a photographic plate has brought us to the threshold of a new frontier. Pluto, once a mere curiosity at the edge of our solar system, was about to reveal its secrets through a relentless pursuit of knowledge and a relentless spirit of exploration.
5, 4, 3, 2, 1. We have ignition and liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit the planet Pluto and then beyond.
In January 2006, humanity embarked on another of its most ambitious journeys. New Horizons, a spacecraft no bigger than a grand piano, was poised to cross the vast emptiness of space, heading for a world barely seen by human eyes. Its mission is to unlock the secrets of Pluto, a mysterious dwarf planet at the edge of our solar system. When New Horizons soared into the sky, it carried the aspirations of countless people who had devoted years to that moment. The journey was a marathon of cosmic proportions, spanning nearly a decade and more than 3 billion miles. With precision, it plotted a path through the void, guided by the gravitational slingshots of celestial bodies in its path. In 2015, after 9 long years, as New Horizons approached its distant destination, the whole world watched with bated breath. The first images were simply revolutionary. Pluto, which was once just a speck of light even in the most powerful telescopes, now appeared to be a world of mountains, valleys, and plains. The landscape that came into view was strikingly varied. Ice mountains, some as tall as the Rockies, rose proudly to the surface, their peaks shrouded in a blanket of methane snow. Sputnik Pallidie, a nitrogen ice plain, stretched across the entire dwarf planet, its surface mottled with a complex pattern of ridges and depressions. Among the most striking discoveries are signs of geological activity. Pluto, long thought to be a frozen relic from the dawn of the solar system, turned out to be alive. Glaciers of nitrogen ice slowly flowed across the landscape, and hints of cryovolcanoes indicated that this distant world was not as inactive as previously thought. New Horizons' leap into the unknown bridged the gap between assumptions and reality. Pluto was no longer just a point of light in our telescopes. It was a dynamic world full of surprises and beauty, waiting at the edge of our solar system. It was just the beginning of a new chapter in our understanding of the cosmos. Pluto's expanse of rugged landscapes is home to one of its most mesmerizing features, the Sputnik Planitia. This enormous heart-shaped glacier is not just a striking visual landmark. It's a geological marvel that's changed the way we think about this distant world. The origin of Sputnik Pallidie is a story of cosmic forces. This vast basin, stretching more than 650 miles, is believed to have been formed by the impact of a massive celestial body, an event that changed Pluto's surface and possibly its entire geology. The basin was filled with various ices, mostly nitrogen, creating a smooth, reflective plain that contrasts sharply with the surrounding topography. The surface of Sputnik Planitia is modeled with a complex pattern of convection cells, each the size of a country on Earth. These cells are the surface manifestation of ice in slow motion, churning and flowing in response to the weak heat coming from Pluto's interior. This lava lamp-like process shows that Pluto is far from the inert, frozen world we once imagined. More mysteries lie beneath the icy facade of Sputnik Planitia. The uniform mass distribution in this region, obtained from spacecraft measurements, hints at the presence of a denser layer beneath the ice. Scientists speculate that this may be a subsurface ocean. It's possible that this reservoir could contain liquid water isolated by the ice crust above. Among other discoveries, scientists have also found that Pluto has an atmosphere hovering above its icy surface, as thin and fragile as an atmosphere can be on the cold fringes of the solar system. Composed mostly of nitrogen, with traces of methane and carbon monoxide, this thin veil provides clues to understanding the planet's most mysterious processes. The structure of the planet's atmosphere does not match the primary expectations. When New Horizons flew by, it found an atmosphere extending hundreds of miles above the surface, much more extensive than expected. This thin atmospheric layer is stratified and has a complex interplay of gases that scatter and refract sunlight, creating a mesmerizing blue hue that resembles Earth's own sky. Because Pluto's journey around the Sun is unlike any other planet in our solar system, with an orbital period of an unimaginable 248 Earth years, each season on Pluto can last decades. Its trajectory is markedly elliptical. It is much closer to the Sun at perihelion than at aphelion, and its axis is tilted at an angle of 120 degrees, resulting in extreme seasonal variations on its surface. As Pluto approaches its perihelion, the heat from the distant Sun, though faint, is enough to cause a remarkable transformation. Surface ices, composed of nitrogen, methane, and carbon monoxide, begin to sublimate, a process by which these ice change from a solid state to a gaseous state, without changing to an intermediate liquid state. This sublimation is most pronounced in regions exposed to the sun's weak but constant rays, resulting in an increase in atmospheric pressure as gases previously trapped in ice form are released to the outside. This outgassing thickens Pluto's atmosphere, making it more substantial during these warm periods. The atmosphere expands, rising hundreds of kilometers above the surface, much more than during colder periods. This expansion is uneven, and it's influenced by Pluto's topography and the composition of its ice, creating a complex and dynamic atmospheric system. As Pluto continues its long journey, moving away from the sun and toward more distant parts of its orbit, the atmosphere is undergoing a dramatic turn of events. The gases that once thickened the atmosphere are now cooling and condensing, falling back to the surface as a fine snow of nitrogen, methane, and carbon monoxide. This cyclical process of sublimation and condensation is a defining feature of Pluto's climate, changing its surface over the centuries. This dance of ice and vapor unfolding over the course of Pluto's long year paints a portrait of a world in constant motion. Far from a static, frozen wasteland, Pluto's surface is a dynamic environment, a reminder of the active and ever-changing nature of even the most distant members of our solar system. Another exciting discovery about Pluto's atmosphere is its escape rate. Unlike the strong magnetic fields and gravitational pull that protect the atmosphere of the larger planets, Pluto's weak gravity allows much of its atmosphere to escape into space. This atmospheric escape contributes to the ionized gas tail, an invisible comet-like trail that Pluto leaves behind it as it orbits the sun. This leakage is not a steady, gentle flow, but a complex interaction with a solar wind, a stream of charged particles emanating from the sun. These particles, colliding with escaping atmospheric gases, create a dynamic and ever-changing environment around Pluto, a miniature magnetosphere in which the drama of solar and planetary forces is played out. From Pluto's dynamic atmosphere and unique climate, we move to its largest moon, Charon, and discover relationships and landscapes that change the very definition of celestial bodies in the outer part of our solar system. Charon, Pluto's largest satellite, orbits in synchronized motion with it. Discovered in 1978, this celestial body turns out to be more than just a satellite. It is a whole world filled with geological wonders and a unique history that's intertwined with that of Pluto. As New Horizons flew past Charon, they saw a landscape of canyons so deep and wide they could easily swallow up parts of Earth's Grand Canyon. These chasms stretched across the surface of the satellite, telling a story of geologic upheaval. Mountains rising dramatically against the lunar surface reveal a dynamic history, their peaks casting long shadows over the valleys below. The origins of Charon's dramatic topography lie in its past, marked by internal processes and possibly cryovolcanic activity. As Charon cooled and compressed over millions of years, its crust split, resulting in vast canyons. At the same time, mountains may have formed from tectonic activity as the moon's surface flexed and broke, pushing some areas upward and raising peaks. The interaction between Pluto and Charon is a kind of gravitational ballet in which both bodies are locked in a synchronized orbit. This means that Charon always faces Pluto on the same side, and vice versa, a phenomenon known as tidal locking. Unlike most moons, which orbit around their planets, Pluto and Charon orbit around a point in the space between them, known as the barycenter. This unique arrangement challenges the conventional definitions of planets and moons, suggesting a binary system where both bodies are partners in their celestial tandem. This gravitational partnership extends beyond Pluto and Charon, affecting the orbits of Pluto's smaller moons, Styx, Nix, Kerberos, and Hydra. Charon's presence stabilizes these smaller satellites, maintaining the complex balance of the system. The dynamics of this mini-solar system give us valuable insight into the gravitational interactions that shape the orbits of celestial bodies throughout the universe. Located in the vast realm of the Kuiper Belt, Pluto stands like a sentinel at the edge of our solar system. This region, a vast cluster of icy bodies extending beyond the orbit of Neptune, is a relic of the early solar system and holds the keys to understanding the formation and evolution of our cosmic neighbor. Pluto, once thought to be the 9th planet, has found its relatives among the vast number of Kuiper Belt objects, or KBOS. Like dwarf planets like Haumea and Makemake, to smaller, lesser-known bodies, each KBO has its own story that contributes to the picture of the solar system. Pluto's varied landscape, from nitrogen ice plains to towering mountains and dynamic atmospheres, reflect the complexity and diversity of the Kuiper Belt landscape. The Kuiper Belt is a window to the past, a frozen archive of the birth of the solar system. The objects included in it, including Pluto, are remnants of the time of planetary formation, untouched by the sun's heat. Their composition, ice mixed with rocks, gives an idea of the materials that abounded in the early solar system and allows us to understand the processes that led to the birth of the planets. Exploring Pluto and its neighbors in the Kuiper Belt has far-reaching implications for our understanding of the solar system. Each mission, like the New Horizons flyby of Pluto and Arrokoth, peels away layers of mystery, revealing the conditions and processes that prevailed in the outer solar system billions of years ago, forcing us to consider the dynamics of planetary formation and the boundaries between planets and smaller celestial bodies. Pluto's position in the Kuiper Belt emphasizes the interconnectedness of celestial bodies, from the smallest piece of ice to the largest gas giant. The dynamics of the Kuiper Belt, with its resonances and orbital interactions, influence the stability and evolution of the outer solar system, shaping the trajectories of comets and affecting the environment of Neptune. However, New Horizons exploration didn't end there. After its historic flyby of Pluto, it traveled onward to Arrokoth, a Kuiper Belt object, meeting it on January 1, 2019, marking the next milestone in space exploration. Arrokoth, resembling a clay snowman, demonstrated the soft merger of two primordial objects, offering unprecedented insight into the building blocks of the early solar system. The story of Arrokoth's formation is a testament to the slow and gentle processes that dominated the outer regions of the early solar system. The large lobe, called Bennu, is not a single formation, but a cluster of a dozen rocks, each more than 3 miles wide, huddled around a central slab. This cluster refutes previous notions of high-velocity collisions in planetary formation, suggesting instead a gradual merger at speeds of less than a dozen feet per second. This intricate interaction between two lobes, losing angular momentum and smoothly merging, forms an image of a patient cosmos where the building blocks of the planets come together in a heavenly cycle of gravity and time. Looking ahead, the horizon of solar system exploration is littered with potential. Concepts for the next New Horizons missions are already stirring the imagination of scientists and engineers. One of them envisions an orbiter capable of mapping Pluto's surface with unprecedented resolution, penetrating the mysteries of its small satellites, and even exploring the eternal darkness of the regions enveloped by Pluto's axial tilt. The project, inspired by the legacy of Cassini, proposes to use Charon's gravity to create complex orbital trajectories around Pluto, allowing for a comprehensive study of the dwarf planet and its satellites. Such missions could utilize electric propulsion, replicating the success of NASA's Dawn, and could potentially go beyond the Pluto system and explore new frontiers in the Kuiper Belt. New technologies such as direct fusion drives promise to propel future spacecraft to the outer solar system with unprecedented speed and efficiency. A report titled "The Fusion-Enabled Pluto Orbiter and Lander" from NASA's Innovative Advanced Concepts NIAC program describes a mission to Pluto with a direct fusion drive. Using a fusion reactor, a 1,000-kilogram orbiter and landing module could reach Pluto in just 4 years, more than twice the speed of New Horizons. These promising propulsion systems could significantly shorten the travel time. opening new pages in the exploration of the distant worlds of our outskirts. As we travel the vastness of space, exploring distant worlds and discovering the secrets they hold, our understanding of the cosmos continues to evolve. The story of Pluto, from its discovery to the present day, is a vivid reminder of the dynamic nature of science and our attempts to categorize the universe around us. Pluto's unique orbital interaction with Neptune adds another layer to its fascinating story. During its 248-year orbit around the Sun, Pluto appears closer to the Sun than Neptune for a brief time, challenging the view of its position as the ninth planet. This crossing of orbits, when Pluto and Neptune change places, occurs because of the elliptical trajectory of Pluto's orbit and its inclination relative to the plane of the solar system. Despite this temporal shift, Pluto's overall trajectory ensures that there's no risk of collision with Neptune due to their mutual orbital resonance. The rather lengthy debate over Pluto's planetary status has long sparked discussion and controversy that reaches far beyond the astronomical community. In 2006, the International Astronomical Union revised the definition of planet in our solar system, which led to Pluto's reclassification as a dwarf planet. This moment was not only a turning point for Pluto, but also a catalyst for the reclassification of celestial bodies. Pluto's history is closely tied to the Kuiper Belt, a region teeming with objects that blur the boundaries between planets, moons, and smaller celestial bodies. Studying Pluto and its neighbors makes us think about the wide range of characteristics that celestial bodies can possess, from their atmospheres and geology to their orbits and interactions. In the grand canvas of the cosmos, every thread, from the smallest asteroid to the mightiest gas giant, plays a critical role in the history of our solar system. As we stand at the threshold of new exploration, Pluto's legacy and the knowledge gained from the Kuiper Belt serve as beacons guiding us to a deeper understanding of our place.
But God evolved into something more to him than a vengeful deity needing appeasement. Kepler conceived God as the cosmic force responsible for its creation. The young boy overcame his anxiety by embracing his natural curiosity. He dared to ponder God's thoughts and wanted to learn more about the eschatology of the world. These terrifying visions, which at first only existed as memories, eventually became a lifelong obsession for the person. The egotistical goals of a young student at a seminary were to lead Europe away from the intellectual cloister of the Middle Ages. It had been more than 1,000 years since the sciences of classical antiquity were last practiced. But in the late Middle Ages, some faint echoes of those voices, which had been preserved by Arab scholars, began to make their way into the educational curriculum of Europe. While he was in Malbronn, Kepler was able to hear their reverberations while studying, among other things, theology, Greek, Latin, music, and mathematics. He believed he had seen an image of perfection and cosmic glory in Euclid's geometry. In later writings he stated, "Geometry existed before the creation." Geometry is co-eternal with the mind of God. The model for creation that God used was provided by geometry. The essence of God can be found in geometry. Amid Kepler's mathematical raptures, and even though he lived a sequestered life, the imperfections of the outside world must also have molded his character. Superstition was a widely available nostrum for people powerless against the miseries of famine, pestilence, and deadly doctrinal conflict. For many, the only certainty was the stars, and the ancient astrological conceit prospered in the courtyards and taverns. In 1589, Kepler left Malbronn to study for the clergy at the great university in Tübingen, and found it a liberation. Confronted by the most vital intellectual currents of the time, his teachers immediately recognized his genius. One of his teachers introduced the young man to the dangerous mysteries of the Copernican hypothesis. A heliocentric universe resonated with Kepler's religious sense, and he embraced it with fervor. The sun was a metaphor for God. Kepler was a brilliant thinker and a lucid writer, but he was a disaster as a classroom teacher. He mumbled, he digressed. He was, at times, utterly incomprehensible. He drew only a handful of students his first year at Graz. The next year, there were none. He was distracted by an incessant interior clamor of associations and speculations vying for his attention. Only 6 planets were known in Kepler's time: Mercury, Venus, Earth, Mars, Jupiter, and Saturn. Kepler wondered why only 6. Why not 20 or 100? Why did they have the spacing between their orbits that Copernicus had deduced? No one had ever asked such questions before. There were known to be 5 regular or platonic solids whose sides were regular polygons, as known to the ancient Greek mathematicians after the time of Pythagoras. Kepler thought the 2 numbers were connected, that there were only 6 planets because there were only 5 regular solids, and that these solids, inscribed or nested one within another, would specify the distances of the planets from the Sun. In these perfect forms, he believed he had recognized the invisible supporting structures for the spheres of the 6 planets. He called his revelation the cosmic mystery. The connection between the solids of Pythagoras and the disposition of the planets could admit only one explanation: the hand of God, the geometer. Kepler was astonished that he, a sinner according to his own perceptions, should have been divinely chosen to make such a significant discovery. In his proposal for a research grant to the Duke of Württemberg, he offered to supervise the construction of his nested solids as a 3-dimensional model so that others could see the beauty of the holy geometry. He did this so that others could see the beauty of the holy geometry. He said it was possibly crafted from silver and precious stones and functioning as a ducal chalice. The proposal was rejected with the kindly advice that he first construct a less expensive version out of paper, which he promptly attempted to do. The intense pleasure I have received from this discovery can never be told in words. I shunned any calculation, no matter how difficult. Days and nights I spent in mathematical labors until I could see whether my hypothesis would agree with the orbits of Copernicus, or whether my joy was to vanish into thin air. But no matter how hard he tried, the solid elegance and grandeur of the theory persuaded him that the observations must be in error, a conclusion drawn when the observations are unobliging by many other theorists in the history of science. There was then only one man in the world who had access to more accurate observations of apparent planetary positions: a self-exiled Danish nobleman who had accepted the post of imperial mathematician in the court of the Holy Roman Emperor, Rudolf II. That man was Tycho Brahe. By chance, at Rudolf's suggestion, he had just invited Kepler, whose mathematical fame was growing, to join him in Prague. The local Catholic archduke, steadfast in dogmatic certainty, vowed to make a desert of the country, then rule over heretics. Protestants were excluded from economic and political power. Kepler's school was burned down. In 1598, one of the many premonitory tremors of the coming 30 Years' War engulfed him. Kepler was a provincial schoolteacher of humble origins and unknown to only a few mathematicians. After departing from Graz, Kepler, his wife, and his stepdaughter began the challenging journey to Prague. Their marriage did not have a lot of joy. Chronically ill and having recently lost 2 young children, his wife was described as stupid, sulking, lonely, and melancholy. She had no understanding of her husband's work, and having been raised among the minor rural gentry, she despised his impecunious profession. He, for his part, alternately reprimanded and ignored her. For my studies sometimes made me thoughtless, but I learned my lesson. I learned to have patience with her. When I saw that she took my words to heart, I would rather have bit my own finger than to give her further offense. However, Kepler remained preoccupied with his work and did not acknowledge his wife's reaction. He envisioned Tycho's domain as a refuge from the evils of the time and the place where his cosmic mystery would be confirmed. He aspired to become a colleague of the great Tycho Brahe, who for 35 years had devoted himself before the invention of the telescope to the measurement of a clockwork universe, ordered and precise. Kepler's expectations needed to be fulfilled. Impatient to see Tycho's astronomical data, Kepler would be thrown only a few scraps at a time. Tycho gave me no opportunity to share his experiences. He would only, in the course of a meal and in between other matters, mention, as if in passing, today the figure of the apogee of one planet, tomorrow the nodes of another. Tycho possesses the best observations. He also has collaborators. He needs more than the architect who would put all this to use. Tycho was the greatest observational genius of the age, and Kepler was the greatest theoretician. Each knew that he would be unable to synthesize an accurate and coherent world system, which they both felt was imminent. But Tycho was not about to make a gift of his life's work to a much younger potential rival. Joint authorship of the results, if any, of the collaboration was, for some reason, unacceptable. The birth of modern science, the offspring of theory and observation, teetered on the precipice of their mutual mistrust. In the remaining 18 months that Tycho was to live, the two quarreled and were reconciled repeatedly. Tycho, having robustly drunk much wine at a dinner given by the Baron of Rosenberg, Tycho, having robustly drunk much wine, placed civility ahead of health, and resisted his body's urgings to leave, even briefly, before the Baron. The resulting urinary tract infection worsened when Tycho steadfastly disregarded advice to moderate his consumption of food and drink. On his deathbed, Tycho bequeathed Kepler his observations, and on the last night of his gentle delirium he repeated over and over again these words like someone composing a poem: "Let me not seem to have lived in vain. Let me not seem to have lived in vain." After Tycho's passing, Kepler, who was by this time the new imperial mathematician, could coax the observations out of Tycho's family, who were resistant. His hypothesis, which proposes that the orbits of the planets are circumscribed by the 5 Platonic solids, is not supported by Tycho's or Copernicus's data in the slightest. His cosmic mystery was completely debunked by the much later discoveries of the planets Uranus, Neptune, and Pluto, because no Platonic solids could determine the distances between the Sun and the planets. In addition, the nested Pythagorean solids did not account for the Moon's presence in our solar system, and Galileo's observation that Jupiter has 4 significant moons was, rather than becoming depressed, Kepler wanted to find more satellites, and was curious about the average number of satellites each planet should have. He sent the following letter to Galileo: "I immediately began to think how there could be any addition to the number of the planets without overturning my Mysterium Cosmographicum, according to which Euclid's 5 regular solids do not allow more than 6 planets around the Sun. I am so far from disbelieving the existence of the 4 circumjovial planets that I long for a telescope to anticipate you in discovering 2 around Mars." Tycho's observations of the apparent motion of Mars and other planets through the constellations were made over many years. These data from the last few decades before the telescope was invented were the most accurate that had yet to be obtained. Kepler worked passionately to understand them. What real motion of the Earth and Mars about the Sun could explain, to the precision of measurement, the apparent motion of Mars in the sky, including it moving through the constellations? Pythagoras in the 6th century BC, Plato, Ptolemy, and all of the Christian astronomers before Kepler assumed that the planets moved in circular paths. The circle was thought to be a perfect geometrical shape, and the planets, placed high in the heavens, away from earthly corruption, were also thought to be, in some mystical sense, perfect. In the beginning, Kepler attempted to explain the observations by imagining that the Earth and Mars moved in circular orbits around the Sun. This was because Galileo, Tycho, and Copernicus were all committed to uniform circular planetary motion. Copernicus specifically stated that the mind shudders at the alternative because it would be unworthy to suppose such a thing in a creation constituted in the best possible way. After 3 years of calculation, he believed he had found the correct values for a Martian circular orbit, which matched 10 of Tycho's observations within 2 minutes of the arc. There are 60 minutes of arc in an angular degree and 90 degrees, a right angle, from the horizon to the zenith. Therefore, a few minutes of arc is a very small quantity to measure, especially without a telescope. The difference between a circular and true orbit could only be distinguished through precise measurement and a courageous acceptance of the facts. The universe is stamped with the adornment of harmonic proportions, but harmonies must accommodate experience. Kepler was shaken when compelled to abandon a circular orbit and question his faith in the divine geometer. As Copernicus had said, the Earth was a planet, and it was obvious to Kepler that it, racked by wars, pestilence, famine, and unhappiness, fell short of perfection. Kepler was one of the first people since antiquity to propose that the planets were material objects made of imperfect stuff like the Earth. And if planets themselves were imperfect, why not their orbits? Oh, what a silly bird I have been in the past. Kepler discovered that Mars moves around the Sun in a circle and an ellipse. The other planets have orbits much less elliptical than Mars, and if Tycho had urged him to study the motion of, say, Venus, Kepler might have yet to discover the true orbits of the planets. In such an orbit, the Sun is not at the center but is offset at the focus of the ellipse. In a uniform circular motion, an equal angle or fraction of the arc of a circle is covered in equal parts. So, for example, it takes twice as long to go 2/3 of the way around a circle as it does 1/3 of the way around. Kepler found something different for elliptical orbits. As the planet moves along its orbit, it sweeps out a wedge-shaped area within the ellipse. When it is close to the Sun, it traces out a large arc in its orbit in a given period. But the area represented by that arc is small because the planet is then near the Sun. When the planet is far from the Sun, it covers a much smaller arc in the same period, but it corresponds to a bigger area because the Sun is now more distant. Kepler found that these two areas were precisely the same no matter how elliptical the orbit. The long, skinny area, corresponding to the planet far from the Sun, and the shorter, squatter area when the planet is close to the Sun, are exactly equal. This was Kepler's second law of planetary motion. Planets sweep out equal areas at equal times. We may dismiss these laws as mere mathematical tinkering, something removed from everyday life. However, these are the laws that our planet obeys as we, glued by gravity to the surface of the Earth, hurtle through interplanetary space. We move following the third and final law of planetary motion many years later. This law relates the motion of various planets to one another, and correctly lays out the clockwork of the solar system. He described this law in a book titled The Harmonies of the World. Kepler understood many things by the word harmony, including the order and beauty of planetary motion, mathematical laws explaining that motion, an idea that goes back to Pythagoras, and even harmony in the microbial world. Compared to the orbits of Mercury and Mars, the orbits of the other planets deviate from circularity to such a small degree that even an extremely accurate diagram cannot show us their true shapes. Our moving platform, the Earth, from which we observe the motion of the other planets against the background of far-off constellations, is the Milky Way galaxy. The inner planets travel through their orbits faster, which is why Mercury is given the name it does. Mercury was the messenger of the gods. The orbital speeds of Venus, Earth, and Mars become progressively slower as they move away from the Sun. As befits their status as kings of the gods, the outer planets, such as Jupiter and Saturn, move stately and slowly. Kepler's third or harmonic law states that the squares of the periods of the planets, the times for them to complete one orbit, are proportional to the cubes of their average distance from the Sun. The more distant the planet, the more slowly it moves. But according to a precise mathematical law, P2 on A3, where P represents the period of revolution of the planet about the Sun measured in years, and An is the distance from the Sun measured in astronomical units. In other words, a similar line of reasoning can be applied to every planet, asteroid, and comet in the solar system. What number, when multiplied by itself, equals 125? 11 is pretty close. Jupiter makes one revolution around the Sun every 11 years. Not content to have merely extracted the laws of planetary motion from nature, Kepler endeavored to find some still more fundamental underlying cause, some influence of the Sun on the kinematics of worlds. The planets sped up on approaching the Sun and slowed down on retreating from it. Somehow, the distant planets sensed the Sun's presence. Magnetism was also an influence felt at a distance, and in stunning anticipation of the idea of universal gravitation, Kepler's fundamental innovation in this area is breathtaking. He proposed that quantitative physical laws that apply to the Earth are also the underpinnings of quantitative physical laws that govern the heavens. This was the first non-mystical explanation of motion in the heavens, making the Earth a province of the cosmos. Magnetism is not the same as gravity, but Kepler's fundamental innovation in this area is breathtaking. He said, "Astronomy is a part of physics." Kepler's place in history is significant because he was the first astrophysicist and the last scientific astrologer. Kepler, who was not known for his modesty or quiet understatement, summarized his findings as follows. Kepler believed that within the symphony of voices, the speed of each planet corresponds to certain notes in the Latinate musical scale that was popular in his day. These notes include do, re, mi, fa, sol, la, ti, and do. He asserted that in the harmony of the spheres, the tones of Earth are fa and mi, that the Earth is perpetually humming fa and mi, and that these tones are a direct translation of the Latin word for famine. He also claimed that the Earth is constantly humming these tones. He argued, not without some success, that the Earth could be summed up in a single gloomy word. In Prague, the event that sparked the 30 Years' War outbreak occurred precisely 8 days after Kepler announced the discovery of the third law that bears his name. The upheavals caused by the war shattered the lives of millions of people, including Kepler. He was excommunicated by the Lutheran Church for his unyielding individualism on matters of doctrine, for which he was responsible for the deposition of his royal patron and for the loss of his wife and son to an epidemic carried by the soldiery. Once more, Kepler was forced to flee his home. Catholics and Protestants portrayed the conflict as a holy war. However, it was more of an exploitation of religious fanaticism by those hungry for land and power. In days gone by, conflicts were typically settled when the warring princes ran out of available resources to fight with. But now, organized pillage was introduced as a means of keeping armies in the field. The barbaric people in Europe watched helplessly as tools like plowshares and pruning hooks were transformed into swords and spears by being literally beaten into shape. Rumor and paranoia spread like wildfire across the countryside, engulfing those without control over the situation. Older women who lived alone were some of the many people targeted to serve as scapegoats. They were accused of practicing witchcraft. In the middle of the night, Kepler's mother was stolen away in a chest of drawers from the laundry room. Between 1615 and 1629, approximately 3 women were persecuted and put to death in the town of Weil der Stadt, which was Kepler's hometown. They were accused of practicing witchcraft. Katharina Kepler was an older woman who lived a stodgy life. She got involved in arguments that irked the local nobility, and she sold drugs that were possibly hallucinogenic and soporific, just like Mexican curanderas do today. Kepler, the poor man, was under the impression that he was responsible for her apprehension. Kepler is credited with writing one of the earliest works of science fiction, intended to explain and popularize scientific concepts. This led to the discovery. It was called the Somnium, Latin for the dream. He imagined a journey to the moon, with the space travelers standing on the lunar surface and observing the lovely planet Earth rotating slowly in the sky above them. By changing our perspective, we can figure out how the world works. One of the primary objections to the idea that the Earth turns was that people do not feel the motion. I want to be one of the many who support this cause. Because of this, I make it a point to explain it to as many people as possible. On another occasion, he wrote in a letter, "Do not sentence me completely to the treadmill of mathematical calculations. Leave me time for philosophical speculations. my sole delight. What Kepler referred to as lunar geography was made possible by the invention of the telescope. In the Somnium, he described the moon as being filled with mountains and valleys, and as being porous, as though dug through with hollows and continuous caves. This referenced the lunar craters Galileo had recently discovered with the first astronomical telescope. Kepler also imagined that the moon had inhabitants well adapted to the harsh conditions of the local environment. Because of the lunar day and night length, Kepler described the great intemperateness of climate and the most violent alternation of extreme heat and cold on the moon, which is entirely accurate. Of course, he did not get everything right. For instance, he believed a substantial lunar atmosphere, oceans, and inhabitants existed. Most curious is his view of the origin of the lunar craters, which make the moon not dissimilar to the face of a boy dripping with blood. He successfully argued that the craters should be depressions rather than mounds. His observations led him to notice the ramparts that surrounded many of the craters and the centrally located peaks. On the other hand, he believed that because of their regular circular shape, which suggested a high degree of order, the only thing that could explain them was intelligent life. He was unaware that large rocks crashing to the surface from space would cause a local explosion that would be perfectly symmetric in all directions and carve out a circular cavity. This mechanism is responsible for forming most of the craters on the Moon and the other terrestrial planets. Instead, he deduced the existence of some race rationally capable of constructing those hollows on the Moon's surface. He reasoned that this race must consist of many individuals so that one group can utilize one hollow while another group constructs another. Kepler offered as counterexamples the pyramids of Egypt and the Great Wall of China, both of which can in fact be seen today from Earth's orbit, refuting the view that such enormous construction projects were unlikely. Kepler's entire life revolved around the concept that the order revealed by geometry points to an underlying intelligence. His argument regarding the craters on the Moon provides an unmistakable preview of the debate regarding the canals on Mars. It is fascinating to consider that the observational search for extraterrestrial life began in the same generation as the invention of the telescope and with the most prominent theoretician of the time. Several parts of the Somnium were very obviously autobiographical. For instance, the protagonist pays a visit to Tycho Brahe. His parents are involved in the drug trade. His mother is known to have associations with ghosts and demons, and it is eventually one of these entities that provides... At the time of the 30 Years' War, science fiction was a novel concept, and Kepler's book was used as evidence that his mother was a witch. However, the Somnium makes it clear to us, even though it did not to all of Kepler's contemporaries, that, in a dream, one must be allowed the liberty of occasionally imagining that which never existed in the world of sense perception. Amid other serious personal problems, Kepler rushed to Württemberg to find his mother, who was 74 years old, chained in a Protestant secular dungeon and threatened, like Galileo in a Catholic dungeon, with torture. He immediately set about, as a scientist naturally would, to find natural explanations for the various events that had precipitated the accusations of witchcraft, including minor physical ailments that the burghers of Württemberg had. He spent his final years in a Silesian town controlled by Wallenstein and called Sagan, and his epitaph, which he composed, was as follows: I measured the skies, now the shadows I measure. Sky-bound was the mind, earth-bound was the body, but the 30 Years' War obliterated his grave. If a marker were to be erected today, it might read, as a homage to his scientific courage, he preferred the hard truth to his dearest illusions. Johannes Kepler had the vision that one day there would be celestial ships with sails adapted to the winds of heaven, sailing through the sky, filled with explorers, who would not fear the vastness of space. Today, those human and robot explorers employ as unerring guides on their voyages through the vastness of space the 3 laws of planetary motion that Kepler discovered during a lifetime of personal struggle and ecstatic discovery. Isaac Newton was born on Christmas Day, 1642, so tiny that, as his mother told him years later, he would have fit into a quart mug. Despite being sickly, feeling abandoned by his parents, quarrelsome, unsociable, and a virgin to the day he died, Isaac Newton was perhaps the greatest scientific genius who ever lived. Kepler's lifelong quest to understand the motions of the planets and seek harmony in the heavens culminated in the work of Isaac Newton. Even as a young man, Newton was impatient with questions that lacked substance, such as whether light was a substance or an accident, or how gravitation could act over an intervening vacuum. He was also impatient with people who questioned his theories. Early on, he concluded that the traditional Christian understanding of the Trinity was based on a misunderstanding of the biblical text. His biographer, John Maynard Keynes, says the following about him. He adhered more to the monotheistic approach of the Maimonidean school of Judaism. He arrived at this verdict not based on anything that could be considered rational or skeptical, but solely on the interpretation of ancient authority. He was convinced that the revealed documents did not support the Trinitarian doctrines, which resulted from late forgeries, and that this was due to the revelations. The God who was revealed was a singular deity. But this was a terrible secret that Newton had spent his entire life doing everything he could to keep hidden. He was not immune to the superstitions of his day, and had many encounters with mysticism. He was similar to Kepler in this regard. In fact, a significant portion of Isaac Newton's intellectual growth can be traced back to the conflict between rationalism and mysticism. At the Stourbridge Fair in 1663, at age 20, he purchased a book on astrology out of a curiosity to see what was in it. He read it until he came to an illustration that he could not understand because he was ignorant of trigonometry. So he purchased a book on trigonometry, but soon found himself unable to follow the geometrical arguments. So he found a copy of Euclid's Elements of Geometry and began to read. 2 years later, he invented differential calculus. Newton, a student at the time, was mesmerized by light and hypnotized by the sun. As a result, he engaged in the potentially fatal practice of staring at the reflection of the sun in a looking glass. I had brought my eyes to such a state in a matter of hours that I was unable to look upon any bright object with either eye. But I saw the sun before me so that I could neither write nor read. But to regain the use of my eyes, I shut myself up in my chamber, made 3 dark days together, and used every means possible to divert my imagination from the sun. If I thought of him, I immediately saw his picture. Newton was an undergraduate at Cambridge University in 1666, when a plague outbreak forced him to spend a year in idleness in the isolated village of Woolsthorpe, where he had been born. During this time, Newton invented differential and integral calculus, made fundamental discoveries on the nature of light, and laid the foundation for the theory of universal gravitation. The only other year in the history of physics that was comparable to Newton's was Einstein's. Isaac Barrow, Newton's mathematics professor at Cambridge, stepped down from the chair he held in favor of Newton 5 years after the young student had returned to the university. Newton's work was considered to be of such great significance. The following is how Newton, who was in the middle of his 40s at the time, was described by his servant. I never knew him to take any recreation or pastime either in riding out to take the air, walking, bowling, or any other exercise whatever, thinking all hours lost that were not spent in his studies, to which he kept so close that he seldom left his chamber unless to lecture, at term time, where so few went to hear him and fewer understood him that oft times he did in a manner, for want of hearers, read to the walls. Students who studied under Kepler and those who studied under Newton were never aware of what they were missing out on. Newton is credited with discovering the law of inertia, which states that an object in motion tends to continue moving in a straight line unless influenced by something that causes it to deviate from its path. It appeared to Newton that the moon would fly off in a straight line, tangential to its orbit unless there was some other force constantly diverting the path into a near circle and pulling it in the direction of the Earth. If this other force did not exist, the moon would fly off in a straight line, tangential to its orbit. Newton coined the term gravity to describe this force, and he believed that it operated at a distance. There is no actual connection between the Earth and the moon on a physical level. Despite this, the pull of the Earth's gravitational pull on the moon never stops, Newton mathematically deduced the using Kepler's third law as his starting point, the fundamental characteristics of the gravitational force. He demonstrated that the same force that causes an apple to fall to the ground is also responsible for keeping the Moon in its orbit around the Earth, and for accounting for the revolutions of the then recently discovered moons of Jupiter in their orbits around that faraway planet. Ever since the beginning of time, things had been going from bad to worse. Since the beginning of human history, people have believed that the Moon followed a path around the Earth. Newton was the first to discover that both occurrences could be traced back to the same driving force. This is what is meant when we use the term universal in Newton's theory of gravitation. The law of gravity is universal and applies in every part of the universe. This is under the law of the inverse square. The force decreases at a rate proportional to the square of the distance. When two objects are separated by a distance that is twice as great, the gravitational force that pulls them towards one another is only 1/4 as strong. If they are more than 10 times further apart, then the gravity is 10 squared, 10 to the power of 2, which equals 100 times less. It is abundantly clear that the force must be inverse in some sense. That is, it must decrease with increasing distance. If the force was direct and increased with distance, then the most powerful force would work on the most remote objects, and I imagine that all of the matter in the universe would end up clumping into a single cosmic mass. No, gravity can't increase with distance. This is why a comet or a planet moves slowly when it is far from the Sun and quickly when it is close to the Sun. The gravity that they experience is weaker the further they are from the Sun. From Newtonian principles, it is possible to derive all three of Kepler's laws regarding the motion of planets. The empirical observations made by Tycho Brahe served as the foundation for Kepler's laws, which were developed later. Newton's laws were theoretical, rather straightforward mathematical abstractions, and they were ultimately the starting point from which all of Tycho's measurements could be derived. As a direct result of these laws, Newton wrote with undisguised pride in the Principia, "I now demonstrate the frame of the system of the world." Newton spent the latter part of his life serving as the Master of the Mint and as the President of the Royal Society. As President of the Royal Society, he focused on combating counterfeit coinage. Some spread rumors that he had experienced the 17th century equivalent of a nervous breakdown. However, Newton continued his lifelong experiments on the border between alchemy and chemistry, and some recent evidence suggests that what he was suffering from may not have been a nervous breakdown at all. His natural moodiness and reclusively grew. He abandoned those scientific endeavors that brought him into quarrelsome disputes with other scientists, primarily on priority issues. His moodiness and wreck, nevertheless, his prodigious intellectual powers persisted unabated. In 1696, the Swiss mathematician Johann Bernoulli challenged his colleagues to solve an unresolved issue called the brachistochrone problem, specifying the curve connecting 2 points displaced from each other laterally, along which a body, acted upon only by gravity, would fall in the shortest time. Bernoulli originally specified a deadline of 6 months, but extended it to 1.5 years at the request of Leibniz, one of the leading scholars of the time and the man who, independently of Newton, invented differential and integral calculus. The challenge was delivered to Newton at 4 p.m. on January 29, 1697. Before leaving for work the next morning, he had invented an entirely new branch of mathematics called the calculus of variations, used it to solve the brachistochrone problem, and sent off the solution, published anonymously at Newton's request. But the work's brilliance and originality betrayed its author's identity. When Bernoulli saw the solution, he commented, "We recognize the lion by his claw." Newton had just turned 55 years old at the time. The concordance and calibration of the chronologies of ancient civilizations was the major intellectual pursuit he focused on during his final years. He did this in a manner that was very much in the tradition of the ancient historians Manetho, Strabo, and Eratosthenes. In his final posthumous work, The Chronology of Ancient Kingdoms Amended, we find repeated astronomical calibrations of historical events, an architectural reconstruction of the Temple of Solomon, a provocative claim that all of the Northern Hemisphere constellations are named after the personages, artifacts, and events in the Greek story of Jason and the Argonauts, and the consistent assumption that the gods of all civilizations, with the sole exception of Newton's own, were essentially the same. Kepler and Newton represent an important turning point in human history. This turning point is the realization that relatively straightforward mathematical laws govern all aspects of nature, that the same rules apply on Earth as they do in the heavens, and that there is a resonance between how humans think and how the world functions. They were unwavering in their commitment to the reliability of the observational data, and the accuracy of their forecasts regarding the movement of the planets provided compelling evidence that humans can comprehend the universe on an unexpectedly profound level. Their insights have significantly impacted our contemporary global civilization, our perspective of the world, and our ongoing investigation of the universe. Newton was secretive about his findings and cutthroatly competitive with his contemporaries in the scientific community. He didn't give a second thought to the fact that the inverse square law wouldn't be published for another decade or two after it was discovered. But in the face of the majesty and complexity of nature, he was, like Ptolemy and Kepler, both exhilarated and disarmingly modest. A few months before he passed away, he penned the following words: "I do not know what I may appear to the world, but to myself I seem to have been only like a boy, playing on the seashore and diverting myself now and then in finding a smoother pebbly or a prettier shell than ordinary, while the great ocean of truth lay all undiscovered before me. The earth is a beautiful and, for the most part, tranquil location. Things are shifting, but only gradually. We can live our entire lives without ever coming into direct contact with a natural disaster that is more severe than a storm. As a result, we start to feel comfortable, relaxed, and careless about the situation. But the record is crystal clear regarding the history of nature. The entire planet has been annihilated. Even we humans have attained the technically dubious distinction of being able to cause our own catastrophes, whether on purpose or dubious distinction. There is abundant evidence of major catastrophes on the landscapes of other planets where past records have been preserved. These are the landscapes. It is just a matter of time at this point. In 100 million years from now, something that is inconceivable happening in the next 100 years may be unavoidable. There have been strange natural occurrences on Earth and even in our own century. On June 30th, 1908, early in the morning, people in the central region of Siberia reported seeing a massive fireball traveling very quickly across the sky. An enormous explosion occurred exactly where it had made contact with the horizon. Near the point of impact, it started a flash fire that consumed thousands of trees and leveled approximately 2,000 square kilometers of forest land. It resulted in the production of an atmospheric shockwave that went around the planet twice. After that, there was such a high concentration of fine dust in the air for the next 2 days that people walking the streets of London, which is more than 6,000 miles away, could see well enough to read a newspaper by the light scattered by the dust. Because it had taken place in such a remote location among the backward Tungus people of Siberia, the government of Russia during the time of the Tsars was not interested in investigating such a meaningless event. After 10 years since the revolution, an expedition finally arrived to investigate the area and question the eyewitnesses. The following is a selection of the reports they brought back. The tent, along with its occupants, was lifted into the air at an early hour in the morning while everyone inside was still sound asleep. The impact of their fall caused everyone in the family to sustain some minor cuts and bruises. But Akulina and Ivan actually lost consciousness. As soon as they came to, they heard a great deal of noise and saw that the forest was on fire all around them, with a significant portion of it destroyed. At breakfast time, I was lounging on the porch of the house that served as the trading station in Vanovara and looking towards the direction of the north. I had just brought my axe up to my shoulder in preparation to hoop a cask when suddenly the sky appeared to be cut in half and high above the treetops. The entire northern portion of the sky gave the impression that it was on fire. At that precise instant, I had the impression that my shirt was on fire. I was about to take off my shirt and toss it when there was a loud explosion overhead, followed by the sound of something crashing to the ground with great force. I was knocked unconscious for a brief period of time after being thrown to the ground approximately 3 sageens away from the porch. My wife ran outside and brought me back inside on her back. Immediately after the impact, a sound sounded like stones falling from the sky or guns firing. When I lay down on the ground, I drew a blanket over my head out of nervousness that I would be struck by falling rocks. The earth was shaking. At that precise instant, when the clouds parted, a sweltering wind, like it had been fired from a cannon, blew past the huts coming from the direction of the north. The terrain bore the imprint of its passage. I was eating breakfast next to my plough when I heard loud bangs that sounded like they were coming from a gun. My horse was brought to its knees by this. A fire started on the northern slope, quickly spreading across the forest's canopy. After that, I noticed that the fir trees in the forest had been blown over, and I immediately thought of a hurricane. I reached out and grabbed hold of my plough with both hands to ensure it would not be lost. The hurricane caused a wall of water to be driven up the Angara, and the wind was so powerful that it carried away some of the soil on the ground surface. Because my land was on a hillside, I could see everything clearly. The horses were so frightened by the roar that some ran away in a frenzy, dragging the ploughs in various directions while others became incapacitated and collapsed. The carpenters had crossed themselves in a stupor after the first and second explosions, and when the third explosion resounded, they fell backwards from the building onto the chips of wood below. I needed to reassure them and bring some back to composure because they were startled and terrified. There, we all quit. Our large groups of local residents were seen congregating in the streets in fear and talking about the phenomenon that had occurred there. I was out in the countryside. I had just begun to attach another horse to the harrow when all of a sudden I heard what sounded like a single loud shot coming from the right. I had just finished harnessing one horse to the harrow. Instantaneously, I turned around and saw an elongated object that was ablaze and flying through the sky. Its color resembled fire during the daytime, and the front portion was significantly broader than the back portion of the creature. It was so much fainter compared to the sun that people could look at it with their bare eyes, even though it was much larger than the sun. Something that looked like dust was trailing behind the flames. It was encircled by a ring of little puffs, and the flames had left behind blue streamers as they died out. As soon as the flame went out, bangs that were even louder than the shots from a gun could be heard, the ground could be felt to shake, and the window panes in the cabin shattered. I was sitting on the bank of the River Can, washing wool at the time. Suddenly a sound that sounded like the frantic flapping of wings by a scared bird came into the room, and the river began to experience some swell. Following this, a single severe bang was so loud that one of the workers was knocked into the water. The remarkable occurrence in Tunguska is known as the Tunguska event. Some researchers believe that it was caused by a piece of antimatter that hurtled through space and made contact with the ordinary matter of the Earth. As a result, the antimatter was destroyed and vanished in a burst of gamma rays. This explanation, however, is not supported by the fact that there was no radioactivity at the site of the impact. Others hypothesize that a miniature black hole exited the other side of the Earth in Siberia after passing through the planet. However, there is no indication of an object that boomed out of the North Atlantic later that day in the records of atmospheric shockwaves. It's possible that it was a spaceship from an extraterrestrial civilization that was so technologically advanced that it crashed into an inaccessible part of an unknown planet due to a catastrophic mechanical failure. However, no indication of such a vessel having been present at the point of impact exists. Every one of these suggestions has been made, some of them in a more serious light than others. There is not a single one of them that the evidence strongly supports. The Tunguska event is best understood because there was an enormous explosion, a significant shockwave, and a massive forest fire. However, there is no evidence of an impact crater at the location. It would appear that there is only one explanation that can make sense of all of the facts. In 1908, a piece of a comet collided with the Earth. In the vast voids between the planets, there are a great number of objects, some of which are made of rock, some of which are made of metal, some of which are made of ice, and some of which are composed of organic molecules. They can be as small as individual dust particles or as large as erratic blocks the size of Nicaragua or Bhutan. And every once in a while, it just so happens that there is a planet in the way. An ice fragment of a comet measuring approximately 100 meters in diameter, or the size of a football pitch, weighing approximately 1 million tons and moving at approximately 30 kilometers per second, or 70,000 miles per hour, is believed to have been the cause of the Tunguska event. In this day and age, if such a collision were to occur, it is possible to be misunderstood as a nuclear explosion, especially given the hysteria that would ensue. The cometary impact and fireball would simulate all of the effects of a 1 megaton nuclear burst, including the mushroom cloud, with the following two exceptions. There would be no gamma radiation and no radioactive fallout. Could a natural but extremely unlikely occurrence, such as the collision of a sizable cometary fragment, set off a nuclear war? Imagine this bizarre scenario. The Earth is struck by a comet, one of the millions that have done so in the past, and in response our society decides to immediately destroy itself. It is possible that it would be beneficial for us to better understand comets, collisions, and disasters than we currently do. On September 22, 1979, a US Vela satellite picked up on a particularly bright and brief double flash of light coming from somewhere in the early theories suggested that either Israel or South Africa had conducted a covert nuclear test using a weapon with a low yield, 2 kilotons or approximately a sixth of the energy of the Hiroshima bomb. The political repercussions were regarded as having significant gravity across the globe. But what if the flashes were caused by the collision of a comet fragment or a small asteroid instead? This is a real possibility, and it highlights the dangers of not monitoring impacts from space better than we do in an age when nuclear weapons exist, as airborne overflights in the vicinity of the flashes showed no trace of unusual radioactivity in the air. The majority of a comet is composed of ice, specifically water, H2O ice, along with a small amount of methane, CH4 ice, and some ammonia, NH3 ice. When it collided with the atmosphere of Earth, even a small fragment of a comet would cause an enormous radiant fireball and a powerful blast wave. This wave would cause trees and forests to be leveled and could be heard all over the world. However, it is possible that it will not leave much of a crater in the ground. The entrance would result in the complete melting of the ice. Very few pieces of the comet could be recognized, possibly just a scattering of small grains originating from the cometary nucleus's non-icy parts. Recent research by the Soviet scientist E. Sobotovich discovered a significant quantity of incredibly minute diamonds scattered across the Tunguska site. It is already well established that such diamonds exist in meteorites that have withstood the force of impact, and that these meteorites may ultimately have originated from comets. If you wait patiently and look up at the sky on a clear night, you will see a single meteor blazing briefly overhead. This will happen on many nights. A meteor shower is a natural fireworks display on the same few days yearly. It is also known as an entertainment show in the heavens. These meteors are composed of extremely minute grains, each of which is no bigger than a mustard seed. They are more like falling fluff than exploding shooting stars. When they enter the atmosphere of the Earth, they have a brief moment of brilliance before being heated and destroyed by friction at a height of approximately 100 kilometers. Comets break up into pieces that eventually become meteors. Comets that have been around for a long time tend to disintegrate and evaporate as a result of repeated encounters with the sun's heat. The debris grows and eventually fills up the entire cometary orbit. At the point where the path of that orbit crosses the path of the Earth's orbit, there is a cloud of meteors waiting for us. Because some portion of the swarm is always at the same position in the Earth's orbit, the meteor shower is always observed on the same day of the year. This ensures that the shower can be reliably predicted. The Beta Taurid meteor shower occurred on June 30, 1908, and was associated with the orbit of Comet Encke. A piece of Comet Encke was responsible for the Tunguska event. This piece of the comet was significantly larger than the minuscule fragments responsible for the dazzling but harmless meteor showers. Fear, awe, and superstition have always been associated with comets. The concept of an unchangeable and divinely ordered cosmos was questioned when they made occasional appearances, which was unsettling. It seemed inconceivable that a magnificent swath of milk-white flame, which rose and set with the stars night after night, was not present for a purpose, and did not hold some significance for the affairs of humankind. As a result, the concept emerged that comets were portents of doom, indications of the wrath of a higher power, and that they predicted the demise of princes and the dissolution of kingdoms. The Babylonians believed that comets were the beards of the gods in the heavens. The Greeks envisioned long, flowing hair, while the Arabs envisioned swords on fire. Comets were meticulously categorized during the time of Ptolemy as beams, trumpets, jars, and so on, according to their shapes. Ptolemy believed that comets caused wars, hot weather, and disturbed conditions. Some depictions of comets from the Middle Ages look like unidentified flying crucifixes. Andreas Calicius, a Lutheran superintendent or bishop of Magdeburg, published in 1578 a work titled Theological Reminder of the New Comet, in which he presented the inspired view that a comet is the thick smoke of human sins, rising every day, every hour, every moment, full of stench and horror before the face of God, and becoming gradually so thick as to form a comet. The oldest record of an apparition of Halley's or any other comet appears in the Chinese book of Prince Huainan, attendant to the march of King Wu against Zhou of Yin. The year was 1057 BC. The approach to Earth of Halley's comet in the year 66 is the probable explanation of the account by Josephus of a sword that hung over Jerusalem for a whole year. In 1066, the Normans witnessed another return of Halley's comet, since it must, they thought, presage the fall of some kingdom. The comet encouraged, in some sense precipitating, the invasion of England by William the Conqueror. The comet was duly noted in the newspaper of the time, the Bayeux Tapestry. In 1301, Giotto, one of the founders of modern realistic painting, witnessed another apparition of Comet Halley and inserted it into a nativity scene. The Great Comet of 1466, yet another return of Halley's comet, panicked Christian Europe. The Christians feared that God, who sends comets, might be on the side of the Turks, who had just captured Constantinople. The leading astronomers of the 16th and 17th centuries were fascinated by comets, and even Newton became a little giddy over them. Kepler described comets as darting through space, as the fishes in the sea, but being dissipated by sunlight, as the cometary tail always points away from the sun. David Hume, in many cases an uncompromising rationalist, at least toyed with the notion that comets were the reproductive cells, the eggs or sperm, of planetary systems, and that planets are produced by a kind of interstellar sex. As an undergraduate, before he invented the reflecting telescope, Newton spent many consecutive sleepless nights searching the sky for comets with his naked eye, pursuing them with such fervor that he felt ill from exhaustion. Following Tycho and Kepler, Newton concluded that the comets seen from Earth do not move within our atmosphere as Aristotle and others had thought, but rather are more distant than the Moon, although closer than Saturn. Comets shine, as the planets do, by reflected sunlight. And they are much mistaken who remove them almost as far as the fixed stars. For if it were so, the comets could receive no more light from our sun than our planets do from the fixed stars. This demystification, this prediction of regular cometary orbits, led his friend Edmund Halley in 1707 to calculate that the comets of 1531, 1607, and 1682 were apparitions at 76-year intervals of the same comet, and predict its return in 1758. The comet duly arrived and was named for him posthumously. Comet Halley has played an interesting role in the solar system's history. Planetary scientists of today sometimes argue that the impact of a comet on a planet might significantly contribute to the planetary atmosphere. For instance, all of the water in the atmosphere of Mars today might be accounted for by the recent impact of a small comet. Newton observed that the matter in the tails of comets is lost to the comet and gradually attracted gravitationally to nearby planets. If they are not supplied from outside, the fluids must be in a continual decline and completely run out in the end, if there is no external supply. Newton appears to have believed that the oceans on Earth originated from comets, and that the only reason life can exist on Earth is because cometary material falls to the planet's surface. He went on to say this in a mystical musing, "I suspect, moreover, that it is chiefly from the comets that spirit comes," which is indeed the smallest but the most subtle and useful part of our air and so much required to sustain the life of all things with us. This was said in the context of his belief that comets were the primary source of spirit. Huggins had found organic matter in the comets. In subsequent years, cyanogen, CN, consisting of a carbon and a nitrogen atom, the molecular fragment that makes cyanides, was identified in the tails of comets. Many people panicked when the Earth was about to pass through the tail of Halley's Comet in 1910. Huggins found an identity between some features in the spectrum of a comet and the spectrum of natural, or olefiant, gas. But that didn't put anyone's mind at ease. For instance, on May 15, 1910, the San Francisco Chronicle featured headlines such as "Comet Camera as Big as a House," "Comet Comes and Husband Reforms," and "Comet Parties Now Fad in New York." In 1910, there were parties making merry before the world ended due to cyanogen pollution. Entrepreneurs hawked anti-comet pills and gas masks, the latter being an eerie. The Los Angeles Examiner adopted a light mood. "Say, has that comet cyanogened you yet? Entire human race. Due for free gaseous bath. Expect high jinx." In 1957, I was a graduate student at the Yerkes Observatory at the University of Chicago. Alone in the observatory late one night, I heard the telephone ring repeatedly. When I answered, a voice, betraying a well-advanced state of intoxication, said, "Let's talk to a strainer. Can I help you?" "Well, see, we're having this garden party out here in Wilmette, and there's something in the sky. The funny part is that if you look straight at it, it goes away. But if you don't look at it, there it is. The most sensitive part of the retina is not at the center of the field of view. You can see faint stars and other objects by averting your vision slightly." I knew that a newly discovered comet called Arend-Roland was barely visible in the sky at this time, so I told him that he was probably looking at a comet. There was a long pause, followed by the query, "What is a comet?" "A comet," I replied, "is a snowball 1 mile across." After an extended pause, the caller asked, "Let's talk to a real strainer." And the conversation continued there. When Halley's Comet made its next appearance in 1986, I couldn't help but wonder which political leaders would be shaken by the event, and what other foolishness would befall us at that time. Even though the planets travel in elliptical orbits around the Sun, the ellipses in which they travel are not very elliptical. At first glance, it is difficult to tell them apart from circles because they are nearly identical in appearance. It is the comets, and more specifically the comets with long periods, that have extremely elliptical orbits. The comets are the newcomers to the inner solar system, while the planets have been around for a long time. Why are the orbits of the planets almost perfectly circular? And why are they so well separated from one another? Because if planets traveled in extremely elliptical orbits, their paths would eventually cross one another, which would inevitably lead to a collision. There were most likely a great number of planets that were still in the process of forming in the early days of the solar system. Those with orbits that crossed each other in an elliptical pattern were more likely to crash into each other and destroy themselves. Those with more circular orbits were more likely to thrive and endure. The current orbits of the planets were established by the planets that managed to survive the collisional natural selection that occurred during the stable middle age of a solar system dominated by early catastrophic impacts. A vast spherical cloud of 1 trillion cometary nuclei orbits the Sun at a speed comparable to that of a racing car at the Indianapolis 500. This cloud is located far beyond the planets in the most distant part of the solar system. A fairly typical comet would resemble a giant snowball that is rolling around about 1 kilometer in diameter. The majority of them are never able to cross the boundary that is denoted by Pluto's orbit. However, on rare occasions, a passing star will cause a gravitational flurry and commotion in the cometary cloud. As a result, a group of comets will find themselves in highly elliptical orbits and begin their descent towards the Sun. After having its trajectory altered even further by the gravitational pull of Jupiter or Saturn, the comet has a habit of, on average, speeding towards the inner solar system once every century or so. It would start heating up and evaporating somewhere between the orbits of Jupiter and Mars. Fragments of dust and ice are carried back behind the comet by the solar wind, which is matter blown outwards from the Sun's atmosphere. This is the beginning of the comet's tail. If Jupiter were only 1 meter across, our comet would be no bigger than a speck of dust. However, once it reached its full potential, the comet's tail would be as long as the distance between the worlds. Each of its orbits around the Sun would cause people living on Earth to behave in superstition whenever they could catch a glimpse of the planet. But in time, they would realize that it did not live in their atmosphere, but rather among the other planets in the galaxy. They would figure out the trajectory of its orbit. And who knows, maybe in the not-too-distant future, they will send a rudimentary spacecraft hurtling through space, specifically designed to investigate this traveler from the realm of the stars. Comets and planets are bound to run into the Earth and its satellite, the Moon, must endure constant barrages from comets and other minor asteroids, remnants from the process of assembling the solar system. There should be more impacts caused by smaller objects than by larger ones because there are more small objects than large ones. An impact of a small cometary fragment with the Earth, such as the one at Tunguska, should occur approximately once every 1,000 years. On the other hand, a collision with a large comet like Halley's Comet, whose nucleus is possibly 20 kilometers across, should only occur about once every billion years. It's possible that a small, icy object won't leave a significant scar on a planet or moon if it has a collision with one of those bodies. But if the object impacting is either more massive or primarily composed of rock, there will be an explosion that will carve out a bowl-shaped depression known as an impact crater. And if there is no process that smooths out the crater or fills it in, it may remain there for billions of years. When we examine the surface of the Moon, we find that it is covered with impact craters, many more than can be accounted for by the sparse population of cometary and asteroid debris that now fills the inner solar system. This is because almost no erosion takes place on the Moon. And when we do examine its surface, we find that it is almost entirely made up of impact craters. The lunar surface provides eloquent testimony of a previous age in which the destruction of worlds occurred, which has now been gone for billions of years. There are impact craters all over the solar system, not just on the Moon. They are found throughout the inner solar system, from Mercury, the planet closest to the Sun, to Venus, which is covered in clouds, to Mars and its 2 very small moons, Phobos and Deimos. These are the planets in our solar system's family of worlds known as the terrestrial planets. They are the planets that are most comparable to Earth. They have solid surfaces, rock and iron interiors, and atmospheres ranging from almost a complete vacuum to pressures that are 90 times higher than the pressure on Earth. They congregate around the Sun, providing light and warmth like campers do around a fire. About 4.6 billion years have passed since the planets formed. They all provide evidence, just like the Moon does, that the solar system's early history was marked by catastrophic impact. After we pass Mars, we enter a very different regime, the realm of Jupiter and the other giant or Jovian planets. This is where we will spend the rest of our time. These are enormous worlds predominantly made up of hydrogen and helium, along with smaller amounts of other hydrogen-rich gases and liquids like methane, ammonia, and water. Here, all we can see is the atmosphere and various cloud types. No solid surfaces can be seen. These are significant planets, not insignificant worldlets like our own planet Earth. Jupiter's interior has enough room to accommodate 1,000 Earths. If a comet or an asteroid were to enter Jupiter's atmosphere, we would not anticipate the formation of a visible crater. Rather, we would anticipate a momentary break in the clouds. Despite this, we know there has been a history of collisions in the solar system's outer reaches dating back many billions of years. This is because Jupiter has a vast system consisting of more than a dozen moons, 5 of which were investigated in greater detail by the Voyager spacecraft. Once more, we discover evidence of past catastrophic events here. When the entirety of the solar system has been explored, we will likely find evidence of an impact catastrophe on each of the 9 planets, ranging from Mercury to Pluto, as well as on all of the smaller moons, comets, and asteroids. On the side of the moon that is closest to Earth and can be viewed through telescopes here on Earth, there are approximately 10,000 craters. Most of them are in the ancient lunar highlands and date back to when the moon was formed from the last accretion of material from space debris. In the Maria, Latin for seas, which are lowland regions that were flooded, possibly by lava shortly after the moon's formation, covering the pre-existing craters, there are approximately 1,000 craters larger than a kilometer across. Therefore, craters on the moon should be formed today at approximately 109 years per 104 craters, 105 years per crater, or 100,000 years between cratering events. This estimate, we may have to wait even longer than 100,000 years before we see a crater form on the moon, because there may have been more interplanetary debris a few billion years ago than there is today. If this is the case, we will need to be patient. As a result of the Earth's larger surface area compared to that of the moon, we may have to wait somewhere in the neighborhood of 10,000 years between collisions that would create craters on our planet that are as large as a kilometer across. Considering that the age of the Meteor crater in Arizona, an impact crater approximately 1 kilometer in diameter, has been determined to be between 20 and 30,000 years old, the observations made on Earth agree with such crude calculations. The actual collision of a small comet or asteroid with the moon could produce a momentary explosion that is bright enough to be seen from Earth. We can imagine our ancestors gazing up into the night sky on some night 100,000 years ago and noticing a peculiar cloud rising from the portion of the moon that was not illuminated by the sun when it was suddenly struck by the sun's rays. This cloud was known as the lunar eclipse. But we would not have anticipated that such a thing would have occurred during historical times. The likelihood of that happening is probably less than 1 in 100 at this point. On the evening of June 25th, 1178, 5 British monks reported something extraordinary, which was later recorded in the Chronicle of Gervase of Canterbury, who was generally considered a reliable reporter on the political and cultural events of his time, after he had interviewed the eyewitnesses who asserted, under oath, the truth of their story. This is how the chronicle goes. There was a brilliant new moon, and as is customary for the moon when it is in that phase, its horns were angled in the direction of the east. The upper horn separated into 2 pieces all of a sudden. A torch that was ablaze and emitting flames, sparks, and hot coals suddenly emerged from the point in the middle of the division. Astronomers Derrell Mulholland and Odile Calamé have calculated that a lunar impact would produce a dust cloud rising off the moon's surface, with an appearance that corresponds rather closely to the report of the Canterbury monks. This finding was possible because a lunar impact would produce a dust cloud rising off the moon's surface. If such a collision occurred 800 years ago, the crater should still be visible today. Even relatively young craters on the moon, ranging from a few billion to tens of billions of years, have retained a high degree of their original structure. This is because there is neither air nor water on the moon. Using the description recorded by Gervase, it is possible to zero in on the moon region to which the observations refer. The explosion creates rays and linear trails of fine powder spewed out, and the impacts produce these rays and trails. These rays are connected to the youngest craters on the moon, such as the ones named after Aristarchus, Copernicus, and Kepler. On the moon, the craters may withstand the effects of erosion, but the moon's extremely thin rays do not. Even the arrival of micrometeorites, tiny dust particles that originate in space, can stir up and cover up the rays, eventually leading to their disappearance. Consequently, rays are the telltale sign of a recent impact. Jack Hartung, a meteoriticist, has pointed out that the moon region referred to by the Canterbury monks contains an extremely recent, very fresh-looking small crater with a prominent ray system. Hartung also noted that this crater has a prominent ray system. It was given the name Giordano Bruno in honor of the Roman Catholic scholar Giordano Bruno, who lived in the 16th century and proposed that there is an infinite number of worlds, many inhabited. In 1600, he was killed by being skewered and burned at the stake for these and other offences. Calamé and Mulholland have provided yet another line of evidence that can be interpreted consistently with this interpretation. A moon struck by an object travelling at high speed causes the moon to tremble ever so slightly. The vibrations will stop occurring at some point in the future, but this will not happen within the next 800 years. The techniques of laser reflection allow for the study of this quivering. Laser retroreflectors are specialized mirrors that the Apollo astronauts placed across the laser beam emanating from Earth hits a mirror and then bounces back. It is possible to measure the round-trip travel time with extraordinary accuracy. This time, multiplied by the speed of light, estimates the distance to the moon at that precise moment. The accuracy of this estimate is truly remarkable. Such measurements, carried out over several years, reveal that the moon is librating or quivering with a period, approximately 3 years, and an amplitude, approximately 3 meters. This finding is consistent with the hypothesis that the crater Giordano Bruno was excavated in the last 1,000 years. This entire body of evidence is inferential and circumstantial. As I've mentioned, the chances of such an occurrence occurring in historical times are extremely low. However, there is at least some evidence that points in that direction. The Tunguska event and the meteor crater in Arizona serve as reminders that the early history of the solar system was not the only period in which catastrophic impacts occurred. Even on the moon, some erosion occurs because only a few lunar craters have extensive ray systems. This fact, however, serves as a reminder that erosion takes place. We can reconstruct the sequence of impact and flooding events on the moon by paying attention to which craters overlap, which others and other signs of lunar stratigraphy. The formation of the crater Bruno is perhaps the most recent example of this event. On this page, you will find an attempt to visualize the processes that resulted in the surface of the lunar hemisphere that is visible from Earth. The distance between the Earth and the Moon is not great. If the Moon is covered in craters to such a severe extent, how has the Earth managed to avoid them? What are the odds of coming across a meteor crater? Do comets and asteroids believe colliding with a planet with people on it would be dangerous? This kind of indulgence is highly improbable. The only explanation that makes sense is that impact craters are formed at similar rates on Earth and the Moon. However, because there is no air or water on the Moon, the craters can remain intact for extremely long periods, whereas on Earth, slow erosion causes the craters to disappear or become filled in. The processes of running water, sand being blown by the wind, and the formation of mountains all take a very long time. However, they can completely remove even the most significant impact scars throughout millions or even billions of years. There will be fast, catastrophic events such as volcanic explosions and processes of excruciating slowness, such as the pitting of a surface by tiny airborne sand grains. These processes will occur on the surface of any moon or planet. It is impossible to provide a definitive response to the question of which processes predominate. Those that take place on the outside or those that take place on the inside. Extraordinary but infrequent occurrences, or everyday but unremarkable ones. On the Moon, catastrophic events reign supreme, whereas slow processes rule the day on Earth. Mars is a case that falls somewhere in the middle. Numerous asteroids, essentially miniature terrestrial planets, can be found in the region between the orbits of Mars and Jupiter. The largest ones have a diameter of a few hundred kilometers. Many of them tumble through space and have shapes that resemble long rectangles. It would appear that at least 2 asteroids are traveling in close orbit around one another in certain instances. A meteorite is a rock created when an object in space, known as an asteroid, collides with another asteroid and breaks apart, sending fragments hurtling through space before hitting the surface of the Earth. Fragments of other worlds can be displayed as artifacts and art in our museums. The asteroid belt is like a giant grinding mill, producing ever-increasingly smaller pieces down to dust particles. The more substantial chunks of asteroids and comets are primarily to blame for the recent craters that have appeared on the surfaces of planets. The asteroid belt may be the shattered remnants of a planet that blew itself up, or it may have been a location in the past, where the gravitational tides of the nearby giant Jupiter prevented the formation of a planet at that location. Both of these possibilities are possible. This seems unlikely because no scientist on Earth knows a mechanism by which a planet could destroy itself, which is probably for the best. The rings of Saturn have been compared to the asteroid belt because of the vast number of extremely small the remains of a moon that strayed too close to Saturn and was ripped apart by the gravitational tides. Or they could be debris that was prevented by Saturn's gravity from accreting into a nearby moon. Either way, they could be interesting. Alternately, they may result from a stable equilibrium between the material that is ejected from one of Saturn's moons, such as Titan, and the material that falls into the planet's atmosphere. The ring systems of Jupiter and Uranus were discovered not too long ago, and are so distant from Earth that we can barely see them. The question of whether or not Neptune possesses a ring is very important to planetary scientists. There is a possibility that planets of the Jupiter type all over the cosmos will have rings surrounding them. An influential book titled Worlds in Collision was written by a psychiatrist named Emanuel Velikovsky and first released in 1950. The book claims that major recent collisions have occurred between Saturn and Venus. He hypothesized that the Jupiter system was responsible for forming an object with the mass of a planet that he referred to as a comet. Around 3,500 years ago, it careened in towards the inner solar system and made repeated encounters with the Earth and Mars. As a result of these encounters, the Red Sea parted, Moses and the Israelites were able to flee from Pharaoh, and Joshua was able to stop the Earth from rotating on command. All of these events are considered to be coincidental events. According to him, it was also the cause of widespread volcanism and flooding. Velikovsky imagined that after a difficult game of interplanetary billiards, the comet would eventually settle down into a stable, nearly circular orbit, eventually becoming the planet Venus, which he claimed had never existed before that time. These ideas are almost certainly incorrect, as I have discussed in some other places in greater detail. Astronomers do not take issue with the concept of major collisions. Rather, they take issue with major collisions that have occurred recently. Because of this, no solar system model can show the planets' sizes on the same scale as their orbits. If this were done, the planets would be so small that they would be difficult to see. If the planets were shown to scale as dust grains, it would be easy to see that the probability of a specific comet colliding with Earth within the next few thousand years is extremely low. This would be the case because the planets would be shown to scale as dust grains. In addition, Venus is a rocky and metallic planet with very little hydrogen, whereas Jupiter, where Velikovsky believed it originated, is almost entirely composed of hydrogen. There are no sources of energy for Jupiter to use in its process of ejecting comets or planets from its system. If one were to pass by the Earth, one would not be able to stop the rotation of the Earth, much less begin it again at the appropriate rate of 24 hours per day. No evidence from geology supports the idea that there was an unusually high frequency of volcanic activity or floods 3,500 years ago. Inscriptions found in Mesopotamia that reference Venus date back to a time before Velikovsky's contention that Venus transitioned from the status of a comet to that of a planet. It is improbable that an object that was previously traveling in a highly elliptical orbit could have been rapidly moved into the nearly perfectly circular orbit of modern-day Venus. And this goes on. It turns out that many hypotheses, both those put forward by scientists and those put forward by non-scientists, are incorrect. However, the scientific method is capable of correcting its own errors. To be considered, novel concepts need to conform to stringent evidence requirements. The most upsetting aspect of the Velikovsky affair is not that his hypotheses were incorrect or ran counter to well-established facts. Rather, The most upsetting aspect is that some individuals who called themselves scientists attempted to suppress Velikovsky's work. The scientific method is based on the principle of free inquiry, which holds that every hypothesis should be evaluated based on its merits regardless of how outlandish it may seem. Suppressing unsettling ideas may be a common practice in religion and politics, but it is not the way to knowledge and has no place in pursuing scientific knowledge. There is no way to predict who will come up. Venus is almost identical to the Earth in terms of its mass, size, and density. Since it is the planet closest to Earth, people have considered it as Earth's sister for centuries. What is the nature of the planet that is our sister? It may enjoy a balmy summer climate, slightly warmer than Earth due to its proximity to the Sun. Does it still have impact craters, or have they been completely worn away by erosion? Is there a volcano nearby? Surely, you jest. The oceans, life. In 1609, Galileo was the first to look through a telescope and observe Venus. He saw a disk that had no distinguishing characteristics whatsoever. We are sometimes looking mostly at the night side of Venus and sometimes at the day side, a finding that incidentally reinforced the view that the Earth went around the Sun, and not vice versa. Galileo observed that it went through phases, similar to the Moon, from a thin crescent to a full disk, and for the same reason we are sometimes looking mostly at the night side of Venus, and sometimes mostly at the day side. As optical telescopes grew in size and resolution, their capacity to differentiate between fine details increased. Scientists began systematically pointing them in the direction of Venus. However, their results were not any more accurate than Galileo's. At first glance, Venus appeared shrouded in a thick blanket of opaque clouds. When we look at the planet during the early morning or late evening hours, we see the sunlight reflected off Venus's clouds. However, despite their discovery hundreds of years ago, the makeup of those clouds remained a complete mystery for centuries. As a result of the dearth of visible features on Venus, several researchers came to the intriguing conclusion that the planet's surface was a swamp, just like it was during the Carboniferous period on Earth. If we may use such a word to describe what transpired, the debate went something like this. I can't see anything on Venus. Why is that? Because there is a complete blanket of clouds over it. What exactly is it that clouds are made of? Water, of course, she replied. If this is the case, why are the clouds on Venus so much thicker than those on Earth? The answer is that there is more water on Venus. However, if there is more water in the clouds, more water must be on the surface. What kinds of ground are considered to be very wet? Wetlands, swamps. And if there are swamps, why not cycads, dragonflies, and even dinosaurs on Venus? The featureless clouds of Venus reflected our own predispositions. We are alive, and we resonate with the idea of life elsewhere. However, only careful accumulation and assessment of the evidence can tell us whether or not a given world is inhabited. The first real clue to the nature of Venus came from work with a prism made of glass or a flat surface, called a diffraction grating, covered with fine, regularly spaced, ruled lines. When an intense beam of ordinary white light passes through a narrow slit and then through a prism or grating, it is spread into a rainbow of colors called a spectrum. The spectrum runs from high frequencies of visible light to low ones: violet, blue, green, yellow, orange, and red. Since we see these colors, it is called the visible light spectrum. But we can see far more light than the small spectrum segment. At higher frequencies, beyond the violet, is a part of the spectrum called the ultraviolet, a perfectly real kind of light that carries death to the microbes. It is invisible to us but readily detectable by bumblebees and photoelectric cells. There is much more to the world than we can see. Beyond the ultraviolet is the X-ray part of the spectrum, and beyond the X-rays are the gamma rays. At lower frequencies on the other side of red is the infrared part of the spectrum. It was first discovered by placing a sensitive thermometer in what, to our eyes, is the dark beyond the red. The temperature rose. The light was falling on the thermometer, even though it was invisible to our eyes. Rattlesnakes and doped semiconductors detect infrared radiation perfectly well. Beyond the infrared is the vast spectral region of radio waves. From gamma rays to radio waves, all are equally respectable light brands. All are useful in astronomy. But because of the limitations of our eyes, we have a prejudice, a bias, towards that tiny rainbow band we call the spectrum of visible light. In 1844, the philosopher Auguste Comte searched for an composition of distant stars and planets. He thought we would never physically visit them, and with no sample in hand, it seemed we would forever be denied knowledge of their composition. But only 3 years after Comte's death, it was discovered that a spectrum could be used to determine the chemistry of distant objects. Different molecules and chemical elements absorb different frequencies or colors of light, sometimes in the visible spectrum and elsewhere. In the spectrum of a planetary atmosphere, a single dark line represents an image of the slit in which light is missing, the absorption of sunlight during its brief passage through the air of another world. Each such line is made of a particular kind of molecule or atom. Every substance has its own characteristic spectral signature. The gases on Venus can be identified from the Earth 60 million kilometers away. We can divine the composition of the Sun, in which helium, named after the Greek sun god Helios, was first found. Of magnetic stars rich in europium, and of distant galaxies through the collective light of 100 billion constituent stars. Astronomical spectroscopy is an almost magical technique. It still amazes me. Auguste Comte picked a particularly unfortunate example. If Venus were soaking wet, it should be easy to see the water vapor lines in its spectrum. But the first spectroscopic searches attempted at Mount Wilson Observatory around 1920 found no hint or trace of water vapor above the clouds of Venus, suggesting an arid, desert-like surface surmounted by clouds of fine, drifting silicate dust. Further study revealed enormous quantities of carbon dioxide in the atmosphere, implying to some scientists that all the water on the planet had combined with hydrocarbons to form carbon dioxide, and that, therefore, the surface of Venus was a global oil field, a planet-wide sea of petroleum. Others concluded that there was no water vapor above the clouds because the clouds were very cold, and all the water had condensed out into water droplets, which do not have the same pattern of spectral lines as water vapor. They suggested that the planet was covered with water, except perhaps for an occasional limestone-encrusted island, like the cliffs of Dover. But because of the vast quantities of carbon dioxide in the atmosphere, the sea could not be ordinary water. Physical chemistry required carbonated water. Venus, they proposed, had a vast ocean of seltzer. The first hint of the true situation came not from spectroscopic studies in the visible or near-infrared parts of the spectrum, but rather from the radio region. A radio telescope works more like a light meter than a camera. You point it towards some fairly broad region of the sky, and it records how much energy at a particular radio frequency is coming down to Earth. We are used to radio signals transmitted by some varieties of intelligent life, namely, those who run radio and television stations. But there are many other reasons for natural objects to give off radio waves. One is that they are hot. And when, in 1956, an early radio telescope was turned towards Venus, it was discovered to be emitting radio waves as if it were at an extremely high temperature. But the real demonstration that the surface of Venus is astonishingly hot came when the Soviet spacecraft of the Venera series first penetrated the obscuring clouds and landed on the mysterious and inaccessible surface of the nearest planet. Venus, it turns out, is broiling hot. There are no swamps, no oil fields, and no seltzer oceans. With insufficient data, it is easy to go wrong. When I greet a friend, I see her in reflected visible light generated by the sun or an incandescent lamp. The light rays bounce off my friend and into my eye. But the ancients, including no less a figure than Euclid, believed that we see by rays somehow emitted by the eye and tangibly actively contacting the object observed. This is a natural notion, and can still be encountered, although it does not account for the invisibility of objects in a darkened room. Today, we combine a laser and a photocell, or a radar transmitter and a radio telescope. In this way, we make active contact by light with distant objects. In radar astronomy, radio waves are transmitted by a telescope on Earth. Strike, say, that hemisphere of Venus that happens to be facing the Earth, and bounce back. At many wavelengths, the clouds and atmosphere of Venus are entirely transparent. Will absorb them or, if very rough, will scatter them sideways, appearing dark to radio waves. By following the surface features moving with Venus as it rotates, it was possible for the first time to reliably determine the length of its day, how long it takes Venus to spin once on its axis. It turns out that, concerning the stars, Venus turns once every 243 Earth days, but backwards, in the opposite direction from all other planets in the inner solar system. As a result, the Sun rises in the west and sets in the east, taking 118 Earth days from sunrise to sunset. Moreover, it presents almost exactly the same face to the Earth each time it is closest to our planet. However, since the Earth's gravity has managed to nudge Venus into this Earth-locked rotation rate, it cannot have happened rapidly. Venus could not be a mere few thousand years old. Rather, it must be as old as all the other objects in the inner solar system. There are just as many craters, not too big or too small, on Venus as in the lunar highlands, so many that Venus is again telling us that it is very old. However, the craters of Venus are remarkably shallow, almost as if the high surface temperatures have resulted in the formation of lava flows rather than craters. This suggests that Venus may have been formed by a collision between two smaller bodies. The surface temperatures on Venus are approximately 400 meton or 900 Celsius, which is hotter than the hottest household oven. The corresponding surface pressure is 90 atmospheres, which is 90 times the pressure we feel from the Earth's atmosphere, and is equivalent to the weight of water 1 kilometer below the surface of the oceans. To survive for an extended period on Venus, a space vehicle would need to be refrigerated and built like a pressure cooker. Let us follow in the footsteps of these pioneering missions and travel to another world. Roughly a dozen spacecraft from the United States and the Soviet Union have broken through the clouds and entered the dense atmosphere of Venus. Some of these spacecraft have survived for up to an hour or so on the surface of Venus. 2 spacecraft from the Soviet Venera series have taken pictures down there. If the cameras look in the ultraviolet, however, we see a graceful, complex, swirling weather system in the high atmosphere, where the winds are around 100 meters per second, or about 220 miles per hour. The atmosphere of Venus is composed of 96% carbon dioxide. Small traces of nitrogen, water vapor, argon, and helium exist. Galileo was the first person to note that the clouds of Venus show virtually no features at all. In the lower atmosphere, the odorous gas sulfur dioxide, SSO2, is present in trace amounts. It is circulated above the clouds, broken down by ultraviolet light from the sun, and recycled. At about 70 kilometers of altitude, there is a continuous haze of small particles. At 60 kilometers, we plunge into the clouds and find ourselves surrounded by droplets of concentrated sulfuric acid. There is no dust, no clouds, just an atmosphere getting palpably denser. The sulfur-colored M-mist extends downward to some 45 kilometers above the surface of Venus, where we emerge into a dense but crystal-clear atmosphere. However, the atmospheric pressure is so high that we cannot see the surface of Venus. With sweltering temperatures, crushing pressures, toxic gases, and everything bathed in an eerie, reddish glow, Venus seems less like the goddess of love and more like the incarnation of hell. The hostile, barren landscape is relieved only here and there by the eroded remnants of a derelict spacecraft from a distant planet, which are completely invisible through the thick, cloudy, poisonous atmosphere. Venus is a kind of planet-wide catastrophe. It is now reasonably clear that the high surface temperature is brought about by a massive greenhouse effect. Sunlight passes through the atmosphere and clouds of Venus, which are semi-transparent to visible light, and reaches the surface. Spectrum. However, the carbon dioxide and water vapor in the atmosphere of Venus are almost perfectly opaque to infrared radiation. As a result, the sun's heat is effectively trapped, and the surface temperature rises. This continues until the small amount of infrared radiation that trickles out of this massive atmosphere balances the amount of sunlight absorbed in the lower atmosphere and on the surface. Many mythical heroes in Greek and Norse mythology made celebrated efforts to visit hell. A great deal can also be learned about our planet, which is a comparative heaven, by comparing it to hell. However, we will return to Venus because it is fascinating. Half human and half lion was built over 5,500 years ago. Its face was once crisp and cleanly rendered. It is now softer and blurrier due to thousands of years of sandblasting in the Egyptian desert and occasional rains. There is an obelisk in New York City called Cleopatra's Needle, which originated in Egypt. In only about 100 years in that city's Central Park, its inscriptions have perhaps 100,000, and large-scale human artifacts only a few thousand. In addition to such slow and uniform erosion, destruction can also occur through large and small catastrophes. The Sphinx is missing a nose because someone shot it off in a moment of idle desecration. Some say it was Mameluke Turks, and others say it was Napoleonic soldiers. On Venus, on Earth, and elsewhere in the solar system, there is evidence for catastrophic destruction, tempered or overwhelmed by slower, more uniform processes. On the Earth, for example, rainfall coursing into rivulets, streams, and rivers of running water, creating huge alluvial basins. On Mars, the remnants of ancient rivers, perhaps arising from beneath the ground. On Io, a moon of Jupiter, what seem to be broad channels made by flowing liquid sulfur. There are mighty weather systems on the Earth, in the high atmosphere of Venus and on Jupiter. There are sandstorms on Earth and Mars, and lightning on Jupiter, Venus, and Earth. Volcanoes inject debris into the atmospheres of the Earth and Jupiter. Internal geological processes slowly deform the surfaces of Venus, Mars, Ganymede, Europa, and Earth. Glaciers, proverbial for their slowness, produce major reworkings of landscapes on Earth and probably also on Mars. These processes need not be constant over time. Most of Europe was once covered with ice. A few million years ago, the present site of the city of Chicago was buried under 3 kilometers of frost. On Mars and elsewhere in the solar system, we see features that could not be produced today. Landscapes carved hundreds of millions or billions of years ago when the planetary climate was probably very different. An additional factor that can alter Earth's landscape and climate is that intelligent life can make major environmental changes. Like Venus, the Earth has a greenhouse effect due to its carbon dioxide and water vapor. Earth's global temperature would be below the freezing point of water if not for the greenhouse effect. It keeps the oceans liquid and life possible. A little greenhouse is a good thing. Like Venus, the Earth also has about 90 atmospheric carbon dioxide, but it resides in the crust as limestone and other carbonates, not in the atmosphere. If the Earth were moved only a little closer to the Sun, the temperature would increase slightly. This would drive some of the CO2 out of the surface rocks, generating a stronger greenhouse effect which would, in turn, incrementally heat the surface further. A hotter surface would vaporize still more carbonates into CO2, and there would be the possibility of a runaway greenhouse effect at very high temperatures. This is just what we think happened in the early history of Venus because of Venus's proximity to the Sun. The surface environment of Venus is a warning. Something disastrous can happen to a planet rather than our own. The so-called fossil fuels are the primary energy sources for our modern industrial civilization. When we burn wood, oil, coal, and natural gas, we release waste gases, primarily carbon dioxide, into the air. As a result, the amount of carbon dioxide in the Earth's atmosphere is dramatically increasing. The possibility of a runaway greenhouse effect suggests we must be cautious. Even a 1 or 2 degree rise in the global temperature can have catastrophic consequences. But we have also been oppositely changing the climate. Humans have been torching and cutting down forests and encouraging domestic animals to graze on and destroy grasslands for thousands of years. Today, slash-and-burn agriculture, industrial tropical deforestation and overgrazing are commonplace. However, Forests are darker than grasslands, and grasslands are darker than deserts. As a result, the amount of sunlight absorbed by the ground has increased. Our lovely blue planet, the Earth, is the only home we know. Venus is too hot, Mars is too cold, but the Earth is just right, a heaven for humans. After all, we evolved here, but our congenial climate may be unstable. We are perturbing our poor planet in serious and contradictory ways. We humans now represent a new and perhaps decisive factor. Our intelligence and technology have given us the power to affect the climate. How will we use this power? Are we willing to tolerate ignorance and complacency in matters that affect the entire human family? Do we value short-term gains over long-term sustainability? The cosmos is all there is, everything that has ever been and will ever be. The cosmos is all there is, everything that has ever been and will ever be. Even our most feeble attempts to contemplate the cosmos are enough to make us feel a tingling in the spine, a catch in the voice, and a faint sensation, almost as if it were a distant memory of falling from a great height. We know that we are getting closer to solving the most perplexing puzzles. The age of the universe and the magnitude of its age are both incomprehensible to the average human being. Our tiny planetary home is probably misplaced between space's vastness and time's eternity. Most human concerns appear insignificant and even trivial from the cosmos perspective. Despite this, our species is still young, full of wonder and bravery, and possesses great potential. Over the past few millennia, we have made some of the most astounding and unanticipated discoveries about the cosmos and our place within it. These discoveries are exhilarating explorations to consider. They serve as a reminder that humans have an innate capacity for wonder, that understanding something brings joy, and that knowledge is essential to survival. I believe our future will be determined by how well we understand this vast universe in which we float around like a speck of dust in the morning sky. These kinds of investigations required a healthy dose of skepticism and creative thinking. Imagination can frequently transport us to worlds that never actually existed. But we won't get very far if we don't have it. We can differentiate fantasy from reality and put our hypotheses to the test when we exercise skepticism. The universe possesses an immeasurable amount of richness, which can be broken down into three categories: exquisite interrelationships, exquisite facts, and the subtle machinery of awe. The shoreline of the infinite cosmic ocean is found on the surface of the Earth. The vast majority of our knowledge came from our experiences with it. Over the past few days, we have ventured out into the ocean just far enough to get our toes, or, at the very most, our ankles wet. It looks like a refreshing place to swim. The call of the ocean. Some component of our being is aware that this is where we originated. We can't wait to get back there. These aspirations are not disrespectful, even though they may upset existing gods, because the dimensions of the cosmos are so vast, utilizing standard units of distance, such as meters or miles, that were chosen for their applicability on Earth would not make much sense. Instead, we use the speed of light as our unit of measurement for distance. A single second is long enough for a beam of light to travel 186,000 miles, close to 300,000 kilometers, and equivalent to 7 times around the Earth. It will arrive at its destination on Earth 8 minutes after leaving the Sun. We can say that the Sun will be visible in 8 minutes. In just 1 year, it travels a distance equivalent to approximately 6 trillion miles, or nearly 10 trillion kilometers, through the intervening space. A light year is a unit of length that measures the distance light travels in 1 year. It does not measure time, but rather distances, extremely large distances. The planet Earth is a location. It is not even close to being the only location. Even by today's standards, it is not a typical place, because most of space in the universe is devoid of matter. There is no such thing as a typical planet, star, or galaxy. Planets, stars, and galaxies appear heartbreakingly rare and beautiful compared to the vast freezing vacuum of the universal space that makes up intergalactic space. This is the only place to be described as normal and the only place in the universe. The probability of our discovering life elsewhere in the universe, if we were to be hurled into space at random, the likelihood of us being on or near another planet, is less than 1 in a billion trillion trillion, 10 to the power of 33, which is a 1 followed by 33 zeros. In normal conversation, the odds at this level are called compelling. There is great value in the world. From a perspective that spans galaxies, we can see an infinite number of flimsy, wispy light tendrils dispersed throughout space like sea foam on the surface of the waves. These are the galaxies in the universe. Some are lone explorers, but most live in communal clusters, huddling together while drifting aimlessly through the vast cosmic darkness. In front of us is the cosmic on the largest scale we are familiar with. We are 8 billion light-years away from Earth, in the region of the nebulae. And our galaxy is made up of gas, dust, and stars, with billions and billions of stars making up its composition. Someone, somewhere, could view any star as their sun. A galaxy contains not only stars and worlds, but also, it's possible, an abundance of living things, intelligent beings, and spacefaring civilizations. However, when viewed from a great distance, a galaxy brings to mind more of a collection of lovely objects that have been found, perhaps seashells or corals, which are the results of nature's labor over aeons of time in the cosmic ocean. There are approximately 100 billion galaxies, and each galaxy contains approximately 100 billion stars on average. There may be as many planets in the universe as stars. 10 to the power of 11 times 10 to the power of 11 equals 10 to the power of 22, which is 10 billion trillion. In the face of such overwhelming numbers, how likely is it that there is only one typical star, the Sun, accompanied by an ordinary planet that people live on? Why should we, tucked away in some obscure part of the universe, be so lucky? There seems to be much more likely to be life throughout the universe. However, we as humans do not yet have this knowledge. The exploration that we are conducting has just started. Even the cluster in which our Milky Way galaxy is embedded is difficult to find from this distance, much less the Sun or Earth. This distance is equivalent to 8 billion light-years. At this great distance, the only planet we can be certain that life exists is a tiny speck of rock and metal that glimmers feebly in the sunlight reflected off it. But for the time being, our travels have brought us to what astronomers here on Earth call the neighborhood group of galaxies. It spans a distance of several million light-years and comprises approximately 20 galaxies that make up its component parts. It is a dispersed, obscure, and unassuming collection of objects. M31 is one of these galaxies, and it can be found in the Andromeda constellation when viewed from Earth. Like other spiral galaxies, it comprises stars, gas, and dust in a pinwheel-like pattern. M31 has 2 smaller satellites that are dwarf elliptical galaxies that are gravitationally bound to it. This same law of physics tends to keep me seated in my chair. The natural laws do not change no matter where you go in the universe. We are currently 2 million light-years away from home at this point. In the region beyond M31 is another galaxy that is very comparable to our own. The spiral arms of this galaxy turn very slowly, once every 250 million years. Now, after traveling 40,000 light-years away from our home, we find that we are moving closer and closer to the immense center of the Milky Way. But if we want to find Earth, we must change our course to the galaxy's far reaches, to an obscure location close to the edge of a faraway spiral arm. Only then will we be able to locate the planet. Even in the middle of the spiral arms, the overwhelming sensation is of stars moving past us. These stars come in all shapes and sizes. Some are as flimsy as a soap bubble, but are so large that they could contain 10,000 suns or 1 trillion Earths. Others are the size of a small town, but are 100 trillion times denser than lead. Some stars, like the Sun, are on their own. The vast majority are accompanied. Double star systems are quite common and consist of two stars orbiting each other. However, there is a gradual progression from triple star systems to loose clusters of a few dozen stars to enormous globular clusters, resplendent, with a million suns. This progression can be seen as a continuous gradation. Some binary stars are so close to one another that their surfaces touch, allowing material from both stars to flow between them. Most are located at a distance comparable to Jupiter's from the Sun. While some stars known as supernovae shine brighter than the entire galaxy in which they are located, others, known as black holes, are so dark that they cannot even be seen from a distance of a few kilometers. Some have a steady, bright glow, while others flicker erratically or blink in a steady, predictable pattern. Some turn with stately elegance, while others spin with such ferocity that they become oblate due to their distorted shape. Most radiate most of their light in the visible and infrared spectrums, while others are brilliant sources of X-rays or radio waves. If a star is blue, it is energetic and young. If it is yellow, it is average and in the middle of its life. If it is red, it is likely old and on its deathbed. And if it is white or black, about 400 billion stars of varying types are contained within the Milky Way, which moves in a complex yet graceful order. The people who live on Earth are only aware of one of the myriad stars in the universe. Each star system occupies its distinct space region, separated from its surrounding regions by light years. I can picture life forms evolving into glimmers of knowledge on an infinite number of worlds, with each of those life forms at first supposing that their meager planet and its few suns are the only things in the universe. We have a very solitary upbringing. We are only just beginning to educate ourselves about the cosmos. There is a possibility that some stars are surrounded by millions of lifeless and rocky worlds. These worlds are planetary systems, frozen at an early stage in their evolution. Many stars may have planetary systems very similar to ours. At the periphery, large gaseous planets with rings and icy moons, and closer to the center, small, warm, blue-white worlds covered in cloud cover. Intelligent life may have developed on some planets, and as part of their massive engineering projects, they may have reworked the planet's surface. These are our planetary kin and the other inhabitants of the cosmos. Are there significant differences between us and them? Which of the following best describes their mode of expression? Biochemistry, neurobiology, history, politics, science, technology, art, music, religion, or philosophy? Perhaps one day we will be able to call them friends. 1 light year away from Earth, we finally arrived at our backyard. The cometary nuclei are a spherical swarm of giant snowballs composed of ice, rock, and organic molecules. They orbit our sun. One of them obligingly careens into the inner solar system occasionally in response to a small gravitational tug given by a passing star. There, the sun's warmth melts the ice, which in turn causes the formation of a beautiful cometary tail. When we think of the planets in our solar system, we think of them as large worlds dominated by the sun that are gravitationally forced to travel in nearly circular orbits and get their heat primarily from the sun. Pluto is illuminated by a distant sun, which appears as nothing more than a bright point of light in an otherwise pitch-black sky. Pluto is covered with methane ice and accompanied by its lone giant moon, Charon. Jupiter, Neptune, Uranus, and Saturn, considered the crown jewel of the solar system, all have a retinue of icy moons orbiting around them. The gassy planets and orbiting icebergs are located on the region's periphery, containing the inner solar system's warm, rocky provinces. There is, for instance, the red planet Mars, known for its towering volcanoes, enormous rift valleys, massive sandstorms covering the entire planet, and the remote possibility that it harbors some simple forms of life. The Sun is the closest star to our solar system. It is an immense ball of hydrogen and helium gas that is constantly undergoing thermonuclear reactions, which is what causes it to be the brightest object in our solar system. At last, after all of our wanderings, we return to our puny, fragile, blue-white world, which is adrift in a vast cosmic ocean beyond our most audacious imaginations. It is one world among an infinite number of others that exist. It's possible that no one else cares about it but us. Our home and mother, the Earth, are here on this planet. This is the place where our kind of life began and where it developed. The human species is maturing in this part of the world. It was on this planet that we first discovered our enthusiasm for traveling throughout the cosmos, and it is still that we are figuring out our fate, even though it causes us some discomfort and offers no assurances. We want to take this opportunity to welcome you to Earth, a world positively teeming with life, with its blue nitrogen skies, oceans of liquid water, cool forests, and soft meadows. I have already mentioned that it is heartbreakingly beautiful and exceedingly uncommon. However, at this very moment, it is also one of a kind in the cosmos. It is the only world we have visited during our travels through space and time that has provided us with definitive evidence that the inanimate matter of the cosmos has developed consciousness and become alive. There must be many such worlds strewn across space, but our search for them begins here, with the accumulated knowledge of the males and females of our species, which was acquired at a great cost over 1 million years. We are extremely fortunate to live in a time and place that values the pursuit of knowledge, and to do so among exceptionally intelligent human race, which was ultimately created in the cosmos but is temporarily residing on a planet known as Earth, has started its long journey back to its origins. The discovery that the Earth is a miniature world was made, like so many other significant discoveries made by humans, in the ancient Near East, in a time that some humans call the 3rd century BC, in the greatest metropolis of the age, the Egyptian city of Alexandria. This discovery was made in the ancient Near East, as were so many other significant discoveries made by humans. A man who went by the name Eratosthenes lived in this location. One of his contemporaries, who was green with envy, referred to him as Beta, the second letter of the Greek alphabet, because he believed that Eratosthenes was the second best of everything in the world. Eratosthenes was an astronomer, historian, geographer, philosopher, poet, theatre critic, and mathematician. The titles of the books he wrote range from astronomy to On Freedom from Pain. He was also the director of the Great Library of Alexandria, where one day he read in a papyrus book that in the southern frontier outpost of Syene, near the first cataract of the Nile at noon on June 21st, vertical sticks cast a shadow on the ground. Eratosthenes was a scientist, and his musings on these commonplaces changed the world. In a way, they made it. It was an observation that someone else might have easily ignored. Sticks, shadows, reflections in wells, and the position of the sun. What possible importance could such simple, everyday matters be? But Eratosthenes was a scientist, and his musings on these commonplaces changed the world. In a way, they made the Eratosthenes puzzled over how, at the same moment, a stick in Syene could cast no shadow, while a stick in Alexandria, far to the north, could cast a pronounced shadow. Imagine a map of ancient Egypt with two vertical sticks of equal length, one stuck in Alexandria and the other in Syene. Suppose that, at a certain moment, each stick casts no shadow at all. This is easy to understand if the Earth is flat, because the sun would be directly overhead. Because the sun is so far away, its rays are parallel when they reach the Earth. Sticks placed at different angles to the sun's rays cast shadows of different lengths. To account for the observed difference in the lengths of the shadows, the distance between Alexandria and Syene would have to be approximately 7 degrees along the Earth's surface. This is the correct response. Eratosthenes' only tools were sticks, eyes, feet, and brains, in addition to a taste for experimentation. With them, he deduced the circumference of the Earth with an error of only a few %, which was a remarkable achievement for 2,200 years ago. He was the first person to accurately measure the size of a planet. At that time, the Mediterranean world was renowned for its seafaring, and Alexandria was considered the greatest seaport on the planet. Once you knew the Earth to be a sphere of modest diameter, would you not be tempted to make voyages of exploration, to seek out undiscovered lands, perhaps even to attempt to sail around the planet? Africa had already been circumnavigated by a Phoenician fleet in the employ of the Egyptian pharaoh Necho, 400 years before Erato. After Eratosthenes' discovery, many brave and enterprising sailors attempted many voyages. Their ships were tiny. They had only rudimentary navigational instruments. They used dead reckoning and followed coastlines as far as they could. In an unknown ocean, they could determine their latitude, but not their longitude, by observing, night after night, the position of the constellations concerning the horizon. The familiar constellations must have been reassuring to them. In the time of Eratosthenes, globes were created that depicted the Earth as seen from space. These globes were accurate to a large extent in the well-explored Mediterranean region, but they became increasingly inaccurate the further away they traveled from home. Our current understanding of the cosmos also possesses this frustrating but unavoidable characteristic. Humans' exploration of other worlds began taking place in almost every significant sense. The subsequent exploration of the Earth was a worldwide endeavor that included voyages from. The culmination of this exploration was the discovery of America by Christopher Columbus, and the journeys of the subsequent few centuries, which completed the geographical exploration of the Earth. Columbus had been an itinerant peddler of old maps and an assiduous reader of the books by and about the ancient geographers, including Eratosthenes, Strabo, and Ptolemy. However, for the enterprise of the Indies to work and for ships and crews to survive the long voyage, the Earth had to be smaller than Eratosthenes had said. The Earth has been thoroughly explored and no longer holds the promise of any new continents or lost lands. However, the same technology that allowed us to explore and inhabit the most remote regions of the Earth now enables us to leave our planet, venture into space, and explore other worlds. It was in Alexandria during the 600 years beginning around 300 BC that human beings, in an important sense, began the intellectual adventure that has led us to the shores of space. However, nothing of the look and feel of that glorious marble city remains. Oppression and the fear of learning have obliterated almost all memory of ancient Alexandria. Its population was a marvelously diverse mix of Macedonian and later Roman soldiers, Egyptian priests, Greek aristocrats, and Pharaoh Alexander the Great established the city, and one of his former bodyguards was responsible for its construction. Alexander was known for promoting an open-minded attitude towards learning and respect for foreign cultures. According to legend, and it does not matter much whether it really happened, he descended beneath the Red Sea in the world's first diving bell. He encouraged his generals and soldiers to marry Persian and Indian women. He respected the gods of other nations. He collected exotic life forms, including crocodiles. But the greatest marvel of Alexandria was the library and its associated museum, literally an institution devoted to the specialities of the 9 muses. Of that legendary library, the most that survives today is a dank and forgotten cellar of the Serapeum, the library annex, once a temple and later reconsecrated to knowledge. A few mouldering shelves may be the only physical remains. Yet this place was once the brain and glory of the greatest city on the planet, the first true research institute in the history of the world. The scholars of the library studied the entire cosmos. Cosmos is a Greek word for the order of the universe. It is, in a way, the opposite of chaos. It implies the deep interconnectedness of all things. It conveys awe for the intricate and subtle way the universe is assembled. Here was a community of scholars exploring physics, literature, medicine, astronomy, geography, philosophy, mathematics, biology, and engineering. Science and scholarship had come of age. Genius flourished there. The Alexandrian Library is where we humans first collected, seriously and systematically, world knowledge. In addition to Eratosthenes, there was the astronomer Hipparchus, who mapped the constellations and estimated the brightness of the stars. Euclid, who brilliantly systematized geometry and told his king, struggling over a difficult mathematical problem, there is no royal road to geometry. Dionysius of Thrace, the man who defined the parts of speech and did for the study of language what Euclid did for geometry. Herophilus, the physiologist who firmly established that the brain, rather than the heart, is the seat of intelligence, Heron of Alexandria, inventor of gear trains and steam engines and the author of Automata, the first book on robots, Apollonius of Perga, the mathematician who demonstrated the forms of the conic sections, ellipse, parabola, and hyperbola. The curves, as we now know, followed in their orbits by the planets, the comets, and the stars. Archimedes, the greatest mechanical genius until Leonardo da Vinci, and the astronomer and geographer Ptolemy, who compiled much of what is today the pseudoscience of astrology. His Earth-centered universe held sway for 2,500 years, a reminder that intellectual capacity is no guarantee against being dead wrong. And among those great men was a great woman, Hypatia, mathematician and astronomer, the last light of the library, whose martyrdom was bound up with the destruction of the library 7 centuries after its founding, a story to which we will return. The Greek kings of Egypt who succeeded Alexander were serious about learning. For centuries they supported research and maintained in the library a working environment. The library contained 10 large research halls, each devoted to a separate subject. It also contained fountains and colonnades, botanical gardens, a zoo, dissecting rooms, an observatory, and a great dining hall where, at leisure, the critical discussion of ideas was conducted. The heart of the library was its collection of books. The organizers combed through all the cultures and languages of the world. They sent agents abroad to buy up libraries. Commercial ships docking in Alexandria were searched by the police, not for contraband but for books. The scrolls were borrowed, copied, and then returned to their owners. Accurate numbers are difficult to estimate, but it seems probable that the library contained 500,000 volumes, each a handwritten papyrus scroll. What happened to all those books? The classical civilization that created them disintegrated, and the library was deliberately destroyed. Only a small fraction of its works and a few scattered fragments survived. And how tantalizing those bits and pieces are. We know, for example, that there was on the library shelves a book by the astronomer Aristarchus of Samos, who argued that the Earth is one of the planets, which, like them, orbit the Sun, and that the stars are enormously far away. These conclusions are correct, but we had to wait nearly 2,000 years for their rediscovery. If we multiply by 100,000 our sense of loss for this work of Aristarchus, we begin to appreciate the grandeur of the achievement of classical civilization and the tragedy of its destruction. We have far surpassed the sense known to the ancient world, but there are irreparable gaps in our historical knowledge. Imagine what mysteries about our past could be solved with a borrower's card to the Alexandrian library. We know of a 3-volume history of the world, now lost, by a Babylonian priest named Berossus. The first volume dealt with the interval from creation to the flood, a period he took to be 432,000 years, or about 100 times longer than the Old Testament chronology. I wonder what was in it. We now know that the universe is much older than the ancients ever imagined. We have looked at the universe from space and seen that we live on a mote of dust circling a humdrum star in the remotest corner of an obscure galaxy. And if we are a speck in the immensity of space, we also occupy an instant in the expanse of the ages. And until we find more intelligent beings elsewhere, we are the most spectacular of all the transformations. We are the distant descendants of the Big Bang, and are dedicated to understanding and further transforming the cosmos where we spring from. For the entirety of my life, I have been curious about whether or not there is life on other planets. What kind of an experience would it be? What would it be composed of exactly? Organic molecules, which are intricate microscopic structures held together by the carbon atom, are the building blocks of everything living on this planet. Before life existed on Earth, the planet was sterile and devoid of civilization. The world we live in is currently teeming with life. What was the reason behind it? How did carbon-based organic molecules come when there was no life to create them? How did the first organisms come into existence? How did life evolve to produce beings as elaborate and complex as us, capable of investigating the mystery of our origins? And finally, if there are infinite planets that orbit other suns, does life exist on any of them? If life exists elsewhere in the universe, does it consist of the same kinds of organic molecules as life here on Earth? Do the inhabitants of other worlds resemble the life on Earth in any significant way? Or are they astonishingly distinct, representing other adaptations that have evolved in response to other environments? What other possibilities are there? The investigation into the origins of life on Earth and the search for life in other worlds are two facets of the same question: the investigation into the nature of who we are. There are clouds of gas, dust, and organic matter that are located in the vast darkness that exists between the stars. Radio telescopes have discovered dozens of organic molecules in that region. The prevalence of these molecules provides evidence that the components necessary for life can be found anywhere. If enough time passes, life's beginnings and subsequent development may be a cosmic inevitability. There won't ever be life on some of the billions of planets that make up the Milky Way galaxy. It might appear briefly on other worlds before vanishing or never progressing beyond its basic forms. Additionally, on a relatively small percentage of worlds, there might be civilizations and intelligence that one will occasionally remark about how fortunate it is that the Earth has conditions ideal for life, such as temperatures that are just right, water that can be liquidized, an oxygen-rich atmosphere, and so on. But here we have a case of confusing the cause with the effect, at least in part. Because we evolved on this planet, we are extraordinarily well suited to the natural conditions that we find ourselves in. Earlier forms of life that were not well adapted to their environments perished. We are descended from organisms that were successful in their environments. There is no doubt that organisms that evolve in very different worlds will also sing praises to this world. There is a connection between all forms of life on Earth. Both our organic chemistry and our evolutionary history are shared between all of us. Consequently, the scope of our biologists' work could be more robust. They only focus on one branch of biology, like focusing on one note in an otherwise complex piece of music. Is this ethereal and breathy melody the only sound for thousands of light years? Or could there be something akin to a cosmic fugue, complete with recurring motifs and counterpoints, dissonances and harmonies, and a billion distinct voices, all contributing to the life music of the galaxy? Please permit me to regale you with a tale concerning a tinier phrase from the song that is Life on Earth. In 1185, the Emperor of Japan was a young boy named Antoku. He was only 7 years old. He was the de facto leader of a samurai clan known as the Heike, who were at war with another samurai clan known as the Genji. This conflict lasted for a long time and was very bloody. Each one argued that they had a more legitimate ancestral right to the throne of the imperial empire. On April 24, 1185, their decisive naval encounter occurred at Dano-ura, in the Japanese Inland Sea. The emperor was present on board one of the ships during the conflict. The Heikes were outmatched in terms of both numbers and strategic ability. Many people lost their lives. In large numbers, the survivors committed their own demise by jumping into the water and drowning themselves. Lady Ni, the emperor's grandmother, decided that she and Antoku would not be taken prisoner by the hostile forces. The following events are described in detail in the tale of the Heike. In that year, the emperor was only 7 but appeared much older. He was so attractive that he gave off the impression of radiating a brilliant light, and his long black hair was styled in a way that allowed it to hang loosely all the way down his back. The question, "Where are you going to take me?" was posed to Lady Ni by the man, who wore a confused and anxious expression. She turned her attention to the young monarch with tears streaming down her cheeks, and consoled him while tying his long hair up in the robe that was the color of a dove. The tears had clouded the child sovereign's vision, and he clasped his adorable little hands together. He began by facing east to bid farewell to the god of ice, and then he faced west to recite the Nembutsu, a prayer addressed to the Amida Buddha. After cradling him tightly in her arms, Lady Ni uttered, "In the depths of the ocean is our capital," and then dove beneath the water's surface with him. The entire battle fleet belonging to the Heike was wiped out. Only 43 women managed to make it out alive. These ladies-in-waiting of the imperial court were coerced into selling flowers and other favors to the fishermen in the area that was immediately surrounding the battlefield. The Heike came dangerously close to being forgotten by history. However, a ragtag group of the former ladies-in-waiting and their offspring among the fisherfolk established a festival to commemorate the battle. This festival was held in the fisherfolk community. April 24th comes around like clockwork every year to mark the occasion. Fishermen who are descendants of the Heike put on black hemp clothing and headgear and make their way to the Akama shrine. This shrine is home to the mausoleum of the emperor who was drowned. They watch a play that depicts the events after the Battle of Danoura while they are there. People believed they could see the ghosts of samurai armies attempting in vain to clean the sea of blood, defeat, and humiliation for centuries after the battle. According to the fishermen, the Heike samurai can still be found prowling the bottoms of the inland sea, but this time they are in the form of crabs. Crabs in this area have peculiar markings on their backs, including patterns and indentations that eerily resemble the face of a samurai. In remembrance of the tragic events at Danoura, these crabs are not consumed after they are caught. This rather presents a very interesting conundrum. How did it come to be that a crab's carapace has a warrior's face carved into it? Humans were responsible for creating the face. The patterns that appear on a crab's shell result from inheritance, but there are a lot of different hereditary lines among crabs, just like there are among people. Imagine that among the crab's remote ancestors, one evolved with a pattern that vaguely resembled a human face. This would be a remarkable coincidence. Even before the Battle of Danoura, it's possible that fishermen were hesitant to eat such a crab because of its reputation. They kicked off a chain of events that would eventually lead to evolution by doing so. If you are a crab, and your carapace is not extraordinary, humans will eat you. Your family tree will have a smaller number of descendants. If your carapace has even the slightest resemblance to a face, they will not let you pass. You will have more descendants than other people. The crabs put a lot of effort into designing the patterns found in their carapaces. There was eventually produced not just a human face, not just a Japanese face, but the visage of a fierce and scowling samurai, because as the generations of crabs and fishermen passed, the crabs with patterns that most resembled a samurai face survived preferentially. This continued until there was eventually produced not just a human face, not just a Japanese face. This whole thing has nothing to do with what the crabs seek. Selection is a process that is imposed from without. Your chances of surviving exponentially increase if you give the impression that you are a samurai. There will inevitably be a great number of samurai crabs in the future. The process in question is referred to as artificial selection. When it came to the Heike crab, the process was carried out more or less unconsciously by the fishermen, and the crabs themselves did not appear to give it any significant thought. However, for thousands of years, humans have deliberately chosen which species of plants and animals will survive and which will perish. From birth, we are surrounded by the sights and smells of commonplace farm and domestic animals, fruits, trees, and vegetables. Where do they get their supplies? Were they once able to live as they pleased in the wild, but later convinced to move to a more manageable environment on a farm? In contrast, the reality is very different. The vast majority of them were produced by our team. No dairy cows, ferret hounds, or large ears of corn existed 10,000 years ago. We were able to exercise parental authority over these plants and animals by controlling their reproduction after we had domesticated their ancestors, which often resembled very different creatures. We made it a point to prioritize the reproduction of certain varieties because they possessed qualities that we regarded as being desirable. When we decided that we needed a dog to assist us in taking care of our sheep, we chose breeds that were both intelligent and obedient, as well as those that possessed some natural ability to herd, as this ability is useful for animals that hunt in packs. Because of the increased demand for milk and cheese among humans, The udders of dairy cattle have ballooned to enormous proportions. Our maize, also known as maize, has been bred for 10,000 generations to make it tastier and more nutritious than its puny ancestors. In fact, it has been changed so drastically that it cannot reproduce on its own without the assistance of humans. This is the heart of what is known as artificial selection, whether for a hickey crab, a dog, a cow, or an ear of corn. There is a strong genetic component to both the outward appearance and the behavior of plants and animals. They always produce the same results. For whatever reason, humans promote the reproduction of certain varieties of plants and animals, while working to suppress the reproduction of others. The variety selected for preferential reproduction will eventually become abundant, whereas the variety selected against will become rare and possibly extinct. But if humans can create new species of plants and animals, shouldn't nature be able to do the same? Natural selection is the name given to this connected process. The modifications humans have made to animals and plants during the relatively short period that they have existed on Earth, as well as the fossil evidence, make it abundantly clear that life has undergone profound transformations throughout aeons. The fossil record provides unmistakable evidence of extinct species that were once abundant but have completely disappeared from the Earth. In the history of the Earth, many more species have gone extinct than there are living today. These extinct species are the evidence. The domestication process has hastened the occurrence of genetic changes in the population. It was not until early medieval times that the rabbit was domesticated. It was bred by French monks in the belief that newborn bunnies were fish, and therefore exempt from the prohibitions against eating meat on certain days in the church calendar. Coffee was not domesticated until the 15th century. The sugar beetroot was not domesticated until the 19th century, and the domestication of the mink is still in its earliest stages. Domestication has increased the weight of wool grown by sheep from less than 1 kilogram of coarse hairs to 10 or 20 kilograms of uniform, fine down in less than 10,000 years. Similarly, the volume of milk given by cattle during a lactation period has increased from a few hundred to 1 million cubic centimeters. Considering that artificial selection can quickly bring about such profound shifts, one can only imagine what natural selection, which operates over billions of years, is capable of. The answer is all the splendor and variety in the natural world. The theory of evolution has no basis in reality. The great discovery made by Charles Darwin and Alfred Russel Wallace is that the driving force behind evolution is natural selection. This discovery is associated with the names of Charles Darwin and Alfred Russel Wallace. More than a century ago, they emphasized that nature is prolific and that many more animals and plants are born than can survive. As a result, the environment selects those varieties that are, by accident, better suited for survival. Because of this, they believed that the environment selects those varieties that are better suited for survival. Mutations, defined as sudden changes in genetic inheritance, are heritable. They supply the essential building blocks for evolution. The environment picks out the few beneficial mutations to survival, leading to gradual changes from one life form into another and the birth of new species. In his book, On the Origin of Species, Charles Darwin wrote, "Variability is not caused by humans. Rather, humans unintentionally expose organic beings to new conditions of life, allowing nature to exert its influence on the organization, which results in variability. However, man can pick and choose among the variations that nature has provided him, and can, therefore, accumulate them in any way he pleases. In this way, he manipulates living things for his own benefit or pleasure, including animals and plants. He may do this on purpose, but it's also possible that he does it unintentionally by keeping the individuals who are the most useful to him at the time, without giving any thought to changing the breed. There is no obvious reason why the principles that have acted so efficiently under domestication should not have acted under natural circumstances. There are always more people born than there is room for them to survive. It only takes the tiniest advantage in one being, at any age or during any season, over those with which it comes into competition or a better adaptation to the surrounding physical conditions, no matter how slight, to tip the scales in one direction or the other. H. Huxley, the most influential 19th century defender and popularizer of evolution, wrote that the publications of Darwin and Wallace were a flash of light, which to a man who has lost himself in a dark night suddenly reveals a road which, whether it takes him straight home or not, certainly goes his way. My reflection, when I first made myself master of the central idea of the origin of species, was, how extremely stupid not to have thought of that. Many people were shocked, some of them still are, by the concepts of evolution and natural selection. Our ancestors looked at the sophistication of life on Earth and noticed how well suited the structures of organisms are to the roles that they play, and they concluded that there must have been an intelligent designer behind all of this. Even the simplest organism, consisting of just one cell, is a far more complex machine than the most intricate pocket watch. However, pocket watches do not spontaneously self-assemble or evolve slowly and methodically from other clocks, such as grandfather clocks. A watch requires the services of a watchmaker. There did not appear to be any way that atoms and molecules could have somehow fallen together spontaneously to create organisms of such astounding complexity and delicate functioning, concept that the great living thing had a unique purpose, and that one species could not evolve into another were perfectly consistent with what our ancestors knew about life, even though they only had access to limited historical records. The concept that every living thing was painstakingly assembled by an all-powerful designer lent significance and order to the natural world and importance to human beings that we continue to yearn for today. An explanation of the biological world that involves a designer is natural, appealing, and completely human. On the other hand, natural selection makes life's music more beautiful as the aeons pass, as Darwin and Wallace demonstrated. This method is just as appealing, humane, and far more compelling. The existence of a great designer may be consistent with the fossil evidence. Certain species are whipped out when the designer grows dissatisfied with them, and new experiments are attempted on an improved design. However, this idea gives me a slightly uneasy feeling. Each plant and animal is exquisitely crafted. However, a designer with such a high level of expertise ought to have been able to create the intended variety from the very beginning. The fossil record suggests that there was a process of trial and error and an inability to predict the future. These are characteristics that are inconsistent with a great designer who is efficient, but are consistent with a designer who has a temperament that is more remote and indirect. During the early 1950s, when I was a first-year student at a university, I had the incredible opportunity to work in the laboratory of H.J. Muller, a distinguished geneticist, who first hypothesized that exposure to radiation causes genetic mutations. Muller was the one who first brought the example of the Heike crab to my attention, as an illustration of how artificial selection works. I worked with fruit flies, also known as Drosophila melanogaster, which literally translates to the black-bodied dew lover, for a significant amount of time to gain experience in the applied aspects of genetics. Fruit flies are tiny, harmless beings with 2 wings and large eyes. We stored them in milk bottles with a pint capacity each. We would breed 2 different types to see what new forms would result from the reorganization of the genes in the parental organisms and from any natural or artificial mutations. The female fruit flies would lay their eggs on molasses that the laboratory technicians would place inside the bottles. The bottles would then be sealed, and we would wait for 2 weeks for the fertilized eggs to develop into larvae, for the larvae to develop into pupae, and for the pupae to develop into new adult fruit flies. One day, I was busy separating the various varieties of adult Drosophila using a camel's hairbrush while looking through a low-power binocular microscope at a freshly arrived batch of adult Drosophila immobilized with a little ether. To my astonishment, I came across something very different. It wasn't just a minor variation like the eyes being red instead of white or having neck bristles instead of having no neck bristles. This was a different kind of creature, and it was very well functioning. It had much more prominent wings and its long and feathery antennae. I concluded that fate had predetermined that an example of a major evolutionary change in a single generation should occur in Muller's laboratory, even though Muller had stated that such a thing could never happen. My unenviable responsibility was to break the news to him. I did so with a heavy heart, as I knocked on the door of his office. I had found a very different kind of fly. I was sure it had emerged from one of the pupae in the molasses. I didn't mean to disturb Muller, but does it look more like Lepidoptera than Diptera? Does it have big wings? He asked, his face lit up from below. I had no idea what he was talking about, so he had to explain it. Does it have feathery antennae? I gave a glum nod in agreement. Muller smiled benignly as he turned on the light in the overhead fixture. It had been told many times before. One moth species had become accustomed to the conditions found in Drosophila genetics labs. It was not comparable to a fruit fly, and I had no interest in having anything to do with it. Molasses was what it desired, specifically that of the fruit flies. While the laboratory technician was unstopping and stopping the milk bottle, for example, to add fruit flies, the mother moth made a dive-bombing pass, dropping her eggs into the delicious molasses while she was running. Before this, I was unaware of any macromutations. It turned out that I had merely stumbled upon yet another beautiful adaptation that had developed in the natural world due to macromutations. Keys to understanding evolution are death and time. The deaths of enormous numbers of life forms imperfectly adapted to the environment, time for a long succession of small mutations that were by accident adaptive, and time for the slow accumulation of patterns of advantageous mutations over long periods. These are the secrets of evolution. Our inability to conceptualize the passage of centuries, let alone aeons, contributes to our rejection of Darwin and Wallace's theory of evolution by natural selection. What does a lifespan of 1/1,000,000th of a second mean to beings that have been around for 70 million years? We are like butterflies that only live for a day but believe their existence will last forever. The events that occurred here on Earth may be more or less typical of the evolution of life on many worlds. However, the history of life on Earth may be unique across the entirety of the Milky Way galaxy in certain specifics, such as the chemistry of proteins or the neurology of brains. Around 4.6 billion years ago, gas and dust from interstellar space coalesced to form the planet Earth. As a result of the fossil record, we know that the beginning of life occurred not long after, possibly around 4.0 billion years ago, in the primitive oceans and ponds on Earth. There is no evidence that the first living things were nearly as complicated as a single-celled organism, already a highly developed form of life. The initial stirrings were of a much more subdued nature. In those early days, lightning and ultraviolet light from the sun broke apart the simple hydrogen-rich molecules that made up the primitive atmosphere. The fragments of these molecules then spontaneously recombined into more complex molecules. The products of this early chemistry were dissolved in the oceans, creating a kind of organic soup of gradually increasing complexity. This continued until one day, quite by accident, a molecule emerged that could make crude copies of itself by utilizing other molecules in the soup as building blocks. This event is considered to be the beginning of life on Earth. At a later time, we will discuss this topic once more. This was the progenitor of deoxyribonucleic acid, also known as DNA, which is the fundamental building block of all life on Earth. It looks like a ladder coiled into a helix, and each rung can be one of 4 distinct molecular parts. These parts correspond to the genetic code's first, second, third, and fourth letters. These steps, called nucleotides, contain the genetic instructions necessary to construct a particular organism. Every form of life that has ever existed on this planet has unique instructions written in the same language. The distinct instructions within each organism's nucleic acid are largely responsible for the observed diversity among living things. A nucleotide can undergo a change known as a mutation if that change is successfully copied into the next generation. Most mutations are harmful or fatal because they involve random changes to nucleotides. These mutations code for enzymes that are inactive and do not function properly. It takes a very long time for a mutation to improve the functioning of an organism. Despite this, the driving force behind evolution is an improbable occurrence known as a beneficial mutation in a nucleotide that is only 10 millionths of a centimeter across. Before 4 billion years, Earth was like a molecule-sized version of the Garden of Eden. There were no dangerous animals around just yet. Some molecules ineffectively reproduced themselves, competed with one another for building blocks, and left behind crude copies of themselves. Even on a molecular level, evolution was well underway due to reproduction, mutation, and the selective elimination of less effective varieties. They gradually became more proficient at reproduction as time went on. Eventually, molecules that had specialized functions came together to form what is now known as the first cell, which is a molecular collective. Photosynthesis is the process by which carbohydrates and oxygen are produced from glucose and carbon dioxide using light energy, water, and carbon dioxide. Modern plant cells contain molecular factories known as chloroplasts, which are responsible for this process. A different kind of molecular factory known as the mitochondrion can be found within the cells that make up a drop of blood. Mitochondria extract usable energy from food by combining it with oxygen. These factories are found in the cells of plants and animals, but they may have been free-living at one point in the past. By 3 billion years ago, several one-celled plants had fused into one organism. This may have occurred due to a mutation that prevented a single cell from dividing into two distinct cells. The first organisms with multiple cells came into existence. Every cell in your body can be considered a community, with its formerly independent components working together to benefit the whole. You, on the other hand, are comprised of 100 trillion cells. Each one of us is a part of a much larger whole. It is estimated that sexual activity began approximately 2 billion years ago. Before that time, the only way new varieties of organisms could emerge was by accumulating random mutations which consisted of the selection of changes made to the genetic instructions letter by letter. The process of evolution had to have been excruciatingly slow. Because of the development of sexual reproduction, two organisms can now exchange entire paragraphs, pages, and books of their DNA code, producing new varieties prepared for selection. It is advantageous for organisms to engage in sexual behavior, as those that do not find it interesting will quickly become extinct. In addition, this is true of the microbes that existed 2 billion years ago. Today, there is a palpable dedication among us humans to the process of exchanging different sections of our DNA. By 1 billion years ago, plants had, through concerted effort, brought about a revolutionary shift in the natural environment of the Earth, the production of molecule oxygen by green plants. As a result of the fact that the oceans were already teeming with simple green plants, oxygen was starting to become a major component of the Earth's atmosphere. This irreversibly changed the atmosphere from its initial state of being rich in hydrogen, and ended the period in Earth's history when the building blocks of life were created by non-biological processes. On the other hand, oxygen has a tendency to cause organic molecules to disassemble. Although we have a soft spot for it, it is, at its core, a toxin for organic matter that is not protected. Due to their inability to function in an oxygen-rich environment, many organisms did not survive the transition to an oxidizing atmosphere and became extinct. Even in modern times, some archaic forms can only live in oxygen-free environments. Examples of these include the botulism and tetanus bacilli. Nitrogen is a much more chemically inert element than oxygen, and as a result it is found in much higher concentrations in the Earth's atmosphere. However, it is also maintained by biological processes. Therefore, biological processes are responsible for 99% of the atmosphere that surrounds the Earth. The atmosphere itself is alive. Since the beginning of life on Earth some 4 billion years ago, the most common organisms have been microscopic blue-green algae, which have covered and filled the oceans for most of that time. Then, approximately 600 million years ago, the algae's monopolizing grip was broken, and an enormous proliferation of new life forms emerged. This phenomenon is referred to as the Cambrian explosion. The fact that life appeared on Earth so soon after the planet's formation hints that it may have resulted from a chemical reaction that could not have been avoided on a planet with similar conditions. The fact that life only advanced a little beyond blue-green algae for 3 billion years suggests that large life forms with specialized organs are difficult to evolve. In fact, it is even more difficult to evolve than the origin of life itself. Many other planets may have abundant microbes, but no large animals or plants. In a short amount of time after the Cambrian explosion, the oceans were already home to a wide variety of life forms. There were vast herds of trilobites around 500 million years ago. These animals had a beautiful construction and were similar to large insects in appearance. Some of them hunted in packs on the ocean floor. Crystals were stored in their eyes so that they could detect polarized light. On the other hand, there are no living trilobites in the world today, and there haven't been any for the past 200 million years. The planet was home to many plants and animals, none of which can be found today in any living form. In addition, every living species now found on this planet was at once absent from it. There is no evidence of animals similar to us in the ancient rocks. The emergence of species is followed by a more or less fleeting presence and eventual extinction. Before the Cambrian explosion, species were succeeding one another in a relatively slow fashion. This may be the case partly because the quality of our information rapidly deteriorates the further back in time we look. During the early stages of the history of our planet, few organisms had hard parts, and soft beings left behind very painstaking evolution of cell structure and biochemistry does not immediately reflect itself in the external forms revealed by the fossil record. However, the slow rate at which dramatic new forms appeared before the Cambrian explosion is partly because this rate was real. Following the Cambrian explosion, exquisite new adaptations emerged one after the other at a comparatively breathtaking rate. In rapid succession, the first fish and the first vertebrates appeared. Plants, which were previously restricted to the oceans, began the colonization of the land. The first insect evolved, and its descendants became the pioneers in the colonization of the land by animals. Winged insects arose together with the amphibians, creatures similar to the lungfish, able to survive both on land and in the water. The first trees and the first reptiles appeared. The dinosaurs evolved. The first mammals appeared. The first birds appeared. The primates thought to have given rise to humans, apes, and monkeys. The first creatures that closely resembled human beings evolved less than 10 million years ago, concurrently with a spectacular increase in brain size. These creatures lived less than 10 million years ago, and then just a few million years ago, the very first true humans appeared on the scene. Our species evolved in the woods, so we have a fundamental connection to these environments. Seeing a tree reaching for the clouds is a beautiful sight. Because their leaves must absorb sunlight to photosynthesize, trees compete with one another by casting shadows on adjacent plants. If you look carefully, you can frequently see two trees jostling gracefully and unhurriedly. Trees are magnificent and aesthetically pleasing machines that are driven by the sun. They can extract water from the soil and carbon dioxide from the air, then turn these elements into food for their own consumption and ours. To carry out its function as a plant, the organism relies on the energy provided by the carbohydrates that it produces. And we animals, who are ultimately just parasites on the plants, have to rob them of their carbohydrates so that we can carry on with our lives. By consuming plants, we can combine the carbohydrates with the oxygen already dissolved in our blood due to our need to breathe air. This allows us to extract the energy that allows us to move around. During this process, we release carbon dioxide into the atmosphere, which the plants can reuse to produce additional carbohydrates. A planet-wide mutual mouth-to-stoma resuscitation, the beautiful cycle is powered by a 150 million kilometers away star. What a marvelous cooperative arrangement, plants and animals inhaling the other's exhalations. Tens of billions of different kinds of organic molecules have been discovered so far. However, only about 50 of them are used for the necessary activities for survival. The same patterns are used repeatedly, but this time more cleverly and economically, for various purposes. At the very core of life on Earth, the proteins that regulate the chemistry of the cell and the nucleic acids that carry the instructions for inheritance, we find that these molecules are essentially the same in all living things, including plants and animals. The same stuff that makes up an oak tree also makes up me. You'll find that we share an ancestor when you return far enough. A living cell is a system that is just as intricate and breathtaking as the universe, which is filled with galaxies and stars. Over 4 billion years, the complex machinery that makes up a cell has been painstakingly developed. Food is broken down into components and then used to make cellular machinery. The white blood cell of today is the equivalent of the creamed spinach of yesteryear. What is the mechanism that the cell uses? On the inside is a complex and intricate architecture responsible for the upkeep of its structure, the transformation of molecules, the storage of energy, and the preparation for self-replication. If we could enter a cell, the majority of the specks that we would see are protein molecules. Some of these molecules are engaged in frenetic activity while others wait. Enzymes, which are molecules that control the chemical reactions that take place within the cell, are the most important proteins. Enzymes are analogous to workers on an assembly line. Each enzyme is specialized for a particular molecular job, such as step 4 in constructing the nucleotide guanosine phosphate, or step 11 in dismantling a sugar molecule to extract energy. Energy is the currency that pays for getting the other cellular jobs done. Enzymes are like workers on an assembly line. However, enzymes are not in charge of the show. They get their instructions from those in charge, who are also responsible for their own construction due to the orders they receive. Nucleic acids are in the cell's nucleus, located far within its interior and considered off-limits. If we were to enter the nucleus of a cell through a pore, we would find something that looks like an explosion in a spaghetti factory. We would find a disorderly multitude of coils and strands, which are the two different types of nucleic acids: DNA, which knows what to do, and RNA, which conveys the instructions issued by DNA to the rest of the cell. These are the best results that 4 billion years of evolution have been able to produce. They contain the complete set of information on how to make a cell, a tree, or a human being function properly. If written in regular language, the amount of information in human DNA would require 100 thick volumes. In addition, the DNA molecules can produce, with extremely limited exceptions, carbon copies that are indistinguishable from themselves. They have an incredible amount of knowledge. The structure of DNA is known as a double helix, and its two strands, which are intertwined, take the form of a spiral staircase. The language of life can be understood by looking at the specific order in which the nucleotides are arranged along either of the constituent strands. During the process of reproduction, the helices split apart with the help of a specialized protein that unwinds them, and then each slice synthesizes an identical copy of the other, using nucleotide building blocks that are nearby and floating in the viscous liquid that makes up the nucleus of the cell. Once the process of unwinding has begun, a remarkable enzyme known as DNA polymerase helps to ensure that the copying process will almost always be successful. If a mistake is made, some enzymes will cut out and replace the incorrect nucleotide with the correct one. These enzymes are atomically precise machines that are capable of phenomenal feats. In addition to producing exact copies of itself, which is the purpose of heredity, nuclear DNA directs the cell's activities, which is the purpose of metabolism, by synthesizing another nucleic acid called messenger RNA. Each of these messenger RNA molecules travels to the extranuclear regions of the cell, where it controls the construction of an enzyme at the appropriate time and location. After everything is said and done, a single enzyme molecule will have been produced. This molecule will then set about organizing a specific component of the chemistry that occurs within the cell. The ladder that makes up human DNA is 1 billion nucleotides in length. Most possible permutations of nucleotides are meaningless because they would synthesize proteins with no practical purpose. The number of nucleic acid molecules useful for complex life forms like ours is extremely low. Despite this, the number of useful ways to combine nucleic acids is mind-bogglingly large. It is probably much higher than the total number of electrons and protons in the universe. Consequently, the number of individual human beings who could exist is significantly higher than the number of humans who have ever existed. The unrealized potential of the human species is enormous. There must be ways of putting nucleic acids together that, according to any criterion we choose, will function significantly better than any human being that has ever lived. To our good fortune, we do not yet know how to combine different nucleotide sequences to produce different kinds of human beings. The possibility that, in the not-too-distant future, we can assemble nucleotides into any sequence we want to produce any characteristics we deem desirable is both a sobering and unsettling prospect. Mutation and selection are the two processes that drive evolution. If the enzyme DNA polymerase makes an error during replication, then mutations may occur. However, it is extremely prone to making errors. It is also possible for mutations to occur due to radioactivity, ultraviolet light from the sun, cosmic rays, or chemicals found in the environment. Each of these factors has the potential to alter the nucleotides or to tangle the nucleic acids. If the mutation rate is too high, we risk losing the inheritance of 4 billion years' worth of painstakingly gradual evolution. If it is too low, no new varieties will be available to adapt to potential environmental changes. Life's evolution must strike a more or less precise balance between random mutation and selective breeding. When that equilibrium is reached, remarkable adaptations begin to take place. A single change in a DNA nucleotide will result in a single change in an amino acid in the protein the DNA codes for. People of European descent tend to have red blood cells that are roughly globular in shape. Red blood cells in the bodies of some people of African descent appear as they carry less oxygen. Sickle cells are responsible for transmitting sickle cell anemia. They also offer a significant degree of protection against malaria. There is no room for debate regarding the fact that having anemia is preferable to being dead. This major influence on the function of the blood is the result of a change in a single nucleotide out of the 10 billion found in the DNA of a typical human cell. The effect is so striking that it is readily apparent in photographs of red blood cells. We still do not fully understand the ramifications of changes made to most other nucleotides. The appearance of humans is quite distinct from that of trees. There is no question that our way of perceiving the world is distinct from that of a tree. However, beneath the surface, at the molecular core of life, trees and humans are virtually indistinguishable. Both you and I pass on genetic information using nucleic acids, and the chemical processes inside our cells are orchestrated by proteins acting as enzymes. The fact that we both use the same codebook to translate information in nucleic acids into information about proteins is perhaps the single most important similarity between us and the vast majority of other living things on this planet. This molecular unity is typically explained by the idea that all living things, including trees and people, anglerfish, slime molds, and paramecia, are descended from a single and shared instance of the origin of life in the early history of our planet. Then, how did the essential molecules come into existence? My research group at Cornell University focuses, among other things, on biological organic chemistry. Through our efforts, we can make some notes on the composition of life. We combine and ignite the gases present on the early Earth, including hydrogen, water, ammonia, methane, and hydrogen sulfide. These elements can also be found on Jupiter and elsewhere in the cosmos. Lightning, which was also present on the ancient Earth and on modern Jupiter, corresponds to the sparks that can be seen. At the beginning of the reaction vessel is clear and the precursor gases are completely unobservable. After 10 minutes of sparking, however, we notice an odd brown pigment slowly spreading along the vessel's sides. The interior eventually turns out to be completely opaque and is coated in a viscous brown tar. If we had used ultraviolet light, we would have been simulating the early sun's rays, and the results would have been relatively unaltered. Tar is an extremely rich collection of complex organic molecules, including the components of proteins and nucleic acids. Tar can be found in various environments, including caves and swamps. It turns out that the essential components of life can be fabricated with relative ease. Stanley Miller, a graduate student of the chemist Harold Urey at the time, was the first person to conduct experiments in the early 1950s. Urey had argued convincingly that the early atmosphere of the Earth was rich in hydrogen, as is most of the rest of the universe. that the hydrogen has since leaked away into space from Earth, but not from massive Jupiter, and that the origin of life occurred before the hydrogen was lost. Someone questioned Urey about what he anticipated the outcome of such an experiment would be after he proposed the idea of sparking such gases. Urey replied, Beilstein. Beilstein is a German compendium in 28 volumes, listing all the organic molecules known to chemists. We can produce the fundamental components of life by utilizing only the most abundant gases present on early Earth, and almost any energy source that breaks chemical bonds. However, the molecules we have in our vessel are only the notes of the music of life, not the music itself. For life to exist, the atomic components must be assembled properly. It isn't easy to conceive of a simpler organism that is, in any sense, livable. The smallest living things known, the viroids, comprise less than 10,000 atoms. They cause several diseases in cultivated plants and have probably most recently evolved from more complex organisms rather than simpler ones. No one has been able to perform an experiment in which the gases and waters of the early Earth were mixed together and had something crawl out of the test tube at the end of the experiment. The smallest known free-living organisms are the PPLO, pleuropneumonia-like organisms, and similar small beasts. They are composed of about 50 million atoms. Such organisms, which must be more self-reliant, are more complicated than viroids and viruses. But the environment of the Earth today is not extremely favorable for simple forms of life. You have to be careful about predators. In the early history of our planet, however, when enormous amounts of organic molecules were being produced by sunlight in a hydrogen-rich atmosphere, very simple, non-parasitic organisms had a fighting chance. The first living things may have been like free-living viroids, only a few hundred nucleotides long. Experimental work on making such creatures from scratch may begin by the end of the century. There is still much to be understood about the origin of life, including the origin of the genetic code. But we have been performing such experiments for only some 30 years. Nature has had a 4 billion year head start. All in all, we have not done badly. The initial gases and the energy sources are ubiquitous throughout the cosmos. Chemical reactions similar to those in our laboratory vessels may be responsible for the organic matter in interstellar space and the amino acids found in meteorites. The molecules of life are abundant throughout the cosmos. But even if life on another planet has the same molecular chemistry as here, there is no reason to expect it to resemble familiar organisms. Consider the enormous diversity of living things on Earth, all of which share the same planet and identical molecular biology. Those other beasts and vegetables are probably very different from any organism we know here. There may have been some convergent evolution because there may be only one best solution to a certain environment. I am only familiar with one form of life on Earth. As a result, I cannot describe what life elsewhere in the universe might be like. Some people, such as science fiction writers and artists, have tried to imagine what other beings might be like. However, I am skeptical about most of these extraterrestrial visions because they appear to be based too heavily on forms of life that we are already familiar with. On a giant gas planet like Jupiter, with an atmosphere rich in hydrogen, helium, methane, water, and ammonia, there is no easily accessible solid surface, but rather a dense, cloudy atmosphere in which organic molecules may be falling from the skies like manna from heaven, like the products of our laboratory experiments. However, there is a characteristic impediment to life on such a planet. The atmosphere is turbulent and hot down deep. An organism must be careful to avoid being. My colleague at Cornell, E. Salpeter, and I have performed calculations to demonstrate that life can exist on a different planet. Although we can't know exactly what life would be like in such a place, our goal was to determine whether or not, following the laws of physics and chemistry, a world of this kind could possibly be inhabited. One way to make a living under these conditions is to reproduce before you're fried, and hope that convection will carry some of your offspring to the higher and cooler layers of the atmosphere. Such organisms could be very small. We call them sinkers. But you could also be a floater, some vast hydrogen balloon pumping helium and heavier gases out of its interior and leaving only the lightest gas, hydrogen, or a hot air balloon, staying buoyant by keeping your interior warm, using energy acquired from the food you eat. Like familiar terrestrial balloons, the deeper a floater is carried, the stronger the buoyant force, returning it to the atmosphere's higher, cooler, and safer regions. A floater might eat preformed organic molecules or make its own from sunlight and air, as plants do on Earth. Up to a point, the bigger a floater is, the more efficient it will be. I imagined floaters kilometers across, enormously larger than the greatest whale ever, being the size of cities. The floaters may propel themselves through the planetary atmosphere with gusts of gas, like a ramjet or a rocket. We imagine them arranged in great lazy herds for as far as the eye can see, with patterns on their skin, an adaptive camouflage implying that they have problems too. Because there is at least one other ecological niche in such an environment: hunting. Hunters are fast and maneuverable. They eat the floaters both for their organic molecules and for their store of pure hydrogen. Hollow sinkers could have evolved into the first floaters and self-propelled floaters into the first hunters. There cannot be many hunters because if they consume all the floaters, the hunters will perish. If there are billions of inhabited worlds in the Milky Way galaxy, perhaps there will be a few that are populated by the sinkers, floaters, and hunters that our imaginations, which have been tempered by the laws of physics and chemistry. Nature is not obligated to follow our speculations. Art bestows a certain charm upon such life forms. There is no predictive theory of biology, just as there is not yet a predictive theory of history. For the same reason, both subjects are still too complicated for us. However, we can know ourselves better by understanding other cases. The study of a single instance of extraterrestrial life, no matter how humble, W. There is no predictive theory of biology, just as there is not yet a predictive theory of history for the same reason. Both subjects are still too complicated for us. But we can know ourselves. Only the voice of life in one tiny world has been audible to us until this point. But we have recently started to pay attention to the other voices that may be present in the cosmic cacophony. The completion of all things. There would only be a little to do if we lived on a planet with a chance of changing anything. There would be nothing that required deduction or deduction. There would be no driving force behind the advancement of science. And if we lived in an unpredictably chaotic world, where things changed in completely arbitrary or extremely convoluted ways, we would not be able to figure out what was happening. Again, the concept of science would be completely non-existent. But we live in a universe somewhere in the middle, and everything around us shifts and changes according to certain patterns, rules, or the laws of nature. If I toss a stick into the air, it will inevitably land on the ground. If the sun goes down in the west, it will always rise in the opposite direction the following morning in the east. As a result, it is now possible to figure out what's going on. We can conduct scientific research, and by doing so, we can make our lives better. The capacity of human beings to comprehend their surroundings is impressive. We have been since the beginning. Only after we had solved a certain problem could we successfully hunt the game and build fires. There was once a time when there was no television, motion pictures, radio, or books. The majority of human history took place during this particular period. On a night with no moon, we sat around the dwindling embers of the campfire and gazed up at the stars. A lot is going on in the night sky. There are recurring themes present. You are capable, without making an effort, of imagining pictures. For instance, a pattern known as a constellation can be found in the northern sky with an Ursine appearance. Some cultures refer to it as the Great Bear. Some people have very different mental pictures. As a matter of course, these images are not projected onto the night sky, rather, we have placed them there ourselves. We were hunters by trade, so we encountered other hunters with their dogs, bears, and young women. These things piqued our interest. Toucans and peacocks, telescopes and microscopes, compasses, and the sterns of ships were some things that 17th century European sailors thought they saw in the southern skies when they first encountered them in the 17th century. If the constellations had been named in the 20th century, we would see things like refrigerators, bicycles, rock and roll stars, and mushroom clouds in the night sky. These things would represent a new set of human hopes and fears that would have been placed among the stars. Occasionally, our ancestors would glimpse a bright star with a tail hurtling across the sky for a moment. They called it a falling star, but this is not an accurate name because the old stars are still there after the falling star falls. There is a regularity here as well. Some seasons have a lot of falling stars, while others have very few. There is order, predictability, and permanence about the stars. In a way, they are almost comforting. Like the sun and moon, the stars always rise in the east and set in the west, taking the whole night to cross the sky if they pass overhead. There are different constellations in different seasons. The same constellations always rise at the beginning of autumn, for example. It never happens that a new constellation suddenly rises out of the east. Certain stars rise just before or set just after the sun, at times and positions that vary with the seasons. You could predict the seasons if you carefully observed and recorded the stars over many years. You could also measure the time of year by noting where the sun rose each day on the horizon. The sky was a great calendar, available to anyone who was dedicated and had the ability. Our ancestors built devices to measure the passing of the seasons. Chaco Canyon, New Mexico, has a great roofless ceremonial kiva or temple dating from the 11th century. On June 21st, the longest day of the year, a shaft of sunlight enters a window at dawn and slowly moves so that it covers a special niche. But this happens only around June 21st. I imagine the proud Anasazi people who describe themselves as the Ancient Ones, gathered in their pews every June 21st, dressed in feathers, rattles, and turquoise to celebrate the sun's power. They also monitored the moon's apparent motion. The 28 higher niches in the kiva may represent the number of days for the moon to return to the same position among the constellations. These people paid close attention to the sun, the moon, and the stars. Other devices based on similar ideas are found at Angkor Wat in Cambodia, Stonehenge in England, Abu Simbel in Egypt, Chichen Itza in Mexico, and the Great Plains in North America. Some alleged calendrical devices may be due to chance, such as an accidental alignment of window and niche on June 21st. However, other devices are wonderfully unique. At one location in the American Southwest, 3 upright slabs moved from their original position about 1,000 years ago. On June 21st, the first day of summer, a dagger of sunlight pouring through an opening in one of the slabs aligns with a spiral carved in the rock. We hunted gazelles, antelope, and buffalo, whose migrations ebbed and flowed with the seasons. Fruits and nuts were ready to be picked at certain times, but not other times. We had to plant and harvest our crops at the right time when we invented agriculture. Annual meetings of far-flung nomadic tribes were set for prescribed times. Only we can hear the wind howling through the canyons of the American Southwest, which serves as a reminder of the 40,000 generations of intelligent men and women who came before us, about whom we know almost nothing, and who are the foundation of our civilization. As time went on, people gained knowledge from their ancestors. The more precisely one knew the position and movements of the sun, moon, and stars, the more reliably one could predict when to hunt, sow, reap, and gather the tribes. But then, much later, another rather curious idea emerged, an assault by mysticism and superstition on what had been primarily an empirical science. The sun and stars controlled the seasons, food, and warmth. The moon controlled the tides, the life cycles of many animals, and perhaps the human menstrual period, of central importance for a passionate species dedicated to having children. There was another kind of object in the sky, the wandering or vagabond stars called planets. There are 10 times as many astrologers in the United States as there are astronomers. In modern Western society, it is easy to buy a magazine on astrology, for example, at a newsstand, while finding one on astronomy is much more difficult. Astrology columns appear in virtually every newspaper in the United States, whereas astronomy columns appear in almost none. Chances of success, 1 in 12. What sign are you? And much less frequently. Have you heard that gold is made in the explosions of supernovae? Or, when do you think Congress will decide whether or not to fund a Mars rover? Astrology contends that the constellation the planets are in at the moment of your birth profoundly influences your future. A few thousand years ago, the idea developed that the motions of the planets determined the fates of kings, dynasties, and empires. Astrologers studied the motions of the planets and asked themselves what had happened the last time that, say, Venus was rising in the constellation of the Goat. Something similar could happen this time as well. It was a subtle and risky business. Astrologers came to be employed only by the state. In many countries, it was a capital offense for anyone, but the official astrologer to read the portents in the skies. A good way to overthrow a regime was to predict its downfall. Chinese court astrologers who made inaccurate predictions were executed. Others doctored the records so that, afterwards, they were in perfect conformity with events. Astrology developed into a strange combination of observations, mathematics, careful record-keeping, fuzzy thinking, and pious fraud. Personal astrology originated in Alexandrian Egypt and spread throughout the Greek and Roman worlds approximately 2,000 years ago. Today, we can recognize the antiquity of astrology in words such as disaster, which is Greek for bad star, influenza, Italian for astral influence, Mazel Tov, and Hebrew, and ultimately Babylonian. There were rovers who were considered sideratio, which means planet-struck. Planets were widely thought to be a direct cause of death. Or consider, it means with the planets, evidently a prerequisite for serious reflection. Consider the mortality statistics in the City of London in 1632. Among the terrible losses from infant and childhood diseases and such exotic illnesses as the rising of lights and the King's Evil, we find that, out of 9,535 deaths, consider two different astrology columns published in the same city on the same day. For example, we can look at the New York Post and the New York Daily News on September 21, 1979. Assume that you are a Libra, which means you were born between September 23 and October 22. The astrologer for the Post predicted that a compromise will help ease tension. This prediction was useful, but vague. You should demand more of yourself, the astrologer for the Daily News advised, providing similarly hazy and distinctive advice. These predictions are not actually predictions. They are advice. They tell what should be done rather than what will occur. They are worded to apply to anyone on purpose, making them extremely general. In addition to this, they exhibit a significant degree of mutual inconsistency. Why are they published with the same lack of remorse as reports on the stock market and sports statistics? The lives of twins can be used to test the validity of astrology. There are many instances in which one of two identical twins passes away during childhood, for example, as a result of a riding accident or being struck by lightning, while the other twin enjoys a long and fruitful life. They were delivered at the same hospital only a few minutes apart. When they were born, precisely the same planets were coming into view. How is it possible for two identical twins to have lives that are so radically different according to astrology? It has also been discovered that astrologers cannot even reach a consensus with one another regarding the interpretation of a specific horoscope. They cannot make accurate predictions about the personalities and destinies of individuals with no information other than their birth time and location, as demonstrated by rigorous testing. A peculiar quality is shared by all of the flags that represent the nations of Earth. The United States flag has 50 stars representing the following: the Soviet Union and Israel with 1 each, Burma with 14, Grenada and Venezuela with 7, China with 5, Iraq with 3, São Tomé and Príncipe with 2, Japan, Uruguay, Malawi, Bangladesh and Taiwan representing the sun, Brazil representing a celestial sphere, Australia, Western Samoa, New Zealand and Papua New Guinea representing the constellation of the Southern Cross. Bhutan, representing stars, are prominently displayed in many socialist nations. Crescent moons are commonly displayed on the flags of many Islamic countries. Almost half of our nation's flags feature astronomical or celestial imagery in some form. The phenomenon crosses cultural boundaries, is secular, and can be found worldwide. It is also not limited to the time that we live in. Seals made in the shape of cylinders that date back to the 3rd millennium BC in Sumer. During the time before the Chinese Revolution, Taoist flags featured various constellations. There is no question in my mind that nations aspire to appropriate a portion of the authority and credibility of the heavens. We are looking to establish a rapport with the universe. When making decisions, we want to keep the big picture in mind. And as it turns out, we are connected, not in the personal, small-scale and unimaginative fashion that the astrologers pretend, but in the deepest ways, involving the origin of matter, the habitability of the earth, and the evolution and destiny of the human species. Claudius Ptolemy, whom we call Ptolemy today, was not related to any of the kings of the same name, despite sharing the same name. Modern popular astrology can be traced directly back to him. He was employed at the Library of Alexandria in Alexandria, Egypt, in the 2nd century. Ptolemy is credited with codifying the Babylonian astrological tradition, where all of the esoteric information about planets ascendant in this or that solar or lunar house, or the age of Aquarius, comes from. The following is an example of a horoscope written in Greek on papyrus during the time of Ptolemy, and pertains to a young girl named Philo, born in 150. It is inscribed with the following information: the birth of Philoe, the 10th year of Antoninus Caesar the Lord, Faminoth 15 to 16, the first hour of the night, Sun in Pisces, Jupiter and Mercury in Aries, Saturn in Cancer, Mars in Leo. Ptolemy believed that not only were behavior patterns influenced by the planets and the stars, but that questions regarding stature, complexion, national character, and even congenital physical abnormalities were determined by the stars. Ptolemy also believed that the stars determined whether or not a person would have congenital physical abnormalities. On this particular issue, modern astrologers have taken a more cautious position. However, contemporary astrologers still need to consider Ptolemy's understanding of the precession of the equinoxes. They don't consider the phenomenon of atmospheric refraction, which Ptolemy wrote about. They give a negligible amount of consideration to the numerous moons and planets, asteroids and comets, quasars and pulsars, exploding galaxies, symbiotic stars, cataclysmic variables, and X-ray sources that have been discovered since the time of Ptolemy. The study of the universe in its present state constitutes the scientific discipline known as astronomy. Astrology is a form of pseudoscience that asserts, without providing sufficient evidence, that the movements of other planets have an effect on our day-to-day lives. When Ptolemy lived, there was a lot of confusion about the difference between astronomy and astrology. Today is the day. As an astronomer, Ptolemy was responsible for naming the stars, compiling a list of their relative brightness, providing compelling evidence to support the notion that the Earth is spherical, formulating guidelines for accurately predicting eclipses, and, perhaps most importantly, attempting to comprehend the reason behind the peculiar meandering motion that planets display against the backdrop of far-off constellations. He devised a predictive model to comprehend the movements of the planets and decipher the hidden message in the skies. Ptolemy experienced something akin to ecstasy due to his research into the cosmos. "Mortal as I am," he wrote, "I know that I was born for a day. But when I follow at my pleasure the serried multitude of the stars in their circular course, my feet no longer touch the earth. Mortal as I am," he wrote, "I know that I was born for a day." This is the most natural idea in the world. The earth seems steady, solid, and immobile, while we can see the heavenly bodies rising and setting each day. Every culture has jumped to the geocentric hypothesis. Johannes Kepler wrote, "It is therefore impossible that reason not previously instructed should imagine anything other than that the earth is the center of the universe." Ptolemy believed that the earth was the center of the universe. He believed the sun, moon, planets, and stars went around the earth. However, how can we explain the apparent motion of the planets, such as Mars, which had been known for thousands of years before Ptolemy? One of the epithets given to Mars by the ancient Egyptians was Sekded F.M. Ketket, which means "who travels backwards," a clear reference to the apparent motion of Mars in a retrograde model of planetary motion can be represented by a small machine similar to those that existed in Ptolemy's time, and served a purpose similar to what Ptolemy's model predicts. It was necessary to determine the real motion of the planets, as seen from up there on the outside, to accurately reproduce the apparent motion of the planets, as seen from down here, on the inside. The challenge was figuring out the real motion of the planets from up there, on the outside. It was thought that perfect transparent spheres on which the planets were mounted would revolve around the Earth. However, instead of being fastened to the spheres directly, they were indirectly connected to them utilizing an asymmetrical wheel. The sphere rotates, the little wheel spins, and Mars appears to perform a loop-the-loop maneuver from our vantage point on Earth. This model allowed for reasonably accurate planetary motion predictions, and they were certainly good enough for the precision of measurement that was available in Ptolemy's day and even many centuries later. There was a heaven or sphere for the Moon, Mercury, Venus, the Sun, Mars, Jupiter, Saturn, and one more for the stars. Ptolemy's ethereal spheres were imagined in medieval times to be made of crystal. This is why we still talk about the music of the spheres and the seventh heaven. Since it was believed that the Earth was the center of the universe, that creation was based on events that took place on Earth, and that the heavens were imagined to be constructed on utterly unearthly principles, people were not motivated to observe the heavens through astronomy. Ptolemy's model, supported by the Church throughout the Dark Ages, was a major factor in preventing the advancement of astronomy for 1,000 years. Nicholas Copernicus, a Polish Catholic cleric, published a quite different hypothesis to explain the apparent motion of the planets in the year 1543. This hypothesis was able to explain the apparent motion of the planets. The idea that the Sun, not the Earth, was at the center of the universe was by far the most audacious aspect of this theory. The Earth was demoted to the status of just one of the planets, moving in a perfectly circular orbit third in distance from the Sun. Ptolemy had considered such a heliocentric model, but he rejected it immediately because, according to the physics of Aristotle, the implied violent rotation of the Earth seemed contrary to observation. When explaining the movement of the planets as seen from Earth, it worked at least as well as Ptolemy's spheres did. On the other hand, it irritated a lot of people. The Catholic Church placed the work of Copernicus on its list of books that were forbidden until corrected by local ecclesiastical censors in 1616, and it remained on that list until 1835. Even some of Copernicus's admirers argued that he had not really believed in a sun-centered universe, but had proposed it as a convenience for calculating the motions of the planets. Martin Luther referred to him as an upstart astrologer. This fool wishes to reverse the entire science of astronomy. But sacred scripture tells us that Joshua commanded the sun to stand still, not the earth. He lived in a time when the human spirit was fettered and the mind chained. The ecclesiastical pronouncements of a millennium or two earlier on scientific matters were considered more reliable than contemporary findings made with technology. This epochal confrontation between the two views of the cosmos, earth-centered and sun-centered, reached a climax in the 16th and 17th centuries in the person of a man who was both an astrologer and an Johannes Kepler was born in Germany in 1571 and was sent to the Protestant seminary school in the provincial town of Maulbronn to be educated by the clergy. It was a kind of boot camp training young minds in using theological weaponry against the fortress of Roman Catholicism. Kepler, who was stubborn, intelligent, and fiercely independent, suffered 2 friendless years in bleak Maulbronn, becoming isolated and withdrawn. His thoughts were devoted to his imagined unworthiness.
While many quantum experiments focus on observing tiny entities like electrons and photons, quantum phenomena permeate our existence, operating across all scales. Nevertheless, detecting them within larger objects can be challenging, potentially leading to the misconception that quantum phenomena are peculiar or otherworldly. Quantum science bridges gaps in our understanding of physics, providing a more comprehensive perspective on our daily lives. Quantum breakthroughs have become integral to our fundamental comprehension of materials, chemistry, biology, and astronomy. These discoveries represent a valuable wellspring of innovation, spawning devices like lasers and transistors, and facilitating advancements in technologies once deemed purely speculative, such as quantum computing. Physicists are investigating how quantum science may revolutionize our understanding of gravity and its relationship with space and time. There's even the potential for quantum science to unveil the interconnectedness of all things in the universe, or across multiple universes, through higher dimensions, which elude our sensory perception. The field of quantum physics arose in the late 1800s and early 1900s from a series of experimental observations of atoms that didn't make intuitive sense in classical physics. Among the basic discoveries was the realization that matter and energy can be thought of as discrete packets, or quanta, with a minimum value. For example, a fixed frequency light will deliver energy in quanta called photons. Each photon at this frequency will have the same amount of energy, and this energy can't be broken down into smaller units. In fact, the word quantum has Latin roots and means how much. Knowledge of quantum principles transformed our conceptualization of the atom, which consists of a nucleus surrounded by electrons. Early models depicted electrons as particles that orbited the nucleus, much like satellites orbit Earth. Modern quantum physics instead understands electrons as being distributed within orbitals, mathematical descriptions representing the probability of the electron's existence in more than one location within a given range at any given time. Electrons can jump from one orbital to another as they gain or lose energy, but cannot be found between orbitals. Other central concepts help to establish the foundations of quantum physics. Wave-particle duality. This principle dates back to the earliest days of quantum science. It describes the outcomes of experiments that showed that light and matter had the properties of particles or waves, depending on how they were measured. Today, we understand that these different forms of energy are actually neither particles nor waves. They are distinct quantum objects that we cannot easily conceptualize. Superposition. This term describes an object as a combination of multiple possible states simultaneously. A superposed object is analogous to a ripple on the surface of a pond that is a combination of two waves overlapping. In a mathematical sense, an object in superposition can be represented by an equation with more than one solution or outcome. Uncertainty principle. This mathematical concept represents a trade-off between complementary points of view. In physics, this means that two properties of an object, such as its position and velocity, cannot be precisely known simultaneously. If we precisely measure the position of an electron, for example, we will be limited in how precisely we can know its speed. Entanglement occurs when two or more objects are connected to be considered a single system, even if they are very far apart. The state of one object in that system can only be fully described with information on the other object's state. Likewise, learning information about one object automatically tells you something about the other, and vice versa. The field of quantum physics emerged during the late 1800s and early 1900s due to a series of experimental observations involving atoms. These observations defied intuitive understanding within the framework of classical physics. One of the fundamental revelations was the recognition that matter and energy could be conceptualized as discrete packets, referred to as quanta, each possessing a minimum associated value. For instance, light with a fixed frequency imparts energy in quanta called photons. Each photon of that specific frequency carries an identical amount of energy, indivisible into smaller units. The term quantum has Latin origins, signifying how much. This newfound understanding of quantum principles revolutionized our perception of the atom, composed of a central nucleus surrounded by electrons. Early models depicted electrons as discrete particles orbiting the nucleus, akin to satellites circling the Earth. In modern quantum physics, electrons are instead described as being distributed within orbitals, mathematical representations that denote the probability of finding electrons at various locations within a specified range at any given moment. Electrons can transition between orbitals as they gain or lose energy but do not exist between these orbital states. Several key concepts formed the bedrock of quantum physics: wave-particle duality. This concept, rooted in the earliest days of quantum science, encompasses the findings that light and matter exhibit characteristics of particles and waves contingent upon the measurement method. In contemporary understanding, these forms of energy are neither purely particles nor waves. They are distinct quantum entities defying easy categorization. Superposition. This term describes an object existing as a blend of multiple possible states simultaneously. An object in superposition can be likened to the intersection of two overlapping waves, analogous to ripples on a pond's surface. Mathematically, a superposed object is represented by an equation with multiple solutions or outcomes. Uncertainty principle. A mathematical concept denoting a trade-off between complementary perspectives. In physics, it implies that two attributes of an object, such as its position and velocity, cannot be precisely known simultaneously. For instance, a precise measurement of an electron's position limits the precision of knowledge about its velocity. Entanglement arises when two or more objects are connected to be viewed as a unified system, even when separated by great distances. The state of one object in this entangled system cannot be fully described without considering the other object's state. Information about one object inherently conveys information about the other, and vice versa. The visualization of many quantum physics concepts proves challenging, if possible. Thus, mathematics plays a crucial role in this field. Equations serve to articulate and predict quantum entities and phenomena with a precision beyond the reach of our imaginations. Furthermore, mathematics is essential for encapsulating the probabilistic nature of quantum occurrences. Consider, for instance, the uncertainty surrounding the exact position of an electron, which is often described as existing within a range of potential locations, such as an orbital. Each of these locations carries an associated probability of discovering the electron there. Given the probabilistic aspect, quantum objects are frequently characterized by mathematical constructs known as wave functions, solutions to the Schrödinger equation. Unlike waves in water, which represent fluctuations in water height or sound waves, depicting alterations in air molecule compression or expansion as they pass. A point, wave functions don't correspond to tangible physical property in this manner. Instead, these solutions offer insights into the likelihood of locating a specific object within a range of potential positions. Much like ripples in a pond or musical notes played on a trumpet extend across multiple points and lack confinement to one location.
To a physicist, quantum mechanics is one of the three great pillars supporting our understanding of the natural world, the others being Einstein's theories of special and general relativity. Einstein's theories deal with the nature of space and time and the force of gravity. Quantum mechanics deals with everything else. And one can argue that it doesn't matter a jot whether it's evocative, bewildering, or fascinating. It's simply a physical theory that describes the way things behave. Measured by this pragmatic yardstick, it is quite dazzling in its precision and explanatory power. There is a test of quantum electrodynamics, the oldest and most well understood of the modern quantum theories, which involves measuring the way an electron behaves in the vicinity of a magnet. Theoretical physicists worked hard for years using pens, paper, and computers to predict what the experiments should find. Experimenters built and operated delicate experiments to tease out the finer details of nature. Both camps independently returned precision results, comparable in their accuracy to measuring the distance between Manchester and New York to within a few centimeters. Remarkably, the number returned by the experimenters agreed exquisitely with that computed by the theorists. Measurement and calculation were in perfect agreement. This is impressive, but it is also esoteric, and if mapping the miniature were the only concern of quantum theory, you might be forgiven for wondering what all the fuss is about. Science, of course, has no brief to be useful, but many of the technological and social changes that have revolutionized our lives have arisen out of fundamental research carried out by modern-day explorers whose only motivation is to better understand the world around them. These curiosity-led voyages of discovery across all scientific disciplines have delivered increased life expectancy, intercontinental air travel, modern telecommunications, freedom from the drudgery of subsistence farming, and a sweeping, inspiring and humbling vision of our place within an infinite sea of stars. But these are all, in a sense, spin-offs. We explore because we're curious, not because we wish to develop grand views of reality or better widgets. Quantum theory is perhaps the prime example of the infinitely esoteric becoming the profoundly useful. Esoteric because it describes a world in which a particle really can be in several places at once, and moves from one place to another by exploring the entire universe simultaneously. Useful because understanding the behavior of the smallest building blocks of the universe underpins our understanding of everything else. This claim borders on the hubristic because the world is filled with diverse and complex phenomena. Notwithstanding this complexity, we have discovered that everything is constructed out of a handful of tiny particles that move around according to the rules of quantum theory. The rules are so simple that they can be summarized on the back of an envelope. And the fact that we do not need a whole library of books to explain the essential nature of things is one of the greatest mysteries of all. It appears that the more we understand about the elemental nature of the world, the simpler it looks. We will, in due course, explain what these basic rules are, and how the tiny building blocks conspire to form the world. But lest we get too dazzled by the underlying simplicity of the universe, a word of caution is in order. Although the basic rules of the game are simple, their consequences are not necessarily easy to calculate. Our everyday experience of the world is dominated by the relationships between vast collections of many trillions of atoms. And to try to derive the behavior of plants and people from first principles would be folly. Admitting this doesn't diminish the point. All phenomena really are underpinned by the quantum physics of tiny particles. Consider the world around you. You are holding a book made of paper, the crushed pulp of a tree. Unless, of course, you're reading an electronic version of the book or listening to the audiobook, in which case you will need to exercise your imagination. Trees are machines able to take a supply of atoms and molecules, break them down, and rearrange them into cooperating colonies composed of many trillions of individual parts. They do this using a molecule known as chlorophyll, composed of over 100 carbon, hydrogen, and oxygen atoms twisted into an intricate shape, with a few magnesium and nitrogen atoms bolted on. This assembly of particles is able to capture the light that has traveled the 93 million miles from our star, a nuclear furnace the volume of 1 million Earths, and transfer that energy into the heart of cells, where it is used to build molecules from carbon dioxide and water, giving out life-enriching oxygen as it does so. It's these molecular chains that form the superstructure of trees and all living things, and the paper in your book. You can read the book and understand the words because you have eyes that can convert the scattered light from the pages into electrical impulses that are interpreted by your brain, the most complex structure we know of in the universe. We have discovered that all these things are nothing more than assemblies of atoms, and that the wide variety of atoms are constructed using only 3 particles: electrons, protons, and neutrons. We've also discovered that protons and neutrons are themselves made up of smaller entities called quarks. And that is where things stop, as far as we can tell today. Underpinning all of this is quantum theory. The picture of the universe we inhabit, as revealed by modern physics, is therefore one of underlying simplicity. Elegant phenomena dance away out of sight, and the diversity of the macroscopic world emerges. This is perhaps the crowning achievement of modern science, the reduction of the tremendous complexity in the world, human beings included, to a description of the behavior of just a handful of tiny subatomic particles and the four forces that act between them. The best descriptions we have of three of the forces, the strong and weak nuclear forces that operate deep within the atomic nucleus, and the electromagnetic force that glues atoms and molecules together, are provided by quantum theory. Only gravity, the weakest but perhaps most familiar of the four, does not at present have a satisfactory quantum description. Quantum theory does admittedly have something of a reputation for weirdness, and there have been reams of drivel penned in its name. Cats can be both alive and dead, particles can be in two places at once, Heisenberg says everything is uncertain. These things are all true, but the conclusion so often drawn that since something strange is afoot in the microworld, we are steeped in mystery, is most definitely not. Extrasensory perception, mystical healing, vibrating bracelets to protect us from radiation, and who knows what else are regularly smuggled into the pantheon of the possible under the cover of the word quantum. This is nonsense born from a lack of clarity of thought, wishful thinking, genuine or mischievous misunderstanding, or some unfortunate combination of all of the above. Quantum theory describes the world with precision, using mathematical laws as concrete as anything proposed by Newton or Galileo. That is why we can compute the magnetic response of an electron with such exquisite accuracy. Quantum theory provides a description of nature that, as we shall discover, has immense predictive and explanatory power, spanning a vast range of phenomena from silicon chips to stars. Quantum theory was precipitated, as is often the case in science, by the discovery of natural phenomena that could not be explained by the scientific paradigms of the time. For quantum theory, these were many and varied. A cascade of inexplicable results caused excitement and confusion, and catalyzed a period of experimental and theoretical innovation that truly deserves to be accorded that most cliched label, a golden age. The names of the protagonists are etched into the consciousness of every student of physics and dominate undergraduate lecture courses even today. Rutherford, Bohr, Planck, Einstein, Pauli, Heisenberg, Schrödinger, Dirac. There will probably never again be a time in history where so many names become associated with scientific greatness in the pursuit of a single goal, a new theory of the atoms and forces that make up the physical world. In 1924, looking back on the early decades of quantum theory, Ernest Rutherford, the New Zealand-born physicist who discovered the atomic nucleus in Manchester, wrote, "The year 1896 marked the beginning of what has been aptly termed the heroic age of physical science. Never before in the history of physics has there been witnessed such a period of intense activity, when discoveries of fundamental importance have followed one another with such bewildering rapidity." But before we travel to 19th century Paris and the birth of quantum theory, what of the word quantum itself? The term entered physics in 1900 through the work of Max Planck. Planck was concerned with finding a theoretical description of the radiation emitted by hot objects, the so-called black body radiation, apparently because he was commissioned to do so by an electric lighting company. The doors to the universe have occasionally been opened by the prosaic. We will discuss Planck's great insight in more detail later in the book, but for the purposes of this brief introduction, suffice to say, he found that he could only explain the properties of black body radiation if he assumed that light is emitted in little packets of energy, which he called quanta. The word itself means packets or discrete. Initially, he thought that this was purely a mathematical trick, but subsequent work in 1905 by Albert Einstein on a phenomenon called the photoelectric effect gave further support to the quantum hypothesis. These results were suggestive, because little packets of energy might be taken to be synonymous with particles. The idea that light consists of a stream of little bullets had a long and illustrious history dating back to the birth of modern physics and Isaac Newton. But Scottish physicist James Clerk Maxwell appeared to have comprehensively banished any lingering doubts in 1864 in a series of papers that Albert Einstein later described as the most profound and the most fruitful that physics has experienced since the time of Newton. Maxwell showed that light is an electromagnetic wave, surging through space. So the idea of light as a wave had an immaculate and, it seemed, unimpeachable pedigree. Yet in a series of experiments from 1923 to 1925, conducted at Washington University in St. Louis, Arthur Compton and his co-workers succeeded in bouncing the quanta of light off electrons. Both behaved rather like billiard balls, providing clear evidence that Planck's theoretical conjecture had a firm grounding in the real world. In 1926, the light quanta were christened photons. The evidence was incontrovertible. Light behaves both as a wave and as a particle. That signaled the end for classical physics, and the end of the beginning for quantum theory. Ernest Rutherford cited 1896 as the beginning of the quantum revolution, because this was the year Henri Becquerel, working in his laboratory in Paris, discovered radioactivity. Becquerel was attempting to use uranium compounds to generate X-rays, discovered just a few months previously by Wilhelm Röntgen in Würzburg. Instead, he found that uranium compounds emit les rayons uraniques, which were able to darken photographic plates even when they were wrapped in thick paper that no light could penetrate. The importance of Becquerel's rays was recognized in a review article by the great scientist Henri Poincaré as early as 1897, in which he wrote presciently of the discovery, "One can think today that it will open for us an access to a new world which no one suspected." The puzzling thing about radioactive decay, which proved to be a hint of things to come, was that nothing seemed to trigger the emission of the rays. They just popped out of substances spontaneously and unpredictably. In 1900, Rutherford noted the problem. All atoms formed at the same time should last for a definite interval. This, however, is contrary to the observed law of transformation, in which the atoms have a life embracing all values from 0 to infinity. This randomness in the behavior of the microworld came as a shock because, until this point, science was resolutely deterministic. If at some instant in time you knew everything it is possible to know about something, then it was believed you could predict with absolute certainty what would happen to it in the future. The breakdown of this kind of predictability is a key feature of quantum theory. It deals with probabilities rather than certainties, not because we lack absolute knowledge, but because some aspects of nature are, at their very heart, governed by the laws of chance. And so we now understand that it is simply impossible to predict when a particular atom will decay. Radioactive decay was science's first encounter with nature's dice, and it confused many physicists for a long time. Clearly there was something interesting going on inside atoms, although their internal structure was entirely unknown. The key discovery was made by Rutherford in 1911, using a radioactive source to bombard a very thin sheet of gold with a type of radiation known as alpha particles. We now know them to be the nuclei of helium atoms. Rutherford, with his co-workers Hans Geiger and Ernest Marsden, discovered to their immense surprise that around 1 in 8,000 alpha particles did not fly through the gold as expected, but bounced straight back. Rutherford later described the moment in characteristically colourful language. "It was quite the most incredible event that has ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." By all accounts, Rutherford was an engaging and no-nonsense individual. He once described a self-important official as being like a Euclidean point. He has position without magnitude. Rutherford calculated that his experimental results could be explained only if the atom consists of a very small nucleus at the center, with electrons orbiting around it. At the time, he probably had in mind a situation similar to the planets orbiting around the Sun. The nucleus contains almost all the mass of the atom, which is why it's capable of stopping his 15-inch shell alpha particles and bouncing them back. Hydrogen, the simplest element, has a nucleus consisting of a single proton with a radius of around 1.75 times 10 to the minus 15 meters. If you are unfamiliar with this notation, this means 0.0000000000000000175 meters, or in words, just under 2,000 million millionths of a meter. As far as we can tell today, the single electron is like Rutherford's self-important official, point-like, and it orbits around the hydrogen nucleus at a radius around 100,000 times larger than the nuclear diameter. The nucleus has a positive electric charge, and the electron has a negative electric charge, which means that there is an attractive force between them, analogous to the force of gravity that holds the Earth in orbit around the Sun. This, in turn, means that atoms are largely empty space. If you imagine a nucleus scaled up to the size of a tennis ball, then the tiny electron would be smaller than a mote of dust, orbiting at a distance of 1 kilometer. These figures are quite surprising because solid matter certainly does not feel very empty. Rutherford's nuclear atom raised a host of problems for the physicists of the day. It was well known, for instance, that the electron should lose energy as it moves in orbit around the atomic nucleus, because all electrically charged things radiate energy away if they move in curved paths. This is the idea behind the operation of the radio transmitter, inside which electrons are made to jiggle, and as a result, electromagnetic radio waves issue forth. Heinrich Hertz invented the radio transmitter in 1887, and by the time Rutherford discovered the atomic nucleus, there was a commercial radio station sending messages across the Atlantic from Ireland to Canada. So there was clearly nothing wrong with the theory of orbiting charges and the emission of radio waves, and that meant confusion for those trying to explain how electrons can stay in orbit around nuclei. A similarly inexplicable phenomenon was the mystery of the light emitted by atoms when they are heated. As far back as 1853, the Swedish scientist Anders Jonas Ångström discharged a spark through a tube of hydrogen gas and analyzed the emitted light. One might assume that a glowing gas would produce all the colors of the rainbow. After all, what is the sun but a glowing ball of gas? Instead, Ångström observed that hydrogen emits light of 3 very distinct colors: red, blue-green, and violet, like a rainbow with 3 pure, narrow arcs. It was soon discovered that each of the chemical elements behaves in this way, emitting a unique barcode of colors. By the time Rutherford's nuclear atom came along, a scientist named Heinrich Gustav Johannes Kaiser had compiled a 6-volume, 5,000-page reference work entitled Handbuch der Spektroskopie, documenting all the shining colored lines from the known elements. The question, of course, was why? Not only why Professor Kaiser, he must have been great fun at dinner parties, but also why the profusion of colored lines? For over 60 years, the science of spectroscopy, as it was known, had been simultaneously an observational triumph and a theoretical wasteland. In March 1912, fascinated by the problem of atomic structure,